Hello. This session will be chaired by Professor Ganesh Natarajan from IT Palakkad. Thank you.
Hello, am I audible? Hello.
Yes, I can hear you.
Yeah, good morning, Dr. Venkatekrishnan.
Good morning.
I think we'll wait for a couple of minutes.
Okay.
Probably Professor Bishwa's talk is just getting over.
Yes. The dangers of virtual parallel conferencing.
Yeah, true.
Yeah. All right. I suppose they will give us a signal when that talk is over.
Yeah, definitely.
Okay. We can wait. I'm ready to go whenever you say.
Yeah, sure.
Sir, you can please start the session.
All right. We don't have to wait any longer. Can I start the session?
No, sir, you can start. Thank you.
All right. Thank you. Good morning, everyone, and welcome to the day one of FMFP 2020 on virtual mode. We'll kickstart session one with a keynote talk, and the keynote speaker for the morning is Dr. Venkatekrishnan, who is Chief Scientist and Head, Experimental Aerodynamics Division at NAL Bangalore. Dr. Venkatekrishnan's main interests lie in the field of fluid mechanics and aerocaustics, as well as flow diagnostics. And Dr. Venkatakrishnan and his group have been instrumental in developing new measurement methodologies as well as techniques for launch vehicle noise suppression. And among their contributions include a field-ready electronic target system. Dr. Venkatakrishnan is a fellow of the INAE and the RAES and associate fellow of AAA, and has been awarded the Professor Satish Dhawan Award for Young Engineers in 2011, in addition to the Best Innovation Award from CSIR NAL in 2013. Dr. Venkatakrishnan is a very well-known and eminent experimental aerodynamist, and he's on the editorial advisory board of the Springer journal, Experiments in Fluids. So without further ado, I would invite Dr. Venkatakrishnan to take on the virtual podium to deliver his keynote address titled On the Phase Average Momentum of Fluidic Oscillators. Dr. Venkatakrishnan, please.
Thank you very much, Professor Natarajan, for the kind words of introduction. Let me begin by sharing my talk. I hope the screen is visible.
Yes, Dr. Venkatakrishnan, it's clear. Yeah. Please.
So, good morning to all the virtual audience out there, and good afternoon and evening for those in other parts. I have to begin this talk by thanking the organizers, Professor Amresh Dalal, especially for inviting me to give this keynote address, and for inviting me to share my thoughts about measurement techniques and methodologies in aerodynamics, fluid mechanics. So today we will dwell a bit on the phase average momentum, as to is it really that simple to obtain a phase average momentum. And in this, I need to acknowledge my colleagues at NAL, Ashwin Kumar, who is also a PhD candidate at IIT Bombay, and Dr. N. Karthikeyan, both of the Experimental Aerodynamics Division, and also funding support from the BRNTI for the past several years in this endeavor. So on to today's topic, we are going to look at how do you obtain the phase average momentum of an oscillating flow or of a time varying flow. Now, it is not as trivial a topic as one would assume, especially when one considers that if the feedback mechanism, or it's not a mechanically actuated oscillator, and the feedback mechanism happens to be fluid mechanically driven. So when this happens, then the problems are plenty, as we will see. So it so happens that the topic chosen is that of fluidic oscillators, but it could be any time varying flow with periodicity and jitter imposed on that. So to move on to the next slide. The slide advance. Can you see it in the slideshow mode?
Yes, yes, Dr. Venkatesh.
Is it on the second slide? May I check?
Yeah, it's on flow separation in aviation.
So we start with where is the need for flow control, and then we dwell a bit on this particular flow control methodology that of fluidic oscillator. Look at the problem of obtaining phase average momentum and a comparison of various approaches available, and what are the criteria to evaluate these approaches, and some conclusions. So the story begins, of course, with a separation that of the boundary layer. If you look here at the x momentum equation, and we see that a positive or a adverse pressure gradient always wants to induce a positive curvature to the velocity profile, leading to separation. Flow separation is a no-no in most areas of fluid dynamics, and more than anything in aviation. Flow separation can be seen on landing gears, on engine nacelles, on the wings, winglets, and even on the tail. Actually, very much on the tail, because in cases of one engine inoperative cases, which do occur more frequently than one would imagine or desire, it is the tail which keeps the aircraft headed in the right direction because of its contribution to the longitudinal or directional stability. So it's the tail which actually, you could say, really wags the dog. Take a look at the family of Boeing 7 series aircraft, all the way from 707 to the 787. And if you look at the tails superimposed, they are remarkably the same size. So essentially, every aircraft is carrying around this huge hunk of metal just so that in such a scenario, you do not have a directional problem. So, in so much that a lot of work is concentrated on making the tail more effective. If one were to have a truly effective methodology for active flow control, wherein separation is, if not completely, majorly avoided and or mitigated, you would result in reduction of the tail size by 17%, contributing to a drag reduction of up to 30%, and because you would get an increased 50% side force on using the same size tail, or conversely, you could reduce the size of the tail. Now, what are the flow control strategies which come to mind once one talks about separation? Of course, there is always the well-known passive method, which is always that there is no energy added and is applicable only to certain flight conditions, very simple in design. But it's often noted that this is applicable only to one kind of condition, and you need really flow control to be effective over a wide range of conditions. So we come to active flow control. Here, energy is added to the flow. There's complications in design, but this very often is the choice of most designers, because then you can tailor your flow control to what you want. Hybrid, of course, is a combination of the two, sometimes with benefits, sometimes with pitfalls, so much more complicated. We shall look at the active flow control methodologies. So here, in an active flow control device, the ideal device would have a minimum power consumption, would be robust and rugged, have easy to integrate into the aircraft, have high gain amplitude, and enough bandwidth to handle any kind of problem the separation throws at it. A sufficient control authority. You don't want to use too much power on the active flow device, so it should have a pack sufficient punch in it. And finally, you should be able to inspect the device whenever possible. If you were to broadly categorize active flow control devices, they would fall into the region of fluidic, moving surface, or plasma. The plasma is still a bit of exotic device. We shall focus for the purpose of this talk just on fluidic devices. And within fluidic devices, we see there's a plethora of devices available to us, right from zero net mass flux jets or synthetic jets to steady blowing and suction, pulse jets using valves, and fluidic oscillators, the very topic on which we shall have a focus on today. Fluidic oscillators themselves come in a variety of designs, mainly on the type of the feedback which is given to them, which could be external, internal, resonator, or mutual blockage of two valves or feedback free. We shall, for the purpose of this talk, look only at an external feedback kind of device, which is one of the most common kind of device encountered. What is this fluidic oscillator? So it is instructive to look at the most basic type of fluidic oscillators, which are feedback and feedback free, also just for comparison to let us know where we are on the chart. So these were initially designed for cleaning car windshields and also to supply fluidic logic circuits. And the great attractiveness of these is that they generate a pulse jet when you supply them with pressure. They are very attractive for flow control, having no moving parts, and have disturbances with a controllable frequency. Basically, these exploit fluidics technology by exploiting the mechanism of either wall attachment or fluidic interaction with the feedback free on the right. So if you look at the feedback type oscillator, your basic oscillator is basically a bistable nozzle wherein a primary jet by means of the Coanda effect attaches itself to one of the walls. The Euler-N equation dictates that the pressure rises in the feedback channel, thereby flipping the jet to the other side, and the process starts all over again, generating a sweeping jet at the exit of the nozzle. On the other hand, the feedback free, just for comparison, is wherein you have two jets at high pressure impinging on each other, having an unstable interaction, and the vertical interaction that they have sweeps the jet from side to side, which produces a jet outside. We shall, for the rest of this talk, concentrate on the feedback type of fluidic oscillator you see on the These have been, of course, introduced onto aircraft, and Boeing has been in the forefront of these kind of innovations. In here on the left is the tail of 737 in the NASA Ames tunnel, and you see on the right the tail going into the test section, and this very preliminary experiment by means of smoke flow shows that it is exceedingly effective when the ejectors are on, when the oscillators are on. As you can see, with the deflection of the rudder, the smoke also gets deflected. So there are several issues here that we have. What's the location of the fluidic oscillator array? How do you size it? How do you space it? And what's the plenum pressure required? So if you look at the fluidic oscillator external flow field, on the right you see an excellent visualization from Garib's group at Caltech, wherein it ranges right from subsonic to supersonic, as you will see in this time-lapse video. And one would divide the nature of the behavior into two dominant parts. One is there's a vortex shed during each cycle, as can be seen from the surface oil flow with on the left, wherein vortex is clearly identifiable, so it behaves like a vortex generator. In addition, there is an unsteady momentum injection, as you can see with this momentum being injected into the flow. In fact, the jet goes sonic at the throat. The frequency of sweeping varies with the plenum pressure or the supplied mass to the jet. So there, one would next want to know what are the parameters which affect performance of these. There is a veritable zoo of parameters here, ranging from the inlet width to the mixing chamber, to the feedback channel inlet, to the feedback channel itself, to the nozzle control width, and to the throat, and finally even the divergence downstream of the throat, which is shown to improve flow control. So confronted with this, one of the biggest questions is what is the momentum coefficient, which C mu, which every designer asks for when you want to design the actuator for a certain class of flow. How do you decide how much pressure is the right pressure to blow? What's the C mu relative to the exit? Now this is not a trivial question, more so when the jet is going sonic at the throat and you have no idea of what the density is at the exit of the divergent section. And if you want to obtain the momentum, it is very obvious that a time average momentum will not suffice, and a phase average, which may have looked simple if it was a mechanically controlled device, I will proceed to show that is not possible because you have inherent jitter in the oscillator. So you will ideally need a row of actuators sweeping in phase. So any disturbance can be irrecoverable and catastrophically destroy the efficacy of the oscillator array. So the spacing is also very important, because the interaction is what bounds or pushes more momentum in the x direction, and the measured momentum is directly dependent on the sweep angle, so which itself is a sinusoidal function, which changes with flow rate. So with all these complications, we look at a typical experimental setup on which I will not spend too much time. This is a schematic of the setup at the low speed lab at experimental level. And you have all the required paraphernalia to set up and control the jet to make precise measurements. While there's a number of measurements which have been done on this, ranging from pressure to PIV, we shall today focus only on the pressure measurements, steady and unsteady, and time resolved Schlieren. And it's on the Schlieren that we want to obtain a phase average momentum picture, which one may think would be qualitative, but which is the first step in identifying that we have in fact obtained a true phase average picture in order to apply that to PIV data. So why is the phase averaging so challenging in this kind of flow? So consider this imaging at 7.5 approximately kilohertz of the flow, and this, as you can see, this is the schematic of the oscillator, which is opaque till the exit, and this is what you see on coming out. These two pins mark the exit, and when you look at this and you look at the histogram, you can see that the 1 sigma is quite broad. So it's not, as one would have thought, a precise frequency of operation. And it is this very jitter which makes it inherently difficult to obtain a phase averaged average picture of the flow. Now, phase determination has been around for a while, and there have been many methods, ranging from the hardware method, which is just a phase lock method depending on hardware, to mathematical approaches, to signal processing approaches. The hardware, of course, depends upon a signal from inside the oscillator, and so does the signal processing approach, which looks at zero detection. In the next few slides, we will look at what happens when you compare the phase lock approach against the mathematical approach and the signal processing approach. In the mathematical approach, the approach is that of proper or orthogonal decomposition, wherein we have looked at different types of PODs, whether on the global flow field or on the reference pressure signal inside the oscillator itself. Now the reference pressure signal comes from the feedback channels from the top and bottom, which you see here on the left. And the difference in them is taken as the reference pressure. Obviously, this is not going to be a clean signal, as is evidenced by inspection of the raw blue trace. And we band pass it with the F0 plus minus 8 hertz filter in order to obtain a sinusoidal variation as seen in the spectral plot on the right. So, of course, we need to do image pre-processing. I will not bore you with the details. These are fairly well documented in image processing textbooks, and we can do any of these. These are only performed on the final average images, and not on prior to doing the averaging, so as not to skew the outcome. So let us first look at those which deal with the mathematical approach, that is the global flow field. The first of the mathematical approach, proper orthogonal decomposition, starts with the intensity field and subtracts the time average field from it to obtain the intensity field fluctuations. We essentially need a snapshot POD. So we need to obtain the spatial modes and the temporal coefficients. And we have employed this on approximately 10,000 images. In this particular ensemble, there are only 8,25,000 because sometimes it also depends upon the processing time you require. So essentially, you compute the scaled coefficients. So from the lambda 1 and lambda 2 are their corresponding eigenvalues. So why do we choose these two? We will come to that in a moment. So the phase angle is computed as the inverse tan of the ratio of the scaled coefficients. Now, the window size was chosen as 3 degrees so that we have 120 windows in one cycle, and the phase averaging ends up allocating images to respective bins. So we can very quickly see by an inspection of these that the first two modes which you see, which have a phase shift of 90 degrees in their temporal coefficients, basically are orthogonal to each other, account for the bulk sweeping motion of the jet, and they account for most of the energies in the seen in the flow. So if you were to take those as seen in the SPOD plot on the right, you would account for pretty much all the energy acquired in the process. So once you do these, you distribute the images corresponding to the modes in their appropriate phase bins. So this results in a highly uneven distribution of images, as we shall see shortly. The second method is you do whatever you did in the method 1, and then you sort them here, like here, and you allocate a fixed number to each bin, because as we already concluded, there's a problem with having varying bin image size. So we want to have equal numbers, so we sort them and allocate them. The problem with that, of course, is the starting and ending degrees in each bin vary vastly. We will come to what is the implication of this second method. There, of course, after you define this, there is a third approach. Suppose you did a POD on the pressure signal itself from the inside the oscillator. We took those two pressures, as you saw in the feedback channel top and bottom, divided into two parts, assume two observers, and assume the two observers are simultaneously recording this data, and do a POD of the observer's data. So the first thing you find that the eigenvalues are very different of the two observers. We'll come to why that happens in a moment. We proceed by finding the phase angle of these, and again attribute them to their respective bits. The final method is the signal processing method, and the signal processing method is essentially a zero crossing detector, where again using the data from the feedback channels, and this is a typical cycle seen by the sinusoidal almost variation of the filtered data, and each of the circles depict a time location of the image. A delta t can be defined between any two images over half cycle, and the phase angle theta is given by 360 times delta t by the total time period of that. So these are going to be compared against the hardware approach. The hardware approach is very familiar to most in the audience, so I will not dwell too much on it. Essentially, it takes some kind of signal. We have taken the same signal for consistency, run it through a signal filter and amplifier, find the rising edge by using a zero crossing detector, have a delay generator to set the phase, because essentially it's if you take a sinusoid, you can depict it as a ramp and you divide that into equal parts in time, and the cycle start is measured in real time. The phase is set by varying delta t times t naught, so which gives you the timestamp of the zero crossing, and the assumption is that the period length is fixed, which turns out to be a crucially fatal assumption, as we will see. So now that we have these four methods, how do we compare them? What is the metric for comparison? So the metrics chosen are image distribution of across phases. So you have say 120 or so bins, and do you have equal images in them? Are they distributed uniformly? Statistically, one would want a uniform distribution. So, having 10,000 images, we would think is a good enough number to have statistical convergence. The second is the centerline intensity profile of the phase average image. Higher the intensity, the better it is, because then you have bright areas coinciding with bright areas and increasing it with intensity. Finally, a correlation of each image in the bin against a reference image. So have they been identified correctly? Have they good and high correlation coefficient or not? So the first thing is the image distribution, and we right off the bat see that there are only two which make the cut. That of the phase locked, of course, as it's a hardware driven preset number cycle, and that of the second type of POD, because we decided that we are going to sort them and give equal numbers to each. So the flip side of that is the image count in this is very small, because we are distributing equally. It's a socialistic distribution, if I may. And the other things we see that the POD, the method one, has a highly uneven distribution, because you have a non-circular phase portrait, because the mode energies are not equal, either in M1 or in M3, like we had already seen earlier. The eigenvalues were very different. The zero crossing has a surprisingly and comparatively smoother variation, and there's a maximum of 10% of the deviation. And the window for all of these is plus minus 1.5, as I already mentioned, 3 degrees in width. The second metric to look at would be a centerline intensity profile. So if we took from each of these methods the case of the max deflection of the oscillating flow and drew the center line by standard means looking at gray levels, so how would it go? So here we would expect this being a supersonic flow on the exit, that we would expect that you identify the peaks properly from each of these corresponding to the shocks which you see in the flow. So we see here again that the phase lock performs exceedingly well, followed by the second POD method, the zero crossing method, and the POD M3. But the POD method 1, which is a standard POD method, performs poorly. What happens if you take the case of the center line? So at the mean position, zero deflection. So this is where the velocity of the sweep actually happens to be the highest, like a simple pendulum. And we see here that in this case, the criteria of the peak being 1.3 times the mean intensity value makes that POD M3 scores highest, followed by the phase locked, and then the zero crossing, and the methods 1 and 2 perform pretty poorly. If you compare then the two front runners, phase locked and the zero crossing method, we see that compared to the phase locked, the zero crossing method has a narrower peak, whether you see for the max deflection case or for the zero deflection case. The phase-locked method may have higher peaks, but it has a much larger spread than the zero crossing. And this is on ensemble averages for 10 consecutive images in each phase bin. Now, the final metric, criteria 3, would be correlation of an image with other images in the bin. How like are the people who are put together? So you take all the images in a bin and take one of the as a reference image, do 2D cross correlation, then you normalize by the reference, and then you plot the RI. Then what you would expect is all of them should be within a small band around the max, about the mean value, right, which corresponds to the maximum of the RI. So the sigma and the mean of RI is for one phase angle. You do this for all the methods again, and we immediately start to see some differences. We see that the phase lock method is the worst, despite having uniform number of images and supposedly identifying the peaks. And because the criteria is you want the maximum mean correlation coefficient, meaning all likes are together, and the spread of them should be as low as possible, meaning there are very few outliers which do not belong in the group. You can see that POD M3 and zero crossing perform pretty well, and the phase lock is the worst among them. Now, what if you correlated instead of one image with the time averaged image over all of them in the bin? How close are you to the average member of the population? Then the correlation coefficient plots in this manner, and you can see that the M3 and the zero crossing again come out on top, with the phase lock again doing one of the worst with the lowest mean correlation coefficient. You can again repeat this for the standard deviation, and then you will see again that it is the M3 and zero crossing which do exceedingly well. So for either of these methods, either time average or the single reference image. So if one were to do a summary of this analysis, you would look at a chart like this. So you have the methods on the column 1 and look at various metrics like usage complexity, image yield, how are the images distributed uniformly in each bin, which of them are good at feature extraction, meaning show out the peaks, and how correlated, similar are they to other people in the bin. You would see that the person who stands out is like the student who never comes the highest in each subject, but is the topper in the class. That is the zero crossing method. So you find it is never the highest yield or the best in terms of image distribution, but it is good in everything. So one would then conclude that zero crossing should be your method of choice for any of these kind of flows where a fluid dynamic feedback gives jitter. So this, having applied this, we can just take a look at what we get, and sure enough, from the flow on the left, this is the time phase averaged Schlieren image extracted from it, wherein all the shocks are reproduced exceedingly well, which is important for flow. And you can see that you can do that over the entire cycle without problems, both at the extreme deflections as well as the center line. So one of the lessons we learned from this exercise, that the phase averaged flow field is challenging to get, especially at high oscillation frequencies where there's a jitter in the periodicity. And if you look at mathematical or signal processing or phase lock techniques applied to time resolved Schlieren, you have to identify metrics to evaluate them, because it is not often a straight answer. So you have to look at the image distribution per phase bin, centerline intensities, or feature extraction, and how close they are with others. So the result shows that the zero crossing method is the Chevy. It is the second best maybe in every metric, but is the best overall. And this kind of method is what should be used to obtain phase averages of quantitative methods like PIV or even the background oriented Schlieren. Thank you. I'll be happy to answer any questions.
Yeah.
Thank you, Dr. Venkatakrishnan, for an exciting talk. May I now invite questions from the audience? Questions for Dr. Venkatakrishnan from the audience, please. Dr. Venkatakrishnan, I have a question.
Yes, please.
Yeah. So one of the not so recent efforts, which also compared different techniques for phase averaging, there was an emphasis on a mathematical method referred to as a partial or full Hilbert transform.
Yes.
Could you just comment on the approach and whether it can be
Yes.
hybridized with POD-like approaches for improving the phase averaging
Yes.
computation?
The POD method, I did not delve deep into that for paucity of time, can also have a Hilbert transform method, wherein you look at various energies in the spectral domain. So, however, that becomes complicated, and we find that it often results in errors for feature extraction. I am aware of the work that you allude to, and also would point out that most of the time these are done on very low frequency oscillating flows. So as soon as we go to the compressible domain, not only do we have the problem that the frequencies go up in such flows, also we have the problem that there's another inherent fluid dynamic jitter. As you're obviously very well aware, you have, as you go into the compressible domain and increased degrees of under expansion, you have, say, what's known as shock jitter. So that gets superimposed on the existing method, and while Hilbert transform method may be good enough for a low speed, low frequency flow, it's not does not work for these kind of flows.
Yeah. Thank you, Dr. Venkatakrishnan. Yeah, thanks for the clarification. Any other questions from the audience? If you have questions, I would request you to raise the hand on Microsoft Teams, and please go ahead with asking the question. Okay, I'm assuming there are no further questions. If that's the case, on the behalf of the organizing committee of FMFP 2020 and on my own personal behalf, I would like to thank Dr. Venkatakrishnan for a very exciting talk and for sharing some of their recent research efforts on flow control and fluidic oscillators with all of us. Thank you once again, Dr. Venkatakrishnan, for your very nice and exciting keynote lecture. And thank you all for joining us.
Thank you very much.
Yeah. So I would request all the participants to now join across the sessions in the 4 halls as FMFP continues on. Thank you, everyone. Thank you, Dr. Venkatakrishnan, once again.
Thank you, Professor Natarajan.
Yeah, thanks.
We thank you, Professor Ganesh Natarajan, for chairing this session. Thank you.
Thank you, everyone.
Yes, sir. Good morning, all. This session will be chaired by Professor Partha Sarthi Guwahati from IIT Guwahati. Thank you. I request Dr. Professor Pattada to start this session.
Thank you for giving me this opportunity to conduct this session. And on behalf of FMFP 2020, I welcome all the participants and all the audience in this session. All of you might have already have some exciting lectures. And without doing any delay, let's start this session. Okay, the theme of this session is microfluidics. So our first participants is from BITS Pilani, Mr. Tilak AK. His topic is two-phase numerical study on the effects of hybrid nanofluid on the performance of microchannel heatsink. So I request Mr. Tilak to start his presentation. Thank you.
Yeah, good morning, sir. Yeah, so my topic is two-phase numerical study on the effects of hybrid nanofluid on the performance of microchannel heatsink. Yeah, hello. Hello. My name
Yeah,
is
you go
Raj
ahead.
Kumar. My topic is two-phase numerical study on the effects of hybrid nanofluid on the performance of microchannel heatsink. The outline of the presentation is the introduction, model description, results and discussion, and the conclusion. Microchannels find as the conducts with hydraulic diameters than 1 mm. Tuckerman and 1981 was to propose and demonstrate the effectiveness of microchannel cooling, dissipating the heat generating electronic device. Due to its high heat transferability, small size, and working fluid demand, the microchannels are getting cooler, and it is an important alternative in management in many applications. Efforts have been made in the past decade to enhance the performance of microchannel heatsinks through geometry modifications such as flow obstructions, bifurcations, develop new cross sections, etc. Also, another way to do this is to have the application of fluids with better thermal physical properties, such as nanofluids, which has received a plenty of attention in the past. Some of the prominent literature available to the effect of nanofluid in microchannel heatsink are by Lee and Mudwar, Chung et al., and Kleth et al., which have used the most popular alumina nanofluid and have reported the very similar findings. That is, there is an increment in performance with increasing Reynolds number and volume fraction of the nanoparticles. In 2012, Mane ETL used alumina and copper oxide, and they have employed a two-phase mixture model, and they have also reported the same finding. In 2010, Abrahami et al. Reported the use of MWCNT, and they have reported enhanced heat transfer using CNT in comparison with the spherical nanoparticles. Hybrid nanoparticles have seen a marked growth in past few years, and the application of hybrid nanofluids have the potential of providing the higher heat transfer rates. Nimgada Venkatava Subbiah in 2015 and 17 have employed the use of hybrid nanofluids such as alumina plus silver, copper aluminum hybrid nanofluid, and have observed a better heat transfer coefficient values compared to that of the base fluid. Last year, we have reported that the CNT use of CNT nanofluid shows higher frictional entropy generation rate, but shows the potential of enhanced heat transfer rates better compared to the alumina nanofluid in the microchannel heatsink. Hence, the combination of both alumina and CNT hybrid nanofluid could be effective in enhancing the performance of an microchannel heatsink. So the main objective of this paper is to explore the effectiveness of alumina CNT and the combination hybrid alumina plus CNT nanofluid in microchannel heatsink. Also, the use of the models such as the Hamilton-Crosser model for the evaluation of thermal conductivity and Brinkman equation for evaluation of viscosity for the CNT nanofluid is not applicable since the CNT nanofluid has a shear thinning behavior. So the present paper is focusing on use of the models which are related to the CNT nanofluid which has a shear thinning behavior and to explore the effectiveness of the hybrid nanofluid in the microchannel heatsink. In the present work, the microchannel heatsink used for the analysis was adopted from Q and Mudwar from 2002. The figure below shows the dimensions in mm of that particular heatsink, adopted heatsink. Now, the computational domain as shown here is being selected for the simulations. The properties of CNT and alumina are shown here for the density, specific heat capacity, and thermal conductivity respectively. Also, the properties of the substrate of the microchannel heat sinks, that is the oxygen-free copper, is also shown here. Now, for the purpose of simulation, the CNT is considered to be well dispersed in water and as a primary phase for the analysis, while the alumina nanoparticle is being considered as secondary phase. This is due to the shape of the carbon nanotubes being cylindrical with a high aspect ratio and non-uniform length. So here the properties of water, which is the base fluid, is considered as a function of temperature as per the correlation that is given here. Also, the values of density and specific heat capacity are calculated using classical models. For the purpose of thermal conductivity, the correlation given by Zhu in 2005 is being used, which is given here. Now, for evaluation of viscosity of nanofluids for spherical nanoparticles, the Brinkman equation was very popular, which is given here. But the CNT nanofluids have a non-Newtonian behavior, so Brinkman equation cannot be used. So the viscosity for CNT nanofluid is given by non-Newtonian power law, where the flow consistency index and the flow behavior index was evaluated by the Levy ETL using the experimental data given by Ding ETL. So the EUDFs are written as per the correlations given here, and they were incorporated during the simulations. For the purpose of simulation, the mixture model is being used. So a mixture model is a two-phase model that considers coupling between the phases is strong, and within any control volume, both volume fraction of the primary phase and the secondary phase exist. So here the governing equations are written for a mixture of continuous and dispersed phases instead of writing separately for each phase. So the continuity momentum equations are given here, energy and the volume fraction equation, slip velocity and drift velocity. Now the mixture model employs a algebraic slip formulation, and according to marine ETL, the slip velocity is given here. The dry fraction is taken from the Schiller and Naumann as given here. Now coming to numerical method, the simulations have been carried out in the ANSYS 15. ICM CFD is used for the mesh generation, but both for the solid and the fluid zones, quadratic hexahedral cells are used. According to Fedorov and Visconta, the high concentration of node near the entrance and the compact non-uniform grids near the walls were taken. Boundary conditions are as mentioned here. The solution method involves the use of simple algorithm. The second order point scheme is employed for momentum energy equation, while quick scheme is employed for the volume fraction. The convergence criteria is set to 10 to the power minus 6 for the continuity momentum equation, while 10 to the power minus 9 for the energy. Now coming to the data reduction, the rate of heat transfer to the fluid inside the microchannel is given here. For evaluation, the parameters such as average heat transfer coefficient, thermal resistance, and pumping power consumption as given here. Now coming to the validation of the model, the obtained numerical results with the experimental data for microchannel heatsink used for the experiments by Lee and Midwar in 2007 were used as it is shown in the figure. For the comparison, the data of the difference of the mean temperature with respect to mass flow rate is shown here. For the mass flow rate varying from 2 to 6 gram per second. You can see from the figure that the obtained numerical results are in well agreement with the. For the grid independency test, the grid independency test is carried out for 2% volume fraction alumina at an inlet flow rate of 2 meter per second. From the grid independency test, 4.18 million mesh shells was selected for the further simulations. Now coming to the results, here we have compared the performance of mono water, the base fluid, the mono nanofluid, and the hybrid nanofluid. So from the figure you can see the increasing velocity. The hybrid nanofluid is showing better performance compared to the alumina nanofluid, the CNT nanofluid, as well as the base fluid. Although the CNT is showing better performance than alumina and the base fluid. Now coming to the pressure drop, you can see for the lower velocity, the hybrid nanofluid is having a higher pressure drop. But as we move forward to higher velocities, the pressure drop is lower for the hybrid nanofluid. The reason behind this can be devoted to a decrease in viscosity with increasing shear rate, that is increasing fluid velocity, which is a characteristic of the shear thinning fluids. Now, if we compare the thermal resistance with the pumping power consumption, we can see the base fluid water is having a higher value of thermal resistance with respect to pumping power consumption. While if you see for a hybrid nanofluid, it is having the least thermal resistance for the pumping power with the pumping power consumption. So from characteristic curves, we also get the information about the preeminence of the hybrid nanofluid over the mono nanofluid as well as the water as the working fluid. Now coming to the conclusions here, the numerical simulations were carried out to compare the thermohydraulic performance of hybrid nanofluid with mono nanofluid, either alumina or CNT, and water as working fluid for the microchannel heatsink. According to the results mentioned, the conclusions are drawn that the hybrid nanofluid has better cooling performance. Due to high shear thinning behavior of CNT, the high pressure drop is observed for hybrid nanofluid at lower velocity, while the low pressure drop is reported at high inlet velocity. Also, the hybrid nanofluid has lower thermal resistance and pumping power consumption compared to the other working fluids. Thank you.
Thank you, Mr. Tilak, for wonderful presentation. So, from the audience, if there is any questions, you can raise your hand. Any questions from the audience? Okay, if there is no questions, I have one small questions to you. So, why do you think that, what is the physical reason behind this better performance of this hybrid system?
Sir, hybrid nanofluid, it is a combination here of CNT and alumina. So the thermal conductivity, the net thermal conductivity value is being increased. Although the addition of the nanoparticles of alumina is 1% only, but the thermal conductivity value is increased compared to the mono, either it be CNT or alumina. That's why there is an increment in the performance, sir.
Okay. Okay, thank you. As we are running out of the time, let's move to our next presentation. Next presentation will be given by Mr. Tejas from NIE Mysore. His topic is numerical investigation of single phase heat transfer in converging and diverging microchannel.
Hello.
Yeah.
Hello to all the dignitaries present. We would like to thank the Committee of FMFP for giving us this opportunity to present our topic on numerical investigation of single-phase heat transfer in converging and diverging microchannel. We are also grateful for Mr. N.S. Srikanth for providing valuable guidance and support throughout our project. Over the years, the size of the electronics has been reducing. The miniaturization of electronics raises a severe challenge for cooling. Insufficient cooling results into degraded performance and in long run may lead to device failure. In order to meet higher computational speeds, the packaging density should be increased. This results in hotspots. Approximately heat flux of 250 watt per centimeter square is dissipated in these hotspots. The conventional cooling system like fans fail to provide effective cooling since air is used as coolant which has bad thermophysical properties. The heat transfer rates are also low. Hence, liquid cooling is preferred for higher heat dissipation like liquid immersion cooling, direct liquid cooling. These systems are less efficient for small devices and the space occupied is more and are unsuitable for high ambient temperature. The effects of insufficient cooling can be seen in these diagrams. Thus, a novel cooling system is required. Microchannel is one such system which is robust and can effectively dissipate heat for a small quantity of fluid flow due to high surface to volume ratio. In a fully developed internal flow, Nusselt number is constant and thus the heat transfer coefficient is inversely proportional to the hydraulic diameter. The cooling units can be 35 to 50% smaller in size. less coolant required, and the factors neglected in macro channels should be considered in micro channels. Factors such as viscous dissipation and compressibility factors cannot be neglected in micro levels. The earliest study in single-phase fluid flow in ducts can be traced back to the year 1978 by Shah and London. They studied forced convection of laminar flow in ducts for different cross-sections. Tuckerman and Pease in 1981 investigated the problem of achieving compact, high-performance forced liquid cooling for planar integrated circuit. Kundlikar SG in his study states that reducing the channel enhances the heat transfer mechanism. Summary of the literature review is that due to various challenges advantages, microchannel cooling technology has been the focus of research to many researchers. Many numerical and experimental work has been done in this field which considered the effect of aspect ratio, cross-section and surface parameters. From the literature survey, it was found that the effect of converging, diverging on the microchannel heat transfer performance is less concentrated compared to other parameters affecting it. The objectives of the current study is to model the single-phase heat transfer process in microchannels using ANSYS Fluent and validate the result using the existing experimental data and correlations, and to study the effects of slope of convergence and divergence on single-phase heat transfer coefficient and pressure drop in microchannels. Cross-section of converging rectangular microchannel is as shown in the figure. Water was considered as the working fluid. It enters the microchannel with a fully developed velocity profile at 300 Kelvin. A grid-independent test was carried out in order to ensure the best mesh spacing of approximately 3 into 10 to the power 6 grid elements. The hydraulic diameter was maintained at a constant of 450 micrometer. To achieve steady-state analysis, pressure bed solver is used for simulation. Simple method is used for introducing pressure into the continuity equation. The simulations are performed for a convergence criteria of 10 to the power minus 6. The boundary conditions are shown in the table. The inlet condition or a laminar velocity inlet type where the velocity was varied from 0.5 meter per second to 2.2 meter per second. The outlet was given pressure outlet. At the bottom wall, a constant heat flux of 50 kilowatt per meter square was given. And the side and top walls were given symmetry. The numerical results were validated for the rectangular straight channel with Shah in London, a microchannel with an aspect ratio of 0.5 and a Reynolds number of 100. The result number obtained from the numerical study was in agreement with the result number obtained from Shah in London. From the graph given below shows that the numerical model used to predict Nusselt number for one wall constant heat flux is in good agreement with the values obtained by V.V. Daraya and S.G. Kundlik. The table shows the dimension considered in the present study. The angle of convergence is represented in terms of slope m, which is nothing but the height at the inlet minus height at the outlet divided by the length of the microchannel, and the slope is varied from 0 to pi. The effect of convergence on Nusselt number for a rectangular microchannel. The result of Nusselt number for the straight channel were compared with converging microchannel. From the graph, it can be clearly seen that the value of Nusselt number is increased linearly with the increase in Reynolds number and the slope of convergence. Effect of slope of convergence on Nusselt number. By keeping the Reynolds number 250 as constant, the Nusselt number value was plotted against the increasing slope of convergence. From the graph, we can clearly see that the Nusselt number varies linearly with the slope of convergence, and a best fit curve was plotted. The increase in Nusselt number in my converging microchannel is due to the increase in velocity along the length of the microchannel, as shown in the graph of velocity versus fractional length. As there is this increase in velocity along the channel length is in accordance with the conservation of mass, as the area of the microchannel decreases along the channel length, there is increase in velocity, and since Nusselt number is directly dependent on the velocity gradient, there is an overall increase in Nusselt number and pressure drop in the microchannels. Comparison of converging and diverging microchannel. There was a decrease in heat transfer rate for the diverging microchannel compared to the straight and converging channels. This is because as the cross-sectional area of the channel increases, there is decrease in the velocity along the channel length. This results in decrease of pressure drop and heat transfer coefficient. Both heat transfer coefficient and pressure drop plays equally important roles in microchannel cooling. For converging and diverging microchannel, it can be inferred that pressure drop is the limiting factor of a converging microchannel. Hence, diverging microchannel could be used in order to obtain reasonable heat transfer coefficient at practical pressure drop. Hence, we focused our study on diverging microchannels. The effect of hydraulic diameter on heat transfer coefficient and the pressure drop. Initially, we plotted heat transfer coefficient and pressure drop for varying hydraulic diameter, but we came to observe that at an hydraulic diameter of 100 micrometer, there was a exponential increase in heat transfer coefficient as well as the pressure drop. So we considered 100 micrometer diameter microchannel. The effect of slope of divergence on the pressure drop and heat transfer coefficient for a diverging microchannel. Considering the 100 micrometer diameter microchannel and varying the slope of the 100 micrometer diameter, uh, heat transfer coefficient and pressure drop were plotted and the graphs are shown below. From this we can see that heat transfer coefficient decreases linearly till the slope of 0.0012 and is increased after that slope. Similarly, the pressure drop is decreased from 7 bars to 4.3 bars and a constant is obtained after 0.0012 slope. So, to know the reason behind the peculiar behavior, further analysis is conducted to study the local heat transfer coefficient and pressure drop along the fractional length of the channel. It is clear that as slope of the divergence increases, the amount of pressure drop in the entrance region also escalates. Same trend was in the case of heat transfer coefficient. The decrease in the local pressure drop and heat transfer in the second half of the channel length is less drastic for channels with higher slope of divergence. As a result, there is an overall rise in the heat transfer coefficient as the slope of the convergence increases from 0.0012. Also, the overall pressure drop becomes constant with the increase in the slope from 0.0012. Converging microchannel has a better heat transfer coefficient compared to a straight channel both at low and high flow rates. The Nusselt number increased by 49.29% for converging channel of slope 5 at a Reynolds number of 1000 compared to a straight microchannel having same hydraulic diameter. At a given flow rate, the Nusselt number can be increased by increasing the angle of convergence of the microchannel. At a Reynolds number of 250, the value of Nusselt number increased by 7.46% for slope of 1 to slope of 5 for converging microchannel having same hydraulic diameter. Diverging microchannel had a lower heat transfer coefficient. Also, there was not much change in heat transfer coefficient on increasing the divergence angle. Diverging microchannel had a lower pressure drop and hence lower pumping power was required. The future work of the current study includes the optimization of converging diverging microchannel for a range of characteristics parameters and validating it with experimental data, and the investigation of heat and flow characteristics in straight converging diverging microchannel in two-phase flow. The two-phase flow study includes both numerical and experimental study. Thank you.
So thank you, Mr. Tejas, for this presentation. I would like to ask the audience if there is any questions. You can raise your hand. Any questions from audience? Okay. Tejas, One thing is that, as you have mentioned, that this converging and diverging microchannel, how it is influence this heat transfer. What was the surrounding medium of this microchannel you have taken?
Around the micro, it said it's atmospheric.
Atmospheric, right? So
Yes, sir.
there, if that means it is an open channel. Is it an open channel?
Yes, sir. The top wall is considered as it's an open channel.
Okay. So, okay, so that should be, I think, highlighted. So the surrounding medium will have some effect, right?
Yes, sir.
We have neglected the conjugate effects.
Okay. Okay, fine. Okay, thank you. It is a good work. Okay, so let's move to our next presentation. Next presentation is by Mr. S. Hajra from IIT Madras. He will present on this viscoelastic droplet dynamics in viscoelastic matrix. Okay.
Welcome everyone to FMFP 2020. I'm Shomik Hajra, working with Dr. Ashish Kumar Sen of IIT Madras and Professor Sushanta Mitra of University of Waterloo. Today I'm going to talk about viscoelastic droplet dynamics in viscoelastic matrix. So the hydrodynamics of microscale objects like beads, cells, vesicles, droplets are of immense importance because they have a crucial role in drug delivery, biological and diagnostic application. So we can answer questions like why does a healthy blood cell behave differently than a diseased cell? A rigid bead can mimic a stiff or dead cell and reveal the answer. Also, we can answer questions like why do white blood cells marginate to the vessel wall while RBCs flow through the center? So we have Newtonian fluids like water, which obeys Newton's law of viscosity and has strain rate independent viscosity, and we have also blood, saliva, which whose viscosity is a function of strain rate. So the motivation behind our study is to find the migration logic at low Reynolds number of the particle. So the Newtonian viscoelastic, shear thinning viscoelastic, or the shear thinning can be the property of both continuous phase or the discrete phase, and the combination which we choose to study here is the droplet dynamics of Newtonian viscoelastic nature in the viscoelastic and shear thinning viscoelastic continuous phases. So let's talk about the forces acting on the object in inertial versus non-inertial region. So in inertial microfluidics, we find mainly two kinds of forces. One is wall effective force, which acts on the object from wall to the center, and the shear gradient force, which acts in the opposite direction, that is the from center towards the wall. And as these two forces are counteracting, the particle migration will depend on both of them counteracting each other, and when these two balance each other, the particle will find its equilibrium position. On the other hand, in the non-inertial regime, we find that an object which is deformable will be acted upon by non-inertial lift force, and also if the continuous phase is non-Newtonian, we find viscoelastic lift forces acting on the object. So for a deformable object at very low Reynolds number, both of these forces will be acting from wall towards the center. So here we talk about the work that we had published in Soft Matter 2019, which talks about the lateral migration of viscoelastic droplets in a viscoelastic confined flow, role of discrete phase viscoelasticity. So we have one two inlet microchannel with one T junction, which flow polyvinyl pyrrolidine, which is constant viscosity viscoelastic fluid. We generate droplets of PDMS or castor oil, and we study the droplet dynamics. We find that at PEP 3%, 6%, or 10%, the migration behavior of Newtonian and viscoelastic droplets are completely different. So at PEP 3%, PDMS and castor oil droplets both migrate to the center, Same thing happens for PEP 10%, but at PEP 6%, castor oil droplets migrate to the center while lateral migration of the PDMS droplet is arrested. From these plots, we find that at PEP 3%, PDMS is migrating at faster rate than the castor oil droplet. At the 10%, the same thing is happening, but at the 6%, PDMS, the lateral migration is arrested, so it is maintaining a constant distance along the channel length, but castor oil again migrating from the wall to the center. So we hypothesize that there will be a force which originates from the discrete phase viscoelasticity, which will be switching its direction based on the PEP concentration. So at PEP 3% and 10%, it is acting on the object from wall to the center. That's why they are migrating at higher rate. And at the PEP 6%, it is switching its direction. It is acting from the center towards the wall and arresting its lateral migration. So let's see these videos one by one. At 3%, we will see that both PEP, PDMS, and castor oil droplets are migrating towards the center. At 10% also, we'll see that both PDMS and castor oil droplets are migrating towards the center, but at the different rate. But at 6%, we'll see that PEP 6%, the PDMS is migrating along the wall, while castor oil droplets are migrating towards the center. So we scale the force based on the difference of the first and second normal stress difference, and we find that the vertical component of the resultant force is our FVD, and finally we get a form like this, where the prefactor F is a function of viscosity ratio K, Weisenberg number of discrete phase, and elasticity is zeta, and also it's a function of mu m, which is a viscosity of matrix phase. G is the droplet size, gamma dot is the strain rate, and H is the spacing of the droplet from the wall. So based on these finding, based on the physics, we can also perform the viscosity bed droplet sorting. So we have again two inlet channel. PVP is coming in and filling the channel, and we are generating castor and PDMS droplets. And as we just shown that PDMS droplet will flow along the channel wall and castor oil droplet will migrate to the center, we can actually efficiently sort them. So these are the PDMS droplets which are flowing along the wall and collected in this outlet, and castor oil droplets which are flowing through the center and being collected at the castor oil droplet. So in this way, 100% efficient sorting is possible. Next, we discuss a very recent work that has been published in Physics of Fluid, cross-stream migration of droplets in a confined shear thinning viscoelastic flow, role of shear thinning induced lift. So here we have again a two inlet channel, and we flow the shear thinning viscoelastic fluids like polyethylene oxide, and we study the dynamics of viscoelastic PDMS or Newtonian castor oil droplets. So we hypothesize that in addition to all the forces that we discussed earlier, due to matrix shear thinning, there will be one force acting on the particle or the object from center to the wall, which we call FSM. As a result, we'll see that both viscoelastic droplets and Newtonian droplets will migrate towards the wall, and they will basically follow their original streamline, and they will not migrate to the center. Also, we find that due to this force, bigger droplets will migrate towards the wall, or they will finally follow their original streamlines. As we can see that for blockage ratio 0.33, the lateral migration is arrested, therefore following their original streamline. However, for smaller droplets as small as beta equals to 0.16, they are migrating from the wall to the center. As we can see that all the beta equals to 0.16 lines are having an upward trend, which means that they have migrated from the wall to the center. So this is where we see that size-based migration is also coming into picture. we try to scale this force. So we have a particle in the STV or the shear thin viscoelastic fluid. We find that viscosity and strain rate at the bottom of the particle is different from the viscosity and strain rate at the top of the particle. So we try to scale this force by equating the migration behavior of the same viscosity, elasticity of shear or only a viscoelastic fluid like PVP. And as in the PEO, the migration is being arrested, we say that if PEO had been the only viscoelastic fluid, it would have experienced a similar kind of lateral migration as in the case of PVP. So we see that FSM or the ratio of FSM divided by delta mu delta gamma into d square. So delta mu is basically the viscosity drop across the particle, delta gamma is the strain rate drop across the particle, and gamma d is the particle diameter, which scales with d by h with the exponent 1.7. So as a result, we find that FSM is scaled as delta mu, delta gamma, d raised to 3.7 and h raised to 1.7. So in conclusion, we studied the lateral migration dynamics of viscoelastic and non-Newtonian droplets in viscoelastic and shear thinning viscoelastic medium. We identify contrasting migration behavior of viscoelastic and Newtonian droplets, and we propose the presence of a force FVD which originates from the viscoelasticity of the discrete phase, which scales as a prefactor, which is a function of viscosity ratio, elasticity ratio, and Weisenberg number. And also, internal property-based sorting is possible. We also studied the droplets in STVE mediums, which exhibited size-based lateral migration behavior. We propose the matrix shear thinning induced force FSM, which scales with delta mu, delta gamma, size d, and spacing h. Size and property-based sorting is also possible. I'd like to thank my supervisor, Dr. Ashish Kumar, and my lab mates, all the funding agencies for continuous support. Thank you.
Thank you, Mr. Harsha, for this nice presentation. Now I would like to open up this session to audience for any questions they have. You can raise your hand if you have any question. Okay, I assume that there is no questions. From my side, I have one small clarification. You have said that this PDMS droplet you are using, right?
Yes.
So it is, I mean, you can change this. It is a droplet. That means you are using liquid PDMS?
Yes.
Okay. So it is not like that you can change this cross-linker and you can modify its rheological property. It is not like that, right?
Yeah.
Actually, we can. We have added cross-linker with the base, and that's why we are able to generate the droplet. So if we purely use the base, it will be too viscous for the microchannel to produce the droplet. So the resulting viscosity of the PDMS phase that we have used is 666 millipascal second, while the base is 4000 millipascal second. So we have actually reduced the viscosity by adding the cross-linker. Yes, and if we vary the cross-linker proportion, then we can change the rheological property also. Yes.
Generally, if you add the cross-linker and make it more rigid, kind of droplet, right?
With time, it will cure. Obviously, it will cure, but we limited our experimental time within 1 hour. So within 1 hour, it is viscoelastic liquid. Okay. So if we let it cure, then it will be solid. Yes.
And if you change that, you have seen a drastic change in the behavior.
Yeah. So we've pinpointed one particular base is to curing agent ratios. For that only, we could generate the droplets. If it change slightly, we can still generate, but bigger, I mean, higher change will not facilitate the droplet generation. So from generation point of view, we limited the cross-linker proportion, but otherwise you can always do that. Some other geometry, yes.
Okay, thank you.
Thank you, thank you.
Let's move to this next presentation by Mr. P. Karan. He is from IIT Kharagpur, and his topic is deformation behavior of viscoelastic microchannels with axially graded wall. Okay, wall softness. Okay.
Greetings, fellow researchers and respected professors. Today I will be presenting the study on deformation behavior of viscoelastic microchannels with axially graded wall softness. The authors are listed on the slide. I am Pratyaksh Karan and I shall present on behalf of the group. We are all affiliated with Department of Mechanical Engineering, IIT Kharagpur. The broad area of research to which our study belongs is microfluidics. With the advent of advanced microscale fabrication and operation technologies, microfluidics has evolved to cater to a wide array of technological applications. One major area of such applications is biomimetics, which is essentially the technology of replicating in vivo biological materials and physiological processes on laboratory scale fabricated in vitro structures. A sizable chunk of biomimetics target vasculature, which is a network of blood vessels running through our bodies. From a biomechanical perspective, two crucial aspects of vasculature are A. The softness of blood vessel walls, and B. Variations in wall softness along the vessel length. Both these aspects have profound effects on the hemodynamics as well as the transport of pre-existing and externally supplied particles like RBCs and injected drugs. As a result, before designing procedures aimed at manipulating the physiology of blood vessels, a prime example being targeted drug delivery, it is crucial to properly model these two effects. Towards this end, we list out two of the features of blood vessels which are liable to be pertinent. First, the tissue bulk beyond vessel wall is generally heterogeneous. And second, the vessel wall and the bulk beyond are viscoelastic in nature. Hence, when designing biomimetic modules for vasculature, it is a crucial requirement to commensurately replicate the gross effects of these two features on vessel shape evolution and blood flow. Keeping this requirement in focus, here we study Poisson flow in a circular microchannel drilled in a big block of polymeric material. This setup is very commonly used to mimic blood vessels. While the general algebra follows similar to the traditional treatment of Poisson flows, there are a few caveats. First, the channel wall deformation leads to variation in channel radius at different axial locations. These variations are considered small enough that the flow remains Poisson. Second, the wall deformation is obtained by modeling the polymer block using the Kelvin-Voigt constitutive formulation for its viscoelasticity. Third, outlet pressure is not taken as zero but is assumed to be the pressure head due to flow through a drainage tube of given diameter and given length. Fourth, while implementing the model for test cases, we impose flow rate and outlet pressure so as to best mimic some of the physiological situations we target. And fifth, all aspects of the system response, those imposed as well as those recovered, are decomposed into sum of sign series. As can be seen on the right half of the slide, this assists us in modeling the viscoelastic nature of the polymer block. With the developed model, we first grossly assess how does the viscoelasticity of the polymeric block affect the channel deformation. For this, we impose the flow rate shown in the left picture and recover the deformation response shown in the right picture. The parameter nu is proportional to the viscosity of the polymeric block. We can see that with a higher nu, there is a larger lag in wall deformation, but the magnitude of wall deformation gets smaller. Next, we consider the case of a channel with graded softness along channel length. For this, we choose two particular PDMS microchannel setups which we had employed in one of our former studies, which is the first reference at the bottom. In the first setup, the cross-linking ratio of base polymer to the curing agent is increased linearly from 5 to 25 as we go from inlet to outlet. This corresponds to the light blue lines in the plot. And in the second setup, the cross-linking ratio is 5 throughout the channel except in the middle where it is 25. It is known that channel softness varies with cross-linking ratio. As such, we have taken the variation of Kelvin-Voigt parameters of PDMS for different cross-linking ratio based on the second reference. We impose the same flow rate profile as the previous slide on these setups and obtain the deformation as shown in the left figure. The monotonically decreasing wall deformation for the first setup and the increased deformation at the middle of the channel for the second setup are expected outcomes. The consequence of polymer viscoelasticity can be seen as the lag in deformation compared to the imposed flow rate. However, the axial variation of this lag is shown in the right figure, and this variation is visibly small. What this implies is that while magnitude of wall deformation gets affected by the imposed axial gradation in polymeric properties, there is no appreciable effect of this gradation on the viscoelastic response. In all, we arrive at the deduction that in order to obtain appreciable axial variation in lag, we have to choose a combination of material and curing conditions that enables axial variation of elasticity and viscosity of the polymeric block in a non-proportional manner. Next, we attempt replicating the deformation behavior for carotid artery as reported by Sojimo et al. In their experimental study. We impose the same flow rate as that of Sojimo et al. For our setup and consider the two situations of the polymer block being purely elastic and viscoelastic. The parameter values for each case is taken such that the maximum wall deformation is identical for the experimental data and the two situations. We can clearly see that when the block is considered viscoelastic as compared to purely elastic, there is a lag in the deformation response. However, as we can see, we are not able to exactly recover the same deformation response as the experiment, even after considering the block to be viscoelastic. We identify three possible issues that could be causing this limitation. First, the sum of signs fit does not appreciably replicate the flow rate of the experiments, as can be seen from the left figure. This issue could possibly be dealt with by employing a DFT methodology rather than sum of signs methodology. Second, there are inherent inhomogeneities in the tissue surrounding the carotid artery, which does not get replicated in the homogeneous polymeric block we are considering. And third, possibly, Kelvin-Watt model is not a general enough viscoelastic model, and we may need to consider a more general model like standard linear solid or Pune series. Having identified the limitations in the last slide, we now set a relatively simpler target and attempt to replicate a full-scale computational study by Wang et al., which in turn was targeted at replicating the flow and deformation behavior in carotid arteries. A key contrast in their setup and ours is that they had replicated the blood vessel as a tube, while we replicated the blood vessel as a channel in a block. They had considered three tubes with three different viscosities. We first obtained the deformation corresponding to these three materials in our setup, represented by the thin lines. Since ours is a block rather than a tube, the deformation obtained is expectedly much smaller than the reference data. Next, we consider much softer materials quantified as having lower elastic modulus, such that the deformation we get is closer to the reference data, which are presented as the thick lines. We can observe a much better match of wall deformation behavior with the reference data compared to the previous slide. In conclusion, we first recap three key observations. First, a higher viscosity of the polymeric block causes more delay but smaller magnitude of wall deformation. Second, to recover effect of axial gradation on deformation delay, elastic modulus and viscosity of the polymeric block have to vary non-proportionally along the axial length. And third, appreciable replication of wall deformation dynamics in carotid arteries, as we have just shown in the previous two slides, demonstrates the potential to utilize our model to get design principles for biomagnetic modules targeted at vasculature, specifically carotid arteries. We next list three avenues of improvement. First, we could have a DFT-based numerical implementation. Second, we could employ a more general viscoelastic constitutive model for the polymeric block. And third, we have to accommodate radial inhomogeneities in the material beyond the blood vessel wall. In closing, we emphasize that the long-term vision for this study is to aid biomimetics by providing design goals for selection of material and fabrication processes for specific vascular physiologies. Thank you.
Thank you, Mr. Karan. Now I'll open up this session for any question from the audience. You can raise your hand if you have any question. Any question from the audience? Okay, Mr. Karan, as you have said that your long-term vision is to mimic this carotid artery, right?
Yeah.
Now this, how you will think of this possible implementation of that? I mean, how you will generate this different morphology in the cell, I mean artery wall and all. So can you comment on that?
So the first way to do it is by varying the cross-linking ratio, as I had said. So that should allow us to get different softnesses along the length of the channel. Plus, not just the cross-linking ratio, by varying the curing time also, it should be possible to get proper variations in the viscosity and elasticity of the material. But this would require a substantial amount of literature survey. The second thing is that we want to better replicate the radial inhomogeneities. Right now, I don't know how this should be possible, but something has to be figured out for that. Because right now, the polymer block, you can have axial variations by putting in slots and curing different cross-linking ratios in different slots. But that can be done, this variation can be obtained in an axial direction. How to obtain such variation in radial direction is difficult right now.
Yeah, that is good. I mean, you have considered this physical properties like rheology of this cell wall and all, but in reality there is some, I mean, chemical interactions also going on between this fluid and this artery wall. So are you planning to consider those as well, or?
No, not right now. Right now the focus is to get some replication of biomechanical aspects, meaning that mainly the channel profile under flow, the time evolution of channel profile under flow, and the flow dynamics. Once this is replicated properly enough, then the chemical effects, replication of chemical effects can be targeted.
Okay. Thank you, Mr. Karan, for your nice presentation.
Thank you.
Now let's move to our next presentation by Mr. Shamik Hajra from IIT Madras, and he is going to present on particle migration in shear thinning viscoelastic fluid.
Welcome everyone. I'm Shamik Hajra, working with Dr. Ashish Kumar Sen of IIT Madras and Professor Shushantika Mitra of University of Waterloo. Today I'm going to talk about particle migration in shear thinning viscoelastic fluid. So let's start with the basics of rheology. We find non-Newtonian fluids of time-independent behavior, which include shear thinning fluid. These fluids can be expressed in terms of viscosity and strain rate. So viscosity is strain rate dependent, and several models are available to describe such fluids. For example, Pavallo model, the Cross model, or the carrier viscosity model. For example, the Cross model is expressed in this way, where eta is viscosity at any given flow rate or the strain rate. Eta infinity is the infinite shear viscosity, eta 0 is the zero shear viscosity, m is a constant, gamma dot is the strain rate, and n is the exponent. On the other hand, we have viscoplastic fluid, which follow Bingham plastic model or Casson model. We have shear thickening or dilatant fluid and viscoelastic fluids. And we also have time-dependent behavior like thixotropy or rheopecty. So in terms of viscoelasticity, we need to understand the behavior of shear thinning and viscoelasticity together. So in nature, we have synthetic polymers like viscoelastic, but not shear thinning nature, which are PVP, polyvinyl pyrrolidine. We have viscoelastic and shear thinning fluids, which are polyethylene oxide. And we also have shear thinning, but not viscoelastic, such, for example, xanthan. So if we can compare the PVP and PEO, from literature we see that in case of PEO, the viscosity drops with strain rate, but for PVP, the viscosity remains same. On the other hand, both PVP and PEO will have crossover frequency, which we basically get from crossover of G prime and G double prime. The crossover frequency at which the two curves meet each other, the reciprocal of that frequency will give us the relaxation time. So let's talk about the origin of the non-Newtonian behavior. So we see that polymer molecules which are coiled and entangled at lower shear rates gradually become disentangled and finally fully straightened out. So all these changes in microstructure facilitate flow, that is, they lead to the lowering of their apparent viscosity with shear, which leads to shear thinning behavior. Also, the concentration of the polymer is important. So when the polymers are dilute, the polymer concentration is too less, then these blobs are isolated. As we keep on increasing the concentration, these blobs come together, and at some point the entanglement starts. So from dilute to concentrated entanglement regime, we find the several crossover frequencies. So this C star is basically differentiating dilute to semi-dilute, entangled, unentangled regimes, and this is important because this C star is considered as the onset of shear thinning. On the other hand, origin of viscoelastic force is attributed to the anisotropy of the stress tensor. For example, sigma xx minus sigma yy gives rise to first normal stress difference, which gives rise to the viscoelastic force. Sigma yy minus sigma zz gives rise to second normal stress difference, and which gives rise to the counter-rotating vortices across the channel cross section. And this viscoelastic force is independent of the channel dimension, or it is observed in microscale as well as macroscale. So let's talk about the forces acting on object in inertial versus non-inertial regime. In inertial microfluidics, we find mainly two kinds of forces. One is wall lift force, another one is shear gradient lift force. Wall lift force acts on the particle or the object from wall to the center, and FLS, or the shear gradient lift force, acts in the opposite direction. Both of these forces are dependent on the fluid density rho, fluid velocity u, size, particle size a, and channel dimension w. On the other hand, in non-inertial regime, we come across non-inertial lift, which acts only on the deformable object. So this force is dependent on the viscosity eta, strain rate gamma, particle size r, particle distance from the wall h, and f of 1 minus v is the factor which takes care of the deformability. On the other hand, if the fluid is viscoelastic, we come across the force which is called viscoelastic lift force. It is also a function of particle size a. Eta p is the polymer contribution to the solution viscosity. Lambda is the relaxation time, and it is also proportional to gradient of gamma square, or the gradient of strain rate square. So coming to our work, we study the particles migration regime in the shear thinning viscoelastic fluid. So the viscoelastic lift force acts from the wall to the center, and we hypothesize that due to matrix viscoelastic shear thinning nature, there will be another force which we call FSM, or the matrix shear thinning induced force, which will act on the particle from wall to the center to the wall, and it is scaled as delta mu. The drop in viscosity across the particle, delta gamma, drop in strain rate across the particle, d is the particle diameter, and h is the distance of the particle from the wall. So microparticles in polyethylene oxide and polyacrylamide, we see that there are 4 different migration regimes. First one is original streamline regime, where particles don't show any specific migration pattern. In bimodal regime, as we increase the Reynolds number and Weisenberg number, we see that particles are aligning themselves across the channel wall as well as at the channel center. As we further increase the Reynolds number or the Weisenberg number, all the particles will migrate towards the channel center line, and as we increase the flow rate or the Reynolds number, particles start defocusing from the central or core regime. On the other hand, particles in polyacrylic acid, they show mainly 2 kinds of migration regime. One is original streamline regime. Again, there is no particular migration fashion. But on the other hand, if we increase the Reynolds number, these particles will try to align themselves across the channel wall. This is the onset, and finally they will be prominent wall migration. So let's talk about the migration regime in PEO in detail. As we discussed, these are the experimental images of these 4 regimes that we discussed in the previous slide. Original streamline to bimodal to center migration to defocusing in a 60 micron microchannel, straight rectangular microchannel. So we observe that BM to CM migration, the change or the transition is happening because the corner regions are becoming thinner, or the corner regions are shrinking because the Reynolds number is increasing. As a result, particles which were placed at the corners are all coming towards the channel center. As a result, we see the central migration regime. Now, we varied the polymer molecular rate, and for each polymer molecular rate, we varied the concentration as well. So we see that for PO4 MDA, below 1%, there is no particular migration pattern. So we call this the original streamline regime. For 1%, we see that there is BM to CM to DM transition. At 1.5%, the flow rate or the Reynolds number at which this transition were happening becomes lower. That means the defocusing regime is widening because the shear thinning has been prominent. And beyond 2%, the central migration regime shrinks, and most of the part we will see that there is defocusing regime. On the other hand, PO1 MDA, if we increase the concentration, we'll see that for 0.5% there is mainly original streamline regime. At higher flow rate there is central migration. At 1% there is BM to CM transition. At 2% there is BM to CM to DF transition. Now at 2% the shear thinning will be more prominent. So at higher flow rate, shear thinning induced lift will be more prominent and defocusing regime will appear. And at 3%, interestingly, the central migration regime completely disappears and migration pattern directly switches from BM to DF regime. On the other hand, in polyacrylamide, we will see similar kind of migration pattern, that is below 5%, below 0.5%. There is no migration pattern, but beyond 0.5% there is BM to CM to DF migration. So it follows PO4 MDA migration regimes. And on the other hand, as we have discussed in the previous slides, that in PAA, prominent wall migration will be observed. So in case of PAA, we see that beyond 0.1%, there is original streamline to wall migration regime is coming into picture. So here we hypothesize that in addition to wall-directed FSM, there should be another force which we call that secondary flow-induced body force, FN2. That will come into picture, and that will overpower the center-directed FVM, that is the viscoelasticity induced force, which was trying to push the particles to the center, and that's why all the particles are aligning themselves across the wall. So I would like to thank my supervisor, Dr. Ashish Kumar Sen, my lab mates, all the funding agencies for helping us with the ongoing research. You can write me to samik.hajra@gmail.com. Thank you.
Thank you, Mr. Hajra. So is there any questions from the audience? Yeah, we have one question from Mr. Shantosh Kumar Jena. So you can ask the question. Yeah, go ahead. Yeah, hello. Mr. Shantosh, you can go ahead.
Yes, sir. Mr. Samik,
yes.
Am I audible?
Yes.
My question is, what is the diameter of the droplet what you are using? for migration?
So these are rigid microparticles, polystyrene beads of 15 micron diameter.
Achha, you are entering using that directly in the disperse phase so that it will along the channel it will move.
Yes.
And what are the flow rates you are using for the
flow rates were varied from 0.005 microliter per minute to 20 microliter per minute.
And one more question is that have you considered the effect of continuous phase inertia force along with the force during that migration?
No. Actually, we deliberately kept the Reynolds number very less than 1. So it is sufficiently less than 1 in our case. So
then what you are telling that when Reynolds number increases, what you are telling that the particles are migrated more towards center, and then larger increase, then it will be little DM regime it will go.
Yes.
And then why did it happen? At what Reynolds number exactly you are working? That what you are telling the Reynolds number increases.
Yes. So if you have seen the regime plot, so it varies from 10 to the power minus 6 to 10 to the power minus 3. So we say that it is sufficiently less than 1. So 10 to the minus 6 to 10 to the minus 2 or like that. So this is the Reynolds number range. So it is channel Reynolds number. Particle Reynolds number will be even lesser.
Okay.
So inertia effect will be completely negligible.
And one more thing, when it increases, what exactly happens so that the particles are segregated more towards center? Means that because of that shear gradient lift force or inertial lift force, which is more?
No. Here the only force responsible for their center migration is this FVM or this elastic lift force that we discussed in the literature slide. So only one force, FVM or the elastic lift force.
Okay. Thank you.
Thank you.
Thank you, sir.
Okay. Thank you, Mr. Hajra.
Yes. Thank you, sir.
So let's move to our next presentation by Mr. Santosh Kumar Jena. He is from IIT Bhubaneswar, and his topic is experimental analysis of droplet generation in T-junction microchannel. You can start.
Hello everyone, I am Santosh Kumar Jena from IIT Bhubaneswar, going to present my topic on experimental analysis of droplet generation in T-junction microchannel. So this topic belongs to a droplet generation which belongs to a broad area of microfluidics. So as far as my area of research is concerned, we will go step by step from droplet microfluidics and then that methodology to be followed, then the various results, then summary of work. So this introduction part, I will go to explain the microfluidics normally refers to the branch which deals with the behavior, precise control and manipulation of fluids and particles in a channel which is of the order of micron. So micron means it may be of smaller size, maybe micrometer or nanometer, or maybe smaller volume of microliter or nanoliter or picoliter. This microfluidics comes into picture around 3 decades ago. But before that, after a great talk by Professor Richard Feynman in 1959, that there is plenty of room at the bottom, that micro working and micro level comes into picture. So at that time, that electronics industry drastically changed their concepts and do much more research in this micro level work. But in the last 3 decades, this microfluidics comes into picture. And as far as microfluidics is concerned, it has many sub branches like continuous flow microfluidics, droplet microfluidics, digital microfluidics, acoustofluidics, and optofluidics, and so more also. So my area of research belongs to this droplet microfluidics. So in droplet microfluidics, there are many aspects like droplet generation, droplet coalescence, droplet mixing, droplet splitting, droplet sorting, many things. So my as far as my topic is concerned, it belongs to a droplet generation process. So in droplet generation, broadly classified into two categories. One is passive method and one is active method. In passive method, we do not need an external source of energy for generating a droplet. But in active method, there are external source of energy required for generation of droplets. So in passive method, the major passive methods you can see here these three One is that capillary flow, or we call this co-flow fluid, passive method of droplet generation. Then T junction, this middle one, and this bottom one. You can see this is a flow focusing of droplet generation. So on that, by doing literature survey, we found that the major parameters that affect the droplet size majorly are the geometric dimension, its contact angle, viscosity of the fluid, capillary number of continuous phase, presence of surfactant, and rate of flow. So all these major parameters affects a lot for the droplet generation process. But as far as my topic is concerned, I focused the work on capillary number of continuous phase, flow rate ratio, and different fluid combinations, uh, which ultimately tells us that the viscosity of different fluids and the effect on droplet size and frequency of droplet generation in T junction. So, in order to carry out this all the experimental work, and experimental setup is being developed in our laboratory. So, in this experimental setup, you can see here this is a schematic diagram of the setup for droplet generation inside the microchannel. So, this all the channel which is used for droplet generation is made up of acrylic, or we can call this a PMMA. And for fabrication purpose, these channels are fabricated using CNC milling, and after that, thermal bonding process is followed. So, which is used for preparing this microchannel. And for pumping the fluid through the channel, two syringe pumps are used through which the fluids are pumped through this channel. And you can see here, this top of the syringe pump, we mark this as continuous phase channel, means it, the fluid flows to the main channel is continuous phase, and this fluid which is flowing through this bottom, perpendicular channel, we call this as disperse phase channel. And in order to capture this video and the process, we use a high-speed camera along with a attached with the computer. And to visualize the process, we use inverted microscope. And at the outlet, you can see a beaker is used, which is used to collect the mix of fluid normally at the form of a beaker. So here you can see we use normally three different continuous phase fluids like in silicon, mineral oil, and silicon oil. And all the cases, dispersed phase used is distilled water. So this on the bottom figure you can see what is the shape of the droplet inside the T junction during when the flow occurs continuously. So here you can see the main channel continuous phase fluid. Here you can donate this as QC, and from the bottom channel or orthogonal channel you can see QD is flowing. Width of the both the channel is noted as WC and WD. And here you can see the neck. How this neck forms when the dispersed phase flow enters to the continuous phase flow, then penetration occurs initially. So as the flow continues, then this neck length increases. An interface is created and the neck length increases. And as the continuous phase flows, it will try to deform the neck to the along the length. And after a certain time, a kink will be formed and the droplet breakup occurs. And the shape and size of the droplet depends upon the flow rate ratios of both the continuous and dispersed phase, geometric dimension, and the viscosity of the fluid, and so many other parameters. So based upon this setup, we conducted experiment for three different fluid combinations, what I told previously, and based upon that, we found a few results. So in this result and discussion part, I want to show you this first plot. You can see it is L by WC. This is a non-dimensional droplet length, where L is known as this droplet length, and this WC is the channel width of the continuous channel, and this capillary number of continuous phase at the x-axis here you can see. So in this you can see for different fluid combinations like mineral oil, silicon oil, and hexadecan oil having different flow rate ratios. We conducted experiment over a wide range of capillary number, that is of the order of 6 into 10 to the minus 3 to 0.23 is capillary number range. And what we found is that the same trend as previously literature suggested, that as capillary number of continuous phase increases, this droplet length decreases. But this similar thing here we find, you can see for this solid one symbol, this cross symbol, and this half field symbol completely shows for all the cases the droplet length decreases. And as flow rate ratio decreases, the droplet diameter also decreases. The reason is that flow rate ratio decreases means that it is unable to penetrate quickly, and the continuous phase quickly breaks the droplet at the interface, so the droplet diameter decreases. And also here you can see, as from the literature, that people have found different regimes. Here also we are able to generate the different regimes like squeezing regime, dripping regime, and jetting regime. So the left hand side shows the different regimes for mineral oil, And this right hand side shows the different regions for hexadecanol, and all the results were for flow rate ratio of 0.5. Here you can see this squeezing regime for mineral oil occurs at capillary number 0.003, then dripping regime at 0.063, and jetting regime at 0.190. And for the this hexadecan case, it is slightly less. Means the jetting regime you can see it is occurs at 0.014, and the possible reason is because of this less viscosity, the flow rate of the continuous phase increases drastically due to high velocity of the continuous phase. So as a result, it tries to drag the interface at a longer length at a very quick time. So that's why it will occur at a very less capillary number. Here you can see I plotted for a non-dimensional droplet length against Weber number of dispersed phase for varying capillary number of continuous phase. And you can see here as Weber number increases, droplet diameter increases for a fixed capillary number. But as capillary number increases, droplet diameter decreases. As you can see from capillary number 0.0025 to 0.1, it is the bottom one, the droplet diameter decreases. And as here actually this Weber number increases means the dispersed phase flow rate is increased for the different flow rate ratios. So as a result of which, as the dispersed flow rate increases, it will drag the interface along with the continuous phase. It increases the helps to increase the length of the droplet, for which the droplet diameter increases. So this is one interesting study what we have studied. And, as far as frequency is concerned, you can see the frequency of droplet generation increases with increase in capillary number of continuous phases. So which shows that for very high frequency rate we found for hexadecan at low capillary number as compared to mineral oil and silicon oil. As mineral oil and silicon oil has a little higher viscosity ratio. So and all the trend you can see here almost follows a linear trend of this frequency of droplet generation. So these are all the findings what we found from our experimental results. So the summary of the work is in the current work we conducted a systematic study over a wide range of varying parameters like capillary number of continuous phase, flow rate ratio, and Weber number of dispersed phase. And it is observed that the droplet size decreases with an increase in capillary number of continuous phase, but increases with an increase of Weber number of dispersed phase for a fixed capillary number. Also, different regimes of droplet generation like squeezing, dripping, and jetting we found and investigated properly, and the frequency of droplet generation also we studied, and we found that it increases with increase in flow rate ratio. So these are all my summary, and few of my references you can see. So,
Thank you, Mr. Santosh Jena. Now I would like to open this session for any questions from the audience. Any questions from the audience? You can raise your hand if you have any question. Okay, it seems that there is no question. I have one thing that you have said that with increasing this Weber number, this length of this droplet is increasing, right?
yes, sir.
Can you physically explain that? I mean, why it is happening? This is a little bit counterintuitive, right? So, can you explain physically why it is so?
Actually, sir, what I have done in that experiment is that by fixing capillary number while increasing Weber number means I increase the dispersed phase flow rate actually for a fixed capillary number. What I have shown in that images. So as what I found, sir, as increases that dispersed phase flow rate. So what happen for the same capillary number means shear force will be same. So and due to the increase of dispersed phase, it will affect that the same shear force acting the means the penetration, so that the droplet will drag a more distance because of that inertia force of this dispersed phase. So that's why the region, and I am also trying to dig more, sir, to analyze properly. But till now, what I have conducted experiment, found this physical explanation, sir. Because of that force coming from the dispersed phase, drags itself to a larger length, so that droplet diameter increases. What I found.
Okay, so what is the typical flow rate you have used for this dispersed phase?
Dispersed phase, sir, I have used
5 into, no sir, 1 minute. Sir, 20 microliter per minute to 700 to 800 microliter per minute. As my channel size is around, sir, 300 micron. The width of the channel. Depth is 200, sir, thick for all channel.
Okay. So, what is your channel that made of?
Channels are acrylic, sir, PMMA.
Okay. Okay. Yeah, I think you just need to look into details of this observation. This is an interesting observation.
Yes, sir. I am working on that also, and I am trying to develop some model also, kind of thing.
Okay, fine. Thank you.
Okay, thank you, sir. Thank you.
Thank you. So let's move to our next presentation by Mr. Vaibhav Jaiswal from IIT Bombay. He will present on paper-based microfluidic pump for point-of-care application.
Hello everyone, I am Vaibhav Jaiswal. I will be talking about paper-based microfluidic pump for point-of-care application. This work is guided by Professor Prasanna Gandhi, Department of Mechanical Engineering, IIT Bombay. The objective of the present work is the development of model for prediction of volumetric flow from paper-based microfluidic device and the development of setup for experimental investigation and analysis of results. The motivation of the work comes from the spontaneous motion of liquid through small capillary and porous media. Thus, our aim is to use the capillary force dominant in mini and micro scale to drive the flow. Coming to the literature survey, Wang and al. Developed a model to predict the flow from filter paper. They assumed a filter paper to be equivalent to a thin radial capillary with capillary pressure difference driving the flow. Result shows a constant volumetric flow through the filter paper. Figure 1 shows the volume of liquid in reservoir and flow rate with respect to time. Wattman number 4 filter paper gives a higher flow rate than Wattman number 1 filter paper. A linear relationship between flow rate and sector angle is also reported. As the sector angle increases, the flow through the filter paper also increases. Elizalde and al. Developed a generalized equation relating wetted length, cross-section of filter paper and flow time. The equation is solved for constant velocity condition and cross-section shape is obtained. Experiments were conducted on filter paper and on slit microchannel as shown in figure 3, in which dimensionless length is plotted with respect to the dimensionless time. As the liquid enters the region of variable cross-section, a linear relationship between non-dimensional length and non-dimensional time is observed, which means a constant velocity of flow in the domain. Model is reported to obey prediction with a variability of around 20%. In this slide, mathematical model for prediction of volumetric flow through the microfluidic pump is reported. First of all, equation for flow resistance through the filter paper is derived. Then, total resistance is obtained by adding resistance offered by capillary tube and filter paper. Laminar Pauli's flow is assumed inside the capillary for determining flow resistance. From the graph, we can see a steady decreasing flow for initial 4.5 seconds, after which flow rate is gradually reduced. Volumetric flow rate comes out to be maximum at a distance of 1 mm from the capillary tube end with a value of 120 microliter per minute, and then flow rate continuously decreases to 13.84 microliter per minute at 30 mm and goes on reducing as the wetting length increases. Numerical simulations are performed with the help of COMSOL Multiphysics 5.5, in which a geometrical domain for fluid flow analysis is made. For simulation simplification, capillary tube is also assumed to be made of porous media. The governing equation for the flow consists of Darcy law and is combined with continuity for both gas and liquid phase. Initial and boundary conditions are taken from the Wicking in paper strip, a COMSOL documentation file. The figure shows the propagation of liquid front from one end to another end with respect to time. The simulation is carried out for different radius and graph for flow rate is plotted. From the graph, it can be seen that as the radius of sector increases, the time duration for which constant flow rate is predicted also increases, with maximum flow rate of around 3.5 microliter per minute for all the sector radius. Flow stops when the liquid front reaches the end of filter paper because at this point filter paper is saturated and there is no capillary force to drive the flow. In this slide, we will discuss about the microfluidic device and the experimental setup. The microfluidic device consists of three components: inlet, capillary tube, and filter paper. Liquid first enters the pump through inlet, moves through the capillary tube, and then spread through the filter paper. Filter paper absorbs the liquid and with the help of which flow is maintained. The flow of liquid is measured with the help of optical displacement sensor, which senses the drop in liquid level in the reservoir. The rate of change of height multiplied by the cross-section area gives the volumetric flow rate through the capillary pump. From the experiments, we observe that the liquid front took around 150 to 200 seconds to reach end of the filter paper. The average flow rate during initial 150 seconds comes out to be 5.54 microliter per minute with the variability of around 40% from experiment to experiment. This variability is because of random fibrous network in filter paper, sensitivity towards inlet pressure, temperature and humidity dependent evaporation. In the present work, we have discussed about a possible low-cost alternate for passive pumping device, which is able to deliver a constant flow. Simulation predicted a maximum flow rate of around 3.15 microliter per minute, while flow rate of 5.54 microliter per minute is obtained from experimental investigation. The difference in numerical and experimental result is because of assuming rectangular channel to be of porous media, which actually is a capillary tube in the experimental setup. Time period for constant flow can be increased by increasing the radius of sector-shaped filter paper. Refinement of experimental setup, ambient temperature and humidity control is needed to decrease the experimental variability. These are the reference paper that I have reviewed while doing this work. At last, I would like to thank FMFP 2020 for giving me the opportunity to discuss this work with you all. Thank you.
Thank you, Mr. Weaver, for this nice presentation. So I would like to ask the audience if there is any questions. Is there any questions from the audience? Okay, so Mr. Weaver.
Yes, sir.
Yeah, so you have said that there is the discrepancy between this mathematical model and this experimental results.
Yes, sir.
Okay, so you have said that because of this square channel you have assumed it is because of that reason. So
Yes,
do you
sir.
think there is some other cause of this limitation apart from this experimental error or something?
Okay. So apart from that, I think, sir, because of the viscous forces, because of the viscous forces that are not that are say dominantly considered in porous media and are not considered in the mathematical model. And but in actual experiments, these things are taken care because of the physical phenomena. So so I think this viscous nature of forces, if we remove the porous thing, then this viscous nature of forces, as well as the placement of the placement of filter paper at the end of capillary, will also have an effect on the flow rate. That I can say.
Right. And there may be that this capillary size of this filter paper, it also may be random. Right.
Yes.
So that may be another point to be
Cause
considered.
no. Yes, sir. Yes, because
Okay.
different grades of filter paper have different porous structure, and that can also affect the flow rate in the dome.
Right, and that too that has some distribution of this force, right?
Yes,
It is not exactly that same for particular filter paper. Anyway,
yes, sir.
so thank you for your nice presentation. Now let's move to the next presentation, uh, which will be delivered by Mr. Shashikumar GN from Homi Bhabha National Institute, and he is also associated with Bhabha Atomic Research Center, Berg. So the topic will be this multi-objective optimization of microchannel for improving mixing characteristics.
Hello everybody, I'm Shashi Kumar from Homi Bhabha National Institute, Mumbai. I will be presenting my work on multi-objective optimization of microchannels for improved mixing characteristics. The contents of the presentation include an introduction followed by solver that was developed, and we will discuss about its validation, the active mixers and passive mixers. These macro mixers have been discussed. We will define the problem that needs to be optimized. We'll discuss about the hybrid optimization solver that was developed, a validation case, and followed by a conclusion. So, to introduce a micromixture, it is a device having a precise static features that are generally much less than 1 millimeter. The device has multiple applications in various fields, in chemical industry, in pharmaceutical industry, and many more. The point I would like to emphasize here is every micromixture is a predecessor to a microreactor, which is generally used in the industry. So the part which we will be concentrating in this presentation is the micromixture, which comes before the microreactor. So we would like to reduce the length of the micromixture by improving its effectiveness. So micromixtures are classified as active mixtures and passive mixtures. Active mixtures are generally used external source of energy, while passive mixtures have some complex structures within the mixtures that enhance the diffusion and advection to improve mixing. The key parameter for micromixture is mixing efficiency. Here, in this discussion, we use composition deviation coefficient as a measure of mixing efficiency. Microchannels operate in translation flow region. Here we demonstrate for next number of points. The unified solver is capable of resolving flows from continuum to transition flow region, which is based on Conceptor PJK model. For a binary mixture of 2 dimensions, the solver uses 5 equations at each mesh point. When you talk about the validation case, we take up a validation case of a multi-component viscous unified solver. Here we show a mixing test case of nitrogen and carbon monoxide gas. Both are separated by a separator at the beginning till 5 micron till this level, and the width of the microchannel is 1 micron. So we find when we plot the composition coefficient, deviation coefficient, we could get a curve like this. And when the composition deviation coefficient reaches 1% of its initial value, we call the system has attained its mixing capability. So the gap between the opening is here, the opening is here. From this opening till the time where it has a 0.01 of CDC, we call it the mixing length. When we compare the mixing length with our mixing length, with the present work and with the literature, we are actually overestimating by 10%. But still, we are able to predict with a great accuracy. And when compared to DSMC, it takes much lesser time, almost 10% of the time what a DSMC solver takes. Study of microchannel have shown shown that its mixing ability increases with increase of net number. This has come from various test cases that were performed. The velocity slip in the x direction at the wall has given us insight what needs to be done for improving the mixing in the microchannel. You can see it depends on the P gradient, the velocity gradient, temperature gradient, and the concentration gradient. The terms in the right hand side of the equation are a combination due to viscous, thermal, and concentration gradient to the slip velocity slip. This shows that the lighter gas would be moving faster than the heavier gas under the influence of this gradient. So what we can do is the mixing ability of the micro mixture can be improved by modifying these gradients. An active mixture by use of pressure differential is demonstrated here at two Knudsen numbers, one is slip flow and another in transition flow region. And in both the cases, we have taken a reference of equal pressure and a differential pressure at the inlet. So we find a differential pressure improves the mixing by reducing the composition deviation coefficient. Similarly, the similar things happen in the transition flow region. When we see plot, we find the advantages are remarkable in slip flow region, but the advantage is not appreciable in the transition flow region. A second study with active mixture has been performed using a differential temperature. The inlet temperature have been maintained constant, but the wall temperature of the microchannel has been altered. In all the cases, the inlet pressures are maintained same for nitrogen and carbon monoxide. So here also we find there is a advantage in mixing by reduction. It is shown as a reduction in composition deviation coefficient in transition zone as well as in slip flow. But the quantum of advantage is more in the slip flow zone compared to the transition flow zone. Also, you can see the mixing of the microchannel is enhanced in the transition zone than in the slip flow zone. As a third test case, we would like to demonstrate passive mixture and its ability to improve mixing in transition flow region. For this, we take two pairs of baffles and optimize their shape, size, and location inside a microchannel. For this purpose, we develop an optimizer which uses CFD solver to evaluate the objective function, and optimum is which should give me the best of the best required solution. And my optimizer should be using minimum number of function evaluation so that the total time for optimization is minimum. So ant colony optimization is global optimization solver, which is population based method, which ensures that you actually reach your global optimum. The advantage of ant colony is that it brings in independence from user-defined bounds or parameters. But being a population-based method, it requires many function calls. We add a local optimizer to ant colony method so that it accelerates the process of optimization. Newton-Raphson method have been tried, which is a root finding method. The goal vector driven optimization is an inverse optimization problem. We generate the Jacobian matrix with the gradient of the objective function for a given perturbation, and that is used in the state update equation so that new set of parameters can be evolved for the next iteration. So how we implement it? We take the hand-following optimizer and we have the Newton-Raphson method. The best number in the hand-following method is transferred to the Newton-Raphson method and a local search is performed. This local search improves my the best member in the population, and this member is added back to the population as an elite. So this addition improves my speed of job, and we have validated with a standard test case of Ziegler, Deb and Carter test case, where it is a non-convex Pareto, which is a non-convex Pareto trend. So what we see here is when we do with a hybrid optimization method, it reaches to the optimum directly. On the contrary, the ant colony method takes a longer path. You see, it takes a longer path and reaches to the optimum. Because of this, it takes larger number of iterations, and still more or less the same optimum is obtained. But this is closer to the Pareto trend than compared to the ant colony. So when we come up with our actual optimization test case, the two of the functions were chosen as the mass flow rate and the composition deviation coefficient. So our target was to reduce the composition deviation coefficient and keep the mass flow rate as maximum as possible. Because when you introduce baffles into the system, mixing improves, but your mass flow rate reduces for a given pressure drop across the end. So we wanted to maintain the mass flow rate and improve the mixing. So we find there are three test cases. This is done with ant-colony optimization, and this will be done Newton-Raphson method. Here it clearly says that it takes trapped in a local optimum, and the hybrid method is able to reach to a better optimum and as well as in a lower number of function calls. You can see the initial one without baffles, and the final optimization, the pink one, we are able to reduce the length of the mixing length by about 30% for the same composition deviation. To conclude, the mixing ability of the micro mixture increased with Knudsen number. At a given Knudsen number, the mixing capability has been enhanced, increasing the magnitude of the velocity shift between the species. This can be done by use of parameters like differential wall temperature, or internal statistics. The enhancement effect is more pronounced in slip flow than in transition flow region. The active mixture should be preferred in slip flow regime, while static mixture should be preferred in transition flow region. For the test case demonstrated, the mixing ability has improved with use of optimized baffles, which gets reflected in as a reduction in mixing length by 30%. Thank you.
Thank you, Mr. Shashi Kumar, for this nice presentation.
Thank you, sir. I'm sorry for the bad background noise which added up in the video.
It's okay. I mean, we are able to hear it. I mean, we can understand that. This is that normal problem for this online webinar and all. So I would like to open up this session for questions from the audience. Any question? Any questions from the audience? Okay, as I think there is no questions, so I have one thing that you are studying this mixing characteristics within the microchannel.
Yes, sir.
Have you checked for this other external perturbation that can be used in the system, like other field, like magnetic field or electric field, to enhance this mixing. So can it be implemented in this optimization hybrid system?
No, the optimization solver is an independent solver, sir, and the CFD solver is independent one. We have coupled it externally so that whenever function call is required, when object function is required, it calls a CFD solver and it so whenever you want. So the implementation of magnetization or this all these additional features should be in the CFD solver than in the optimization solver.
Okay, and these parameters can be called from the CFD into your solver.
Yes,
right?
yes, it can be. Okay. It can be called.
Okay. Okay. Thank you for this nice presentation. By this, I think we should conclude this session for this microfluidics. At this point, I would like to thank all the organizers of FMFP 2020, and I'd like to thank all the participants and audience for present in this session. And also, I would like to thank the volunteers. They are working tirelessly to make this conference successful. So thank you all. By this, I would like to conclude the session. Any words from these organizers or volunteers?
We thank you, Professor Pata, for chairing this session. Now we will have a lunch session from 12:30 to 1:30. Then we will have a keynote lecture session in hall 1. We will have a key lecture of Professor Yosuke, and in the hall 2 we will have a keynote lecture of Professor Ebi Wang. So, and the presentation part will begin again from 2 p.m. Okay, thank you, Professor Partha.
Yeah. Also, I would like to tell all the audience that there will be all these lectures will be very exciting. So I would request all the audience and participants to attend the lectures as much as possible. Okay. Thank you.
Sound.
Tu es trop grand pour comprendre des choses aussi petites. tu es trop grand pour comprendre des choses aussi petites.
papillon. Tu es trop grand pour comprendre des choses aussi petites.
you.
Finished. आपने क्वेश्चन आंसर करते हैं, ठीक है। फिर उसके बाद जब तक वो लोग बात करेंगे, आप वीएलसी में जाइएगा, राइट क्लिक करके प्लेलिस्ट में वो वीडियो, जो भी वीडियो नंबर नेक्स्ट है 31, जैसे आपका 71 आएगा, फिर 71 नंबर देख के
क्लिक करना होगा क्या? बोला कि एंड करने से आ जाएगा।
नहीं नहीं, माली सीक्वेंस गड़बड़ हो ना, माली कभी जैसे मेरे
जैसे कि मैं कर रहा था कि सीक्वेंस गड़बड़ हो,
तो माली नेक्स्ट आप नेक्स्ट करें कोई और वीडियो, माली कोई और लगा ना, फिर नेक्स्ट करके मैं ही कर रहा था, प्लेलिस्ट में जा रहा था, वही वीडियो ऐसे करके यहाँ सेलेक्ट करके और यहाँ जाके पॉज करके छोड़ दिया, ठीक है। फिर जैसे मैं क्वेश्चन आंसर करता हूँ, बोले ओके विल,
फिर तो शेयर करना पड़ेगा ना फिर तो।
हाँ, फिर वीडियो से करें इंक्लूड ऑडियो, वो हर बार करना है, वीडियो हर बार शेयर करना है, हर बार इसको स्टॉप शेयरिंग,
जब क्वेश्चन आंसर होगा उस टाइम शेयर ऑफ कर देना है।
हाँ शेयर ऑफ करना, काम से चलता रहेगा। जैसे आप वेलसी खोलिए, बता रहे हैं आप यहाँ पे, इसको यहाँ पे वीडियो नंबर जो भी होगा, जैसे बोलेंगे ओके मूवी के नेक्स्ट करंट प्लेलिस्ट खोल के हाँ चल कौन भाई चाबी तुम्हारे पास?
Vous allez l'écrire à l'instant.
Tu es trop grand pour comprendre des choses aussi petites.
को बोला नहीं था कहाँ कैसे डेस्कटॉप पे ही डेस्कटॉप पे गई ओके
Vous allez laisser à l'instant.
Tu es trop grand pour comprendre des choses aussi petites.
Vous allez écrire un instant.
Tu es trop grand pour comprendre des choses aussi petites.
Vous allez l'écrire à l'instant. you. Tu es trop grand pour comprendre des choses aussi petites. Vous allez l'écrire à l'instant.
you.
Tu es trop grand pour comprendre des choses aussi petites. es trop grand pour comprendre des choses aussi petites.
Drop impacts on a liquid.
Vous allez toucher un enfant.
Yeah, Professor Arul Prakash is also there. So I invite Professor Arul Prakash to chair the session.
Dr. Yosuke Hasegawa to deliver the keynote lecture for this session. Dr. Yosuke Hasegawa received PhD degree from Department of Mechanical Engineering at the University of Tokyo in 2004. After working as a postdoc and a research associate in the same department, he moved to the Technical University of Darmstadt in Germany and spent 2 years as a visiting professor from April 2010 until April 2012. After returning to Japan, he was appointed as an assistant professor in Institute of Industrial Science, the University of Tokyo. In 2013, he became a lecturer and started leading his own lab as a principal investigator. Since 2015, up to present, he has been appointed as an associate professor. So his expertise is prediction and control of turbulence and associated transport phenomena. So he has published more than 30 peer-reviewed papers and 100 conference papers. So now I request Professor Yosuke Hasegawa to deliver the keynote lecture on optimal control of wall turbulence for dissimilar heat and momentum transport. Professor Hasegawa, please.
Thank you very much. Very kind introduction. Can you hear me?
Yes, Professor.
And do you see my pointer as well?
Your presentation is not visible.
Oh, my presentation is not visible yet?
Yes.
I tested last time and it was working. How about this? Do you see my screen now? No.
No, we are seeing you. Yeah, now it's coming.
Okay. Let me share once again. Do you see my screen now?
Yeah. Yes. Yeah, please make it as full screen. Yeah.
Okay. Do you see my screen?
Yes, it's perfect.
And do you see my mouse pointer?
Yes.
All right. Thank you very much. Kind introduction. I was really willing to visit India, this opportunity. Maybe, hopefully, I have another chance soon, next time. Okay, so today I would like to talk about some of our results on the optimal control of wall turbulence for heat transfer and momentum transport. So let me start from our problem setting. So we consider flow over the solid wall, and we have a flow field like this, and we also have a concentration field. And we have a turbulence. If you look at a particular distance from the wall, we have momentum transfer and scalar transfer. In this work, we call it scalar, but mostly we consider heat. So those two are Reynolds shear stress and turbulent heat flux. This will cause a wall friction and wall heat flux. Reynolds proposed a so-called Reynolds analogy, which means that a dimensionless heat flux, which is called the Stanton number, should be close to CF, which is a dimensionless skin friction, because of this similarity of the transport phenomena. And this is afterwards that also proposed by Planto by introducing a mixing length theory. And as you already know, that the mixing length theory predict AD viscosity and AD diffusivity as a product of the typical length scale of AD and the velocity scale, so L times V. So since the same flow field is transport momentum scalar, again, we can expect that this ratio is around 1. So we expect that a strong similarity between momentum transfer and scalar transfer, and which is also used in various applications, engineering and also environmental science. So now if we look at the engineering applications, people develop a lot of different surfaces in order to enhance the heat transfer. So starting flat surface, dimple surface, wavy fin, offset fin, louver fin, etc. So now try to plot the horizontal axis is pressure loss, so CF times Reynolds number, and the vertical axis is J times Reynolds number. J is similar to Stanton number I shown before, but take into account Prandtl number effect. So anyway, according to the Reynolds analogy, those two values are similar, so that this line. And then this black line shows that the result of the flat surface, so laminar flow located here, and with increasing the Reynolds number, flow becomes turbulent, and eventually it converts to Reynolds analogy. So basically, Reynolds analogy is provides a good prediction for the flat wall. And if you plot all the data for different levels I introduced before, all of them go below this Reynolds analogy. So this means that even you can get a higher heat transfer, right? However, pressure loss is more enhanced. So if you look at the ratio between heat transfer and pressure loss, it's always worse than the Reynolds analogy line. So obviously, our purpose is to achieve above this line, whether it is possible or not. We can also introduce an analogy factor, which is a ratio between this Stanton number and the friction coefficient. So according to the Reynolds analogy, as I said, this is 1, and this black broken line and the solid line is a flat surface data. And as I said, all the different surfaces are below this line. So we would like to, again, achieve this region, whether this is possible or not. So background is that, as I said, various techniques for enhancing heat transfer have been developed, but they are mostly commonly suffer from an increase of the pressure loss. So analogy factor is always less than unity. Therefore, fundamental question is it possible to achieve dissimilar heat transfer enhancement, which means that heat transfer enhancement is larger than the pressure loss, that of the pressure loss. And present study tried to answer that question by applying optimal control theory. So let's think about a very simple case. We have a channel flow between the two parallel walls. And we have a flow field driven by pressure gradient, mean pressure gradient. And we also have a heat source term inside the fluid. And so this heat source is equal to the pressure drop, pressure gradient. So both of them drive the flow and the temperature. As for the boundary condition, we assume that non-slip boundary condition on the wall. And similarly, temperature is a non-dimensional. So this is a dimensionless temperature is said to be 0, so which corresponds to the constant temperature on the wall. In this particular case, if we consider a mean momentum transport equation, it looks like that. So pressure gradient is balanced by Reynolds shear stress and the viscous stress. Similarly, energy equation look like heat source equal to turbine heat flux and a molecular heat flux. And here we also assume that the Prandtl number equal to 1. So in this situation, boundary condition and the governing equation become very similar, so that this will be the most difficult case to achieve a dissimilarity between U and theta. And we assume blowing suction from wall blowing suction as a control input. So our problem is that I can do blowing suction anywhere, anytime on the wall in order to achieve a dissimilar control. The question is, what is the spatial time-space distribution of this optimal control input? And such a problem is usually very difficult. So this is the schematic showing that the optimization problem in some fluid system in general. So in our case, now we have a control input, which is a wall blowing suction, and which can be applied anywhere, anytime, and any amount of the amplitude. So it's a very large degree of freedom. And such an input is applied to a fluid system, and as a result, we can get a performance, like a heat transfer, pressure loss, in other applications due to a chemical reaction, mixing, whatever. So and then finding optimal distribution is not so easy from this kind of forward analysis. However, in the optimal control theory, what we do is actually we consider that the sensitivity of our control input to the cost functional. So we consider that how our control input should be modified in order to decrease my cost functional. So in such a case, we have to solve backward in time the joint equations, and then sensitivity feedback to original control variable. And by doing this, you can get the sensitivity, and based on that, you can modify the control input. So this strategy is very powerful, especially when you have a large degree of freedom for control input, like our current case. So what kind of cost function we should minimize this time? So first term is look like phi square. Phi is my space and time distribution of the blowing and suction. So this is something like a control input, and I put the square, so both blowing and suction becomes a cost. And the second term is a pressure loss. So I want to also minimize the pressure loss. And the last term is a heat transfer. I want to maximize this heat transfer. So that's the reason why I put the minus here. So our problem is now we want to find the distribution of the phi so as to minimize this cost functional. So physical meaning is that I want to achieve a maximum heat transfer with minimum pressure loss and also minimum amount of the control. So that's the physical meaning of this problem. How can we do this? So more specifically, first we set some time horizon in which we do optimization. And then we solve forward equation with some prescribed input. Usually we start from zero blowing suction. So this is starting from uncontrolled flow and solving a velocity and temperature field in time. This is a standard DNS. And then we solve the adjoint equation backward in time. And in this process, we get the sensitivity, which location and which time which you apply blowing suction. And once you get such sensitivity, you can update your control input and you iterate such optimization. Afterward, you can get the optimal control input within this time horizon. And of course, this time horizon longer is better because you can take into account more future physics. However, when you solve the adjoint equation, you need to store all the space and time information of the velocity field and temperature. So it's computationally very expensive. So typically what people do is that we slide this time horizon. So once you finish the first time horizon, you slide the next time horizon, and then third time horizon. We repeat like this way. Now the question is that how long the time horizon should be. So depending on the length, we categorize into suboptimal and optimal control. So suboptimal control means that we consider infinite, very small time horizon, so that we don't need to take into account that the long-term behavior and only short-term physics are taken into account. So more specifically, we only take into account the linear process. So in such a case, control input can be obtained analytically, I show here, so that you don't need to solve the adjoint equation because time horizon is very short, so that you can easily predict that what's going to happen in the next time step. Similarly, you can optimize your input analytically. On the other hand, if you take into account finite length of the time horizon, then you can take into account the long-term dynamics, which is basically nonlinear effects. But in this case, you need to solve a joint equation as I shown here. And then this computational cost becomes large. So let's start from the suboptimal control. Like you only take into account the next time step. And it's something like I always try to apply some inputs so that your cost functional becomes minimized in only the next time step. Actually, such a simple strategies work quite well, and I want to show these results. So here, the horizontal axis is the time, and then now I plot that Stanton number, so heat flux, and also the wall friction, how it's changed in time. So this is the uncontrolled value, and according to Reynolds analogy, both of them behave very similar way. Now, when you apply the suboptimal control, you can see that heat transfer is much more enhanced than the wall friction. So obviously, we can achieve a dissimilar heat transfer enhancement. And specifically, we get 3 times more heat transfer, and the pressure loss is only doubled. So let's see that how the control input look like. So this is the instantaneous snapshot of the control input and the flow field obtained by suboptimal control. And you see that the bottom wall and top wall, and I only plot that the control input on the bottom wall. And the red region is a blowing, and the blue region is a suction. And as you can see that the red and the blue region comes the alternating pattern, and interestingly, input is almost uniform in the z direction, and then only has some distribution in x, and it is propagating to the downstream. If you look at it from the cross sections, the side view, you can see that the blowing and suction also comes alternatively, and it is one large wave within the domain. And you can also see that even though that the governing equation u and t is very similar, you see that the response of the velocity and temperature field is quite different. You see that here is a fast fluid region, but there is no such high-speed region for the temperature, and the low temperature is more penetrate into the fluid. So although a suboptimal control achieves a dissimilar heat transfer, there is one problem that if you extend your computational domain, this wave of the control input also becomes larger, longer and longer. So we always have one pair of the blowing and suction in the domain. So this means that our control input depends on the domain size. So this is obviously not real optimal. So we switch to optimal control with a finite time horizon. As I said, that this time time horizon is set to be t plus, which is a wall unit, equal 100, which is a typical value that people use for optimal control. So in this case, we can take into account future dynamics up to t plus 100 later. And then here I show that the control input top and bottom wall, and the red region is blowing, and the blue region is a suction. So now we can see we have a multiple wave in our domain. And actually this wavelength is almost independent of the domain size. So we consider that this is a real optimal wave. And as you can see, the wave is propagating downstream, and the top and bottom wall blowing happens the same location, and the bottom is also the suction is happening similar location. So obtained mode is a traveling wave with a varicose mode, and this streamwide wavelength is around 300 in wall unit, and phase speed was 5. Again, this in the friction velocity. So now let's compare the performance of the suboptimal control I already explained and this optimal control. So this red line is a result of the optimal control, and as you can see, heat transfer is increased double. So enhancement is actually lower than suboptimal. However, this time we achieved the pressure loss reduction. So we achieved the simultaneous achievement of the heat transfer enhancement and the pressure loss. If we look at the analogy factor, which is the ratio of Stanton number and CF, actually this is far above 1. So in the case of the optimal control, it almost reaches 3. So which is a significant performance is obtained by optimal control. So now we plot our suboptimal and the optimal control result. It looked like this. I didn't introduce all our results for the different Reynolds number, but basically we can achieve this region above the line. If we look at the another map for analogy factor, our result is coming around here. So obviously, such a streamwide traveling wave is quite promising. So now we are interested in what's the mechanism of such a streamwide traveling wave, how they enhance the heat transfer only. And we consider a simple traveling wave like this. And then we also did another parametric survey of this traveling wave, and we already identified that streamwide wavelengths of 170 and phase speed of 5 is optimal for for maximizing analogy factor. So we're focusing on this particular case and want to discuss how the dissimilarity can happen. So we start from Fukagata Iwamoto Kasage identity, which is often called FIK identity. This is a useful equation because that CF can be decomposed into laminar contribution, which is 6 over Reynolds, plus turbulent contribution. So this is a weighted Reynolds shear stress. So usually in the case of the turbulence, CF is larger than the laminar value, and this can be explained by the Reynolds shear stress. And similar way, we can also calculate the Stanton number, laminar contribution plus turbulent contribution. So any difference between Stanton number and the CF comes from the difference of this turbulent contribution, as shown here. In our case, our problem is a little bit more complicated because now we apply a traveling wave like this. So we have some coherent fluctuation to this wave, and also we have an additional fluctuation of the random. So we further decompose into time-space mean plus coherent fluctuation, which is coherent to traveling wave, and less of the random input. And of course, a coherent input looks like a steady fluctuation if we travel with the wave. So now the wave is traveling downstream. So we consider some averaging window in this blue region. And then our window is travel with a wave, traveling wave. And then in such a frame, this coherent component looks steady, and the unsteady part becomes a random component. So we like to analyze our flow field decomposing those two. So turbulent fluctuation can be expressed by sum of the coherent and random contribution. So if we decompose, so this D is a difference between Stanton number CF, and this further decomposes into coherent contribution and the random contribution. And this is actually the plot of the integrand. So coherent contribution is very large, cross to the wall, and then go to 0. And more interestingly, we have a large random contribution away from the wall. And this is somehow surprising because our input is a coherent traveling wave. However, this coherent traveling wave is also affect the random contribution through nonlinear effect. So, and then we have a more contribution from the random component. This is something interesting. And let's see that how the coherent field look like. So this is a conditional, averaging coherent component. So this is now our window is traveling with a wave. And this is a thermal field, and this is a wall normal velocity component. And the psi equals 0 corresponds to the suction region. And this region and this region is a blowing region. And if we look at near the wall, this is a conditional, average. So here is a coherent component. And here this is now our window is traveling with a large and this is a thermal field here. And then this brings a high temperature fluid across the wall. 0, so we have a high temperature region here. And this region and this region is a blowing region. And as I said, we are moving look at our flame near the wall. So this is this kind of coherent fluctuation. So here is a coherent component. And here this is now our window. And we have a large and this is a thermal field. And then this brings a high temperature fluid across the wall. 0, we have a high temperature velocity component. And this region and this region is a blowing region. And as I said, and this is because look at our flame near the wall. This is this kind of coherent fluctuation. So here is a coherent component. And this is now here. And we have a large, but the temperature is not affected by pressure. So that's the mechanism, how U and theta had a different distribution. As a result, we have a difference between C tilde, theta tilde, and U tilde. And then multiply B tilde, we can get a coherent contribution. And this coherent contribution explains that the large peak near the wall. And if you look at here, actually, if you look at here, we have a strong peak, and this will cause this peak. So now next question is how does random contribution look like? So this is an instantaneous movie showing that how the random component contribution distributed. This is an uncontrolled flow, and this is a controlled flow. Now you can see that the lead positive contribution is basically split entire channel. We look at the budget of this random contribution, and we don't go in so much detail, but we found that eventually this production term is the most dominant. So here we show that the budget of this random contribution, and this production term is a dominant source term, and this peak location agree fairly well with the peak of the random contribution. So let me summarize that what is happening, how the dissimilarity happened by traveling wave. So we consider flow over the flat wall, and we apply some streamline traveling wave. And as I said, this generates some coherent velocity field, which is coherent to the traveling wave, and which is something like a span-wise law like this. And then this will generate dissimilarity of the mean flow and the scalar flow, temperature distribution. Afterwards, what happened is this is not the end of the story, but we have a turbulence. And because this B dash dash is always positive, so if you have a difference between the theta and the U, this will further enhance the dissimilarity. And this effect is much larger than the coherent itself. So that's what we found as a mechanism. So finally, let me conclude my talk. So we apply optimal control theory for dissimilar heat transfer enhancement. And as a result, interestingly, we obtain downstream traveling wave with particular wavelengths and phase speed. And further analysis shows that there is a two contribution from the coherent and the random. And interestingly, random contribution is larger than coherent, which suggests that the nonlinear interaction between the applied wave and the flow. Yeah, basically that's all. And the talk I presented here is that from those publications. And also one of my former students, Arjun, will also talk in this conference on the third Friday on the laminar flow. So today I talk about mostly a turbulent flow, but he will also talk about extension to laminar flow. Thank you for your attention.
Yeah, thank you, Professor Hasegawa, for a wonderful presentation and on the optimal control of wall turbulence. Any questions? Okay. Okay, so I'm having some questions, couple of questions. Professor Hasegawa, so
yes.
So when you're applying this suction and blowing, it is the vertices are generated till the current vertices are generated, whether it is within the wall region or it is extended up to outer region. Means what is the Y plus up to what?
I see. Yeah. This is a very small region. As I show here, actually coherent field is only penetrate very close to the wall. So in this case, it is normalized by delta, but this is, for example, 0.9, so which means that around less than 20 in wall unit.
Okay.
So very close to the wall, below the buffer region, we have a strong coherent contribution. And this one is, as I show here, it's a span-wise law. So this 0.9 corresponds to Y plus 15 now.
Okay.
So basically, our traveling wave generate a very thin span-wise law across the wall. However, this will also affect the outside by random components. So random field is definitely affected by this wave.
Okay. Okay. And will not create any thermal instability because of this suction and blowing alternatively.
Could you repeat once again? What kind of instability?
Because the gradients will be changing. For example, there is a section that is a positive enhancement and is followed by some decrease in the temperature. So this will means increase the not only the heat transfer enhancement, at the same time there is an maybe in the case of channel flows, this will not create much problem. But suppose if I'm having some curved surfaces like having some recirculation regions.
Mm-hmm.
So when you're having a recirculation regions and by introduction of this some control that will cause a slight increase in the thermal gradients and which will also create some hotspots.
Mm-hmm.
So that induce the thermal stress. Is it a possibility like this? Any comment on that?
Yeah, actually, so current wave is at a downstream traveling wave, as I said. And in such a case, this will trigger flow instability. So when we apply this kind of control to laminar flow, for example, we can still enhance the turbulence. So we can trigger turbulence because of this control input. So definitely,
Hello. Yes, sir. अच्छा तुम दो क्या नहीं नहीं ठीक लेकिन सर तो आ गए हैं हेलो हेलो प्रोफेसर रॉय
Hello.
हेलो प्रोफेसर रॉय
Yeah. Hello.
Hello, sir. This is Harshit Gaikwad from IIT Guwahati. I'm one of the FMFP organizer team. Good afternoon, sir, and good afternoon, all. I think all are present over here. And today's this session is session 2C, Hall 3, and the topic of the session will be aerodynamics. And we have with us Professor Sukanta Roy from Curtin University as chairperson of this session. So I hand over this session to Professor Roy. So please, sir.
Good afternoon, everyone. Welcome to the session of aerodynamics. Today we will have total 8 presentation, and I can see all the presenters are available in the hall. So I would request the other participants also please post your questions in the chat option, or at the end of the presentation you can raise your hands so that we can take your question. The presentation time will be 10 to 13 or 14 minutes, although it's fixed at 12 minutes, but we will not be very much strict on that. Rather than since it is a recorded presentation, so we'll follow the full recording, and after that we'll take the questions based on the time available. So with that, now I'd like to invite the presenter Viresh Thakure to present his paper on effect of back pressure ratio on the shock train structure in the isolator of scramjet inlet at different Mach numbers. So
okay, I will play the video.
Yeah.
PhD student under Dr. K. Venkat.
in the Department of Mechanical and Aerospace.
Hello, sir.
Yeah, your voice is not coming.
Hello, sir. Is this video audible? Please check.
Yes, video is fine. You can start playing.
Okay, sir.
At IIT Hyderabad, the topic of my presentation today is effect of back pressure ratio on the shock train structures in the isolator of scramjet inlet at different Mach numbers. My presentation are introduction, problem definition and objectives, numerical methodology and solver details, boundary conditions, grid sensitivity and validation, results and discussion, conclusion and references. The quest for high-speed air travel, that is to travel faster than the speed of sound, led to the invention of supersonic and hypersonic vehicles. These vehicles have many applications like space exploration, military applications, commercial applications, and the design and development of air-breathing propulsion system for these supersonic and hypersonic vehicles have many challenges like shock reflection, shock oscillations due to combustion pressure, shock boundary layer interactions, shock-shock interactions. Dual mode of, here is an illustration of dual mode of scramjet engine. We can see in the isolator there are multiple shock waves occurring either due to the shock entering from the inlet or the formation of shock trains owing to the interaction of incoming flow with the combustion pressure exerted by the combustion process. If these shocks, multiple shocks, are not controlled and contained in the isolator, they will lead to the engine unstart. We have considered a two-dimensional rectangular channel as an isolator in which air is flowing from left to right at supersonic speeds under the influence of back pressure ratio specified at the exit of the channel. The back pressure ratio specified at the exit of the channel is higher than the inflow pressure. The objectives are to investigate the effect of Mach number on the shock train structures, to investigate the effect of back pressure ratio on the shock train structures, to investigate the effect of back pressure ratio on the streamwise velocity variation. Numerical methodology and solver details. We have developed a two-dimensional unsteady state density-based solver, which is an explicit solver used for compressible turbulent flows. The governing equations are average Navier-Stokes equations in non-dimensional form. The closure is achieved using two-equation k-omega turbulence model. This finite difference method is used to discretize the governing equation. Nonlinear terms in the governing equations are discretized using the sixth-order compact finite difference schemes. Diffusion terms in the governing equations are discretized using the second order central difference schemes. Numerical instabilities. Numerical computations of shock boundary layer interactions are prone to numerical instabilities arising due to the presence of sharp gradients of flow variables in the vicinity and across the shocks. To mitigate numerical instabilities, we introduce a small amount of artificial viscosity at each time step. Using this method, recently we have published a paper wherein we have used a channel flow without the back pressure. And finally, the time integration is achieved using Rangekutta fourth order schemes. Entire solver is developed in the Fortran 95 language. Coming to the boundary conditions, uniform velocity, pressure, temperature, density are specified at the inlet. Turbulent intensity at the inlet is 5%. Viscosity ratio is 5. No slip boundary conditions are applied for velocity field at the top and bottom wall. Turbulent kinetic energy is set to 0 at the top and bottom wall. Newman boundary conditions are employed to calculate the temperature, density, pressure, and specific dissipation rate at the top and bottom wall. Both the top and bottom walls are insulated, that is adiabatic boundary condition is imposed. All the flow variables except the pressure and density are extrapolated at the exit. The pressure at the exit of the channel is specified using the BPR, that is back pressure ratio, which is defined as the P exit by P in, which is equal to 2 and 4. Density is computed using the equation of state to satisfy the mass conservation at the exit of the channel. Grid sensitivity and validation. Figure A highlights the variation of Mach number at the center line of the channel for coarse, medium and fine grids for these inflow conditions. From the figure, we can see that as the grid size increases from coarse to fine, the solver is able to capture the flow physics, and for the results of fine grid are matching well with the experimental results of Corel as shown in figure B. This corroborates that the results, the current solver is able to capture the flow physics. Furthermore, because of the complex nature of the flow, that is shock train formation in a channel or isolator, a stringent grid independent may not be possible. Hence, we have restricted to the study of grid sensitivity. Here I am presenting the effect of Mach number at BPR equal to 2. Here we specify back pressure ratio and vary the inflow Mach number to see its implications on the shock train structures. Let us first understand how the shock train structures are formed in the channel subjected to back pressure. The pressure originating from the inlet and the pressure originating from the outlet interacts with each other, and the interaction of these two leads to the formation of first shock or leading shock, which then interacts with the turbulent boundary layer at the top and bottom wall. At the interaction point, the boundary layer thickness increases and the propensity to separate of the wall depends on the shock strength. The boundary layer further grows under the influence of adverse pressure gradient created by the back pressure, leading to the flow confinement and eventually the formation of multiple shocks. These multiple shocks are characterized by a series of oscillations as shown in figure A. From the figure A, we can see that formation of shock trains is present for all the Mach numbers, that is 2, 2.5 and 3, and the strength of the successive shocks reduces as we move from Mach 2 to 3, and the number of shock trains, successive shocks, also reduces as we move from the Mach 2 to 3 due to the presence of dominant stream-wise velocity for higher Mach numbers, which assists in negating the effect of back pressure present at the exit of the channel. Figure B shows the variation of Mach contours for different Mach numbers. From the figure B, we can see that there is no substantial change in the Mach contours, but the magnitudes are different. Figure A highlights the variation of mean wall pressure at different Mach numbers for BPR equal to 2. From the figure, we can observe that for Mach 2, the mean wall pressure increases steadily from the inlet to the exit, whereas for Mach 2.5 and 3, the mean wall pressure increases up to near to the exit and it eventually falls to the pressure specified at the back pressure specified at the exit. This indicates that for Mach 2.5 and 3, the streamwise momentum dominates the back pressure compared to Mach 2. Magnitude of density gradient variation for different Mach numbers is shown in figure B. The magnitude of density gradient is computed using this formula, which represents numerical Schlerin image. From the figure B, we can see that there is no substantial change in the contours of density gradient, but the magnitudes are different. Here I present the effect of Mach number at BPR equal to 4. Here we specify the back pressure equal to 4 at the exit of the channel and vary the inflow Mach number to see its implications on the shock train formation. Figure A highlights the variation of central line Mach number at different Mach numbers at BPR equal to 4. From the figure, we can see that at Mach number equal to 2, the shock trains are completely expelled out from the inlet, that is discoursed from the inlet, whereas for Mach 2.5 and 3, we can observe the formation of shock trains in the channel. Furthermore, we can see that there is a substantial change in the magnitude of shock trains for Mach 2.5 owing to the enhancement of boundary layer interaction. Mach contours variation for different Mach numbers is highlighted in figure B. From the figure B, we can observe the formation of shock trains for Mach 2.5 and 3. This study indicates that for Mach 2, BPR equal to 4, the shock trains are completely disgorged from the inlet, leading to the subsonic conditions in the channel, which may lead to the engine unstart because the entire regime is at supersonic conditions. Figure A highlights the variation of mean wall pressure at different Mach numbers for BPR equal to 4. From the figure, we can observe that for Mach 2, the wall pressure suddenly rises up to the value of back pressure specified at the channel exit. This clearly indicates that for Mach 2, the effect of back pressure specified at the exit of the channel felt up to the inlet, whereas for Mach 2.5 and 3, the mean wall pressure increases steadily from the inlet to the exit. The magnitude of density gradient contours for different Mach numbers is shown in figure B. From the figure, it is observed that for Mach 2, the shock trains are completely expelled or disgorged from the inlet, whereas for Mach 2.5 and 3, the shock train formations are observed. Here I present the effect of back pressure on streamwise velocity variation. Here we have plotted the variation of streamwise velocity along the wall normal direction at x is equal to 3L/4 up to the channel center. From the figure A, B and C highlights the variation of streamwise velocity at BPR equal to 2 and 4. From figure A, we can observe that for Mach 2, as the BPR increases from 2 to 4, the boundary layer thickness reduces and there is a substantial change in the velocity magnitudes, that is higher velocity gradients are present at Mach 2 for BPR equal to 4. Similarly, at Mach 2.5, if I increase the back pressure ratio from 2 to 4, we can observe that there is an increase in the boundary layer thickness due to the shock boundary layer interaction. At Mach 3, the effect of PPR is not even felt. That is, there is no substantial change in the streamwise velocity as shown in figure C. Following are the important conclusions from the present study. For Mach 2, as the BPR increases from 2 to 4, the shock train structure is disgorged, that is expelled from the inlet, forming subsonic conditions in the channel. For Mach 2.5, as the back pressure ratio increases from 2 to 4, a fewer number of shocks are observed, but with higher magnitudes as compared to BPR2. Higher boundary layer thickness is observed for Mach 2.5 as the BPR increases from 2 to 4. For Mach 3, the variation of BPR did not manifest in substantial change in the shock train structure as compared to 2 and 2.5. Acknowledgement. We thank organizers of FMFP 2020 for giving us the opportunity to present our work. We thank all the reviewers for their valuable suggestions in improving the quality of paper. These are the references.
So, thank you, presenter Viresh Thekure, for this nice presentation. Now we would like to take few questions from the audiences. So if anybody having any questions, please you can raise your hand or ask your question in the chat option. I cannot see any questions at the moment. Any questions from the audiences, please? Okay, if nobody having a question, I would like to just confirm one thing. During your simulation, so yes, during your simulation, you have considered turbulent intensity with varying Mach numbers, right?
Yes, sir.
So when you change the Mach numbers from 2, 2.5, 3, did you consider changing turbulent intensity also, or it was fixed?
It was fixed, sir, at 5%.
Okay, so do you think that there will be any changes with the Mach number increase for turbulent intensity for the inlet conditions?
Yes, sir. The turbulent intensity will change it. So for a particular range of Mach number, the variation may not be. So if we go beyond a certain Mach number, then obviously the turbulent intensity at the inlet will affect.
Okay, thank you for your answer. Any other questions from the audiences? Okay, if no questions, thank you, presenter, for your presentation, and we would like to move to our next presentation.
Thank you.
Our next presentation will be by Nikhil Bharadwaj, and he will be presenting on parametric analysis using computational fluid dynamics of a formula student race car. So I would request the organizers to play his video.
And this is the hypotenuse. Hello all. So hope everybody is safe and secure. Over here, this will be my r sin theta in these testing times for all of us. I am Nikhil Bharadwaj, part of Team Haya Racing, PS University, Bangalore. I will be presenting our research on behalf of my co-authors Rahul and Professor Rajendra Prasad. Our research paper is titled Parametric Analysis Using Computational Fluid Dynamics for a Formula Student Race Car. Our paper ID is 31. Looking at the agenda for this presentation, we will start off with a brief introduction to the topic of interest and then summarize 2 out of the many research papers that we referred to before starting off our work. We will discuss the objective of the study and then cover the methodologies employed in order to achieve this. We will discuss the important results obtained and then finally conclude our research work. Introduction. What is aerodynamics? It is the study of motion of air. It is the study of forces and the resulting motion of objects through air. It is a subfield of fluid and gas dynamics and hence has many common theories. Here we see the reference coordinate system that is used in our study for the forces and moments on the race car. The force opposing the motion of the car is drag and acts along the x-axis. The vertically upward force is the lift force, which acts along the positive z-axis, or we can consider down force acting vertically downwards, that is along negative z-axis. Side force acts along the y-axis. The moment about the x-axis is the rolling moment. That about the y-axis is the pitching moment, and the moment about the z-axis is the yawing moment. An airfoil is an aerodynamic structure with a curved surface designed to give the most favorable ratio of lift and drag. It is used as the basic form of wings. In the given application for the race car, we use multi-stage wings to obtain the highest downforce and efficiency. It is characterized mainly by the camber line, chord length, and angle of attack. A multi-stage wing is an assembly of multiple airfoils used in stages. The relative angle, that is the angle of the aerofoil with respect to immediate flow direction, is set close to the stall angle for the latter stages of the wing. The overall focus of this study is to analyze the effect of wings on race car stability and performance. Literature survey. Now, I will summarize 2 of the many research papers that were reviewed before starting our work. The first one was titled CFD Analysis of an FSA race car equipped with front and rear wings. Radhakrishnan and team conducted a 3D CFD analysis of an FSA race car. The authors found out that the addition of wings increased the downforce and hence increased the tire grip. But the decision must be made judiciously by ensuring that the drag penalty is not huge. The second paper is titled Use of Computational Fluid Dynamics for the Design of Formula SAE Race Car Aerodynamics. Puneet Dodegowda and team analyzed the performance of wings on FSA race cars. The authors used the K-epsilon model for running the CFD simulations. A mesh-independent study was conducted for a single aerofoil and the results validated with experimental data. They found that CFD predicted the solution with an error of 10%. The authors concluded that mesh quality and refinement is crucial to obtain accurate results. In general, we found that very few papers analyze the performance of wings while keeping the balance and stability of the race car in mind. Very few papers use the concept of center of pressure for this purpose. These 2 points were primarily identified as the gaps in literature. Now we have the necessary information to look at the problem statement for our paper. The objective of this study is to analyze the aerodynamic performance of 4 design iterations of an FSA race car. Our aim is to determine the forces and moments acting on the car and its efficiency parameters. Additionally, we aim to analyze the stability of the car, and these are the 4 designs that are evaluated in the project. Design 1 is that of the car without any aerodynamic devices. Design 2 is that of the car with a 3-stage front wing and a 3-stage rear wing with a guide wing at an angle of attack equal to 0 degrees. Design 3 is similar to Design 2 in all ways, except that the guide wing is at an angle of minus 12 degrees to direct flow into the rear wing. Design 4 uses the same rear wing as Design 3 and uses a 2-stage front wing instead of a 3-staged one. Meshing is an integral process of the simulation setup and greatly impacts the accuracy of the solution. Here are a few mesh parameters that we kept in mind. The targeted skewness was 0.4, the average orthogonal quality was 0.9, and the average cell aspect ratio was 0.95. The flow region represents a virtual wind tunnel through which the air is blown and the behavior simulated using CFD. We considered the effect of ground proximity, the inlet, outlet, and the wall distance to model while choosing the optimum dimensions for our enclosure. The flow region was 21 meters in length, 6 meters in width, and 3 meters in height. Here we see the details of the CFD simulation. The most important parameter is the turbulence model. We have chosen the K-omega shear stress transport turbulence model. We compared the different models available and found that the K-omega SST model has the best accuracy inside and outside the shear boundary layer. Coming to the boundary conditions, we used no slip condition on all the walls. The ground was given the moving wall condition. The pressure at the outlet was set to the atmospheric pressure. Velocity at the inlet was varied from 10 to 30 meters per second. Results and discussions. The first step was to obtain a mesh-independent solution. Mesh independence is said to have been achieved when the variation in the parameters is around 1%. Here we see that we achieved this state with mesh number 4. The results obtained from simulating this mesh was used for comparison with other designs. The same process was followed for all the models in the project. The table shown here has the values of drag, lift, and side force for all designs at a velocity of 10 meters per second. Positive value of lift suggests that the force is directed vertically upwards, and negative value of lift suggests that the force is directed vertically downwards. We notice that design 3 produces the highest negative value of lift, that is the highest value of downforce out of all the designs. Inevitably, the drag force goes hand in hand with lift. Design 3 has the most efficient rear wing and a 3-stage front wing, which explains its superior performance. In this slide, we can see the coefficient of drag plotted against inlet velocity. By referring to the legend, we immediately notice that design 1 has the lowest value of CD. This is observed as the absence of aerodynamic devices means that there is less obstruction of incoming air. This is also why it produces the least amount of downforce. Design 3 has the highest coefficient of drag and is followed by Design 2 and Design 4. The biggest takeaway from this plot is the variation of CD with velocity. We see that CD reduces slightly with velocity. This is due to flow separation. At lower velocities, the air does not have enough energy to combat the adverse pressure gradients in contours such as the suction side of airfoils. But at slightly higher velocities, this phenomenon reduces, hence increasing the efficiency of the aerodynamic devices. That is why we notice a reduction of CD at higher velocities. Downforce to drag ratio, also known as efficiency, is a good indicator of the aerodynamic performance of a body. A higher value indicates that a lesser drag penalty has to be incurred to produce the same value of downforce. We notice that designs 2 and 3 have the highest value of downforce to drag ratio. The increase in efficiency with velocity can again be explained by the concept of flow separation. Now we look at the moments that act about the center of gravity of the race car. We observe that design 1 has a positive moment, which is a nose-up moment. This would reduce front tire grip and make the car incredibly hard to control. Design 4 seems to be the most balanced model, given that designs 2 and 3 have incredibly high negative values of pitching moments. The net pitching moment about the center of wheelbase is calculated by considering both the aerodynamic forces and the weight of the car. This parameter signifies the load distribution between the front and the rear tires. We observe that designs 2 and 3 are very sensitive to velocity, which is highly undesirable. Design 4 has a relatively flat curve and very low magnitude of moments at all velocities. This makes it the most balanced design in the study. Center of pressure is an imaginary point at which all the forces seem to be acting. It follows that the moment about the center of pressure must be zero. We observe from the two pictures that the position of center of pressure is very sensitive to velocity in both the designs. This presents an unbalanced case. Design 3 seems to be a development from both the previous designs, but the best scenario is presented by Design 4. The COP has relatively very little movement with velocity. Also, the COP is located close to the center of wheelbase, making this the most desirable setup. Conclusions. From the force analysis, it seems that Design 3 is the most desirable given that it produces the highest downforce and is the most aerodynamically efficient design in the study. But when the moment analysis was conducted and the center of pressures analyzed, Design 4 turned out to be the most stable one. Designs 1, 2, and 3 presented a virtually undrivable scenario which would not result in any lap time improvement. To conclude, it might be an exciting prospect to use huge wings to produce the highest downforce and hence increase the grip. But considering the stability and balance of the race car simultaneously would result in the best performance on track. These are our references without which the report could not have been completed. Thank you.
Thank you, speaker, for your presentation. Nikhil Bharadwaj, you are here, right?
Hello. Hi.
Yes. Actually, I have few questions. Before that, I would like to take some questions from the audiences.
Hello.
Sure.
Sir, can you hear me?
Yes, please.
In one of the slide, you have negative downforce to drag ratio. What does that mean?
Yeah. So we have considered lift to be positive when the force is acting vertically upwards, right? Okay. So now if the force is acting vertically downwards, we consider that as downforce. So if there is negative downforce ratio, so then we have that it's actually producing positive lift. That means the net resultant force along the y-axis on the car is upwards. So downforce to drag ratio is negative, means that we're actually producing lift on the car.
Okay, thank you. And you are referring to the center of pressure. I mean, is it the standard terminology used? Because otherwise that is called as neutral point, right?
Yeah, so in our race car aerodynamics, we use this, to roughly, get an idea of what exactly is happening, where all our forces are acting. So we've used the same convention here.
Okay, thanks.
Yeah, thank you.
Hello. I want to ask one question, sir.
Yes, please.
Yeah, actually, as it is shown in the one of the slide, it is audible, sir?
Yes. Yeah, please go ahead.
And the dimension of the car have been taken on what basis? I mean, what is the basis of taking the dimension as 1.3, 1.5 meter width and height? What is the basis of selecting these parameters?
Sure. Okay. Thanks for that question. So the background of this whole project is that we are building a race car for a Formula student competition. Okay. Right? So the rules for building this car is based on a rule book which is provided by the organizing committee. So Formula Student is an organization which organizes student competitions all over the world. Formula Bharat is the Indian leg of that particular event, right? It happens in Coimbatore every year, and we actively have been participating in that for the past 10 years. So Formula Student Committee issues a rule book where we, which we use as our, our guiding light, if you will, to design our particular race car. And there are a lot of stringent rules there based on which we have arrived at this particular configuration.
I think I want to suggest one thing.
Yeah.
That if these parameters will be represented in the form of the non-dimensional parameter, means these height, width, etc. will be non-dimensionalized with any parameter, then this study will be broadly means that these results can be
generalized
used for the any other research also. Means if the result is presented in the form of the non-dimensional parameter.
Okay. Yeah, that makes sense.
The hydraulic diameter or any other thing, it can be non-dimensionalized.
Okay.
Okay.
Sure.
Okay.
Yeah.
Good. We have another question from
hello.
Vaibhav.
Yeah.
Please.
Yes, sir. Thank you. Hello, Nikhil. My question is that you have taken velocity approximately 20 meter per second. Am I correct?
Yeah. So we conducted the study for a range of velocities, 10 meters,
range
10,
of
20,
velocity, and 10. Yeah. So, in my knowledge, in the high racing cars, the velocity should be greater than maybe 70, 80 meter per second, because the drag force. Yeah.
Sorry, please complete your question.
So why you have taken 20 meter per second? Because if we increase the velocity, so the inlet condition will also change basis on the drag forces and the start at inlet condition of your.
Correct. Yeah. Thank you for your question. So now the way we arrived at the velocity ranges for our particular simulation is taking the track configuration in the competition, right? So the specific track where the competition is held in Coimbatore, that is the Kari Motor Speedway, we cannot reach high velocities at all. So the average velocity that the car would reach there is around 16.66 to 20 meters per second. So that is why we have taken a range of velocities from 10 to 30 meters per second. Okay, so as this is a student level competition, and if I can also give you a brief about our engine configuration. So we use the KTM 390cc engine, right? So yeah, so this is a reduced version of a real race car, because this is a student version. So we do not reach very high velocities, and our particular study has been focused for that particular application.
Okay, thank you.
Yeah.
Okay, thank you. I think we'll stop taking questions here. Just a quick questions to you. What material you considered during simulation for the race car design?
Yeah, so we have actually glass fiber for the nose cone, and we have aluminum panels for all our body works, and the chassis pipes are we use chromoly. So roughly, more than the material, we've considered the surface roughness. So we have used GFRP itself for our nose cones and all our aerodynamic devices which are there. And then, for the bodyworks, which again are GFRP, only for the chassis pipes we have considered, chromoly.
Okay. Okay. I think. Thank you. A very nice presentation, Nikhil. So.
Thank you. Thanks everyone for patiently listening to it. Thank you.
So we'll now invite for our next presentation, and our next presentation will be by Jade Palova, and he will be presenting on numerical investigation of heating and cooling effect to the cavity and pylon exposed to supersonic flow. So I would request organizers to play his video.
Excuse me, sir.
Yes.
Video ID 43 number is also present here. The presenter name is Vaibhav Sharma.
Yes, sir.
Okay, so we may take after also, no problem. We can continue. Yeah.
Okay, sir. So should I play Vaibhav Sharma's presentation?
Yeah, please present
Yes.
please start the Jait Palwa and then we'll take the Boiver Sharma. It's okay.
Okay, sir. Okay. Okay.
My, my name is Zed Palova, and today I'll be presenting the research we did named Numerical Investigation of Heating and Cooling Effect to the Cavity in Pylon Exposed to Supersonic Flow. We are a group of three members, including myself, Zed Palova, our guide, Mr. Vishnu A.S., and another team member, Miss Gaganasi. So today's talks include the part of introduction to our study, what we are actually trying to do and what we achieved. Then, since our study is completely computational based analysis, we needed to have a numerical model, then the validation case, so that we can prove that our the software we are using is giving valid results. Then there are case studies we performed, then the conclusion and what ultimately we got from the studies, and there are references from which we did our literature survey. The study consists of effect of heat transfer on the pylon walls, different pylon walls and the cavity, and how does it changes the flow dynamics of inside the cavity. What kind of phenomenon occurs and how much mass is emanating inside the cavity, and how the shear layer thickness and shear layer reattaching point is varying when the heat is removed or when the heat is being added. The ultimate goal of this research was to study the effect of energy addition or removal, and this addition and removal of the energy has been done in different cases when the pylon was divided into three walls and the cavity was kept as a singular wall. For the literature survey, the basics of heat transfer phenomenon were reviewed. The cavity-based flame holders concept studied by Mr. Emma Gruber was studied, and how the simulation approach should be and what should be the numerical modeling and the acoustic features of the flow inside the cavities were done. Flow cavities has always been oscillating in nature, and it results in strong coupling between the flow dynamics and acoustics. In the current study, the mechanism of shear layer generation and vortices cascading has been discussed, and the graph between the pressure ratio and the dimensionless length of the cavities has been provided. Due to the shear layer lifting, the thickness of the shear layer remains the same or remains constant, but the reattachment point of the wall of the cavity extends further downstream and causes the mass to spillage. As Gates studied in his experiment, that due to elevated temperature, the momentum of the fluid increases and the primary size of the primary vortex increases, and this also leads to the growth of the size of derived vortex. The numerical modeling is as follows. The picture shown on the top right corner of the slide is the cross-sectional view of our geometry, and it is being zoomed so as we can differentiate between the adiabatic walls, the pylon walls, and the cavity. The wall 1 is over here, the wall 2, which is the horizontal wall, is being here, and the wall 3 is the adjacent wall of the pylon. The angle of the pylon is kept at 29 degrees and the angle of the cavity is kept as 22 degrees, whereas the length and depth of the cavity are kept at 3.812 inches and 2.5 inches respectively. The simulation is done using the CFD++ software, and the numerical validation is done using the Hart and Lex Van Leer contact scheme, and the turbulent model used was SST K omega. The Mach number is maintained at 2 throughout. At the exit, the back pressure is maintained at 101.325 kilopascal with the method of characteristic base pressure imposition. Next comes the validation case. Since our study is completely based on the results from computation analysis, we needed to validate our results with already published paper. So we choose Mr. M.R. Gruber's Fundamental Studies of Cavity-Based Flame Holder Concept for Supersonic Combustion. And the graph provided over here implies the variation of pressure ratio with respect to the non-dimensionalized cavity length. The red dot present in the graph are from the Gruber's experiment, and the black curve are from our experiment. And it is evident from the graph that the validation of our software is pretty much similar to that the Gruber's experiment. First case, the first case being considered is the adiabatic pylon and cavity under supersonic flow. As the flow passes over the pylon, a compression wave is generated and a ramp recompression vortex is formed, as it is evident from the pressure contour. The boundary layer formed after the recompression wave advances to wall 1 and wall 2 of the pylon, and it develops into a shear layer. The second case considered was the cooling of pylon walls in the cavity, and it was divided into 5 subcases. The first three being the cooling of pylon wall 1, 2, and 3, and the fourth one being the cooling of full pylon, and the fifth one being the cooling of full cavity. The turbulence in the flow field is stabilized due to the energy removal in the cooling case. From the Schlieren images, cooling of wall 1 can reduce the turbulence and delays the boundary layer separation. There is an increase in the vortex size, and this happens due to the low density flow beneath the shear layer. And due to the high density mass entrainment, there is a lift of the shear layer to the free stream flow. The wall 2 cooling reduces the boundary layer thickness, which indeed reduces the shear layer thickness. As for the wall 3 cooling, the denser fluid beneath the shear layer reduces the momentum and the vortex tries to become steady. The cooling of full pylon and cavity have the same effect as shown in the pressure contour of the images. It is evident from the pressure contour that there is ramming pressure field on upstream to the pylon, and it is getting stronger as heat flux moves especially downstream due to the disturbance of the free stream flow, and this happens due to the shear layer and shock waves at that condition except cavity cooling. The third case considered was the heating of pylon and cavity, and again it was divided into 5 subcases, the first three being the heating of pylon wall 1, 2, and 3, the fourth one being the heating of full pylon, and fifth one being the heating of full cavity. In the case of heating of wall 1, the attached boundary layer on the pylon wall 1 thickens due to the elevated temperature, causing a wide and low density shear layer. The reduced mass entrainment due to thick and low density shear layer reduces the size of primary vortex, which is evident from the Schlieren images of the pylon wall 1. As for the heating of wall 2, it causes the shear layer to scatter, and thus this causes a partial spillage of the mass, which reduces the size of the primary vortex, and the secondary vortex will be deformed. It is evident from the Schlieren images that the size of the primary vortex is again being reduced, and the deformation of secondary vortices in this region are also being deformed. In the case of heating of wall 3, pylon wall 3, there are multiple vortices being formed in the cavity region. This shows that the heating of wall 3 has a major impact on the flow field, and the multiple vortices indicates better mixing of the fluid. As for the case of full heating of full pylon, there is the significant change in steady state pressure as observed from the Schlieren images, and the significant vortex deformation is not observed when heat flux is being applied to the whole pylon. This is because the heating of wall 1 and its impact on the shear layer, which is being heated as well due to the heating of the whole full pylon. Vortex deformation is comparable with the previous cases. The cavity heating causes the thickening of shear layer towards the aft wall due to the low density and higher temperature of the gases. As it's evident from the Schlieren images, there's the partial spillage of the fluid happening due to the shear layer thickening at the outfall of the cavity, and this leads to the reduction in mass entrainment inside the cavity. To conclude the presentation on our study, we gathered 7 points, which basically tells the advantages of having the heated and the cooled pylon and cavity under supersonic flow. The graph present over here shows the variation of temperature inside the cavity and the whole region of consideration. The black curve shows when the pylon wall 1 was kept as adiabatic, that is, there was no addition or removal of heat. The red curve shows there was addition of heat to the pylon wall 1, and the cooling of pylon wall 1 is being showed by the blue curve. It is evident from the graph that when the flow reaches the cavity region, and in case of cooling of wall 1, the pressure is quite more as compared to the adiabatic wall condition and the addition of heat to the wall 1. The graph on the left shows the wall 3 heating and cooling case when compared to the adiabatic case. The shear layer lifts across the free stream flow, and this happens because there is a transfer of positive heat flux to the wall 3, and it causes a light density vortex beneath the shear layer, and this results in the extension of reattachment point downstream the flow, and it causes the mass spillage. Wall 3 cooling causes addition of dense fluid to the shear layer, and a slight shift in the fluid reattachment point is observed. The graph on the right shows the heating and cooling case of the cavity as compared to the adiabatic case. Towards the outfall, the thickening of the shear layer happens because the cavity is being fully heated. Also, the pressure peak seems to be decreasing at high heat flux at outfall reattachment point. These are the papers we referred for our literature survey. Thank you.
Respected sirs and ma'am.
Okay. Thank you, Jayed, for your nice presentation. Now I open the floor for questions. We may take 2 to 3 questions. You can raise your hands or unmute your mic and ask the question. Okay, we have a question from Vivek Kumar. Please ask your question.
Hello, sir. Can you hear me?
Yes, please go ahead.
Sir, if you see which configuration is very effective if you speak in terms of total pressure drop?
Hi, Vivek. Thanks for your question. And as I concluded in my in our research, actually, we found that the heating of wall 3, which is exactly adjacent to the cavity, it is quite advantageous because it basically increases the efficiency of fuel mixing. So we concluded that the heating of the wall 3 is a very good combination as compared to the other heating and cooling cases.
Thank you. Any more question? Zaid, I have a question that how you selected the wall thicknesses, those wall 1, wall 2, wall 3, how actually selected?
So actually there is, if you are asking about the length, then I can say like we referred the OMG Arya Dutt's paper, which was published in the International Journal of Fluid Mechanics, heat transfer energy, and according to that paper we selected the dimensions of the pylon, and for the cavity we selected the Gruber's paper, and we selected the dimensions of gravity from the Gruber's paper.
Okay. Any more questions? If we don't have any more question, then we'll move to our next presentation. Our next presentation will be by Vaibhav Sharma on flow investigation of U-turn in an internal serpentine passage by using stereo PIV. So now from CFD we are moving to experimental aerodynamics. Dear organizers, please play the video of
everyone.
My name is Vaibhav Sharma, and today I am here to present my paper titled Flow Investigation of U-Turn in an Internal Serpentine Passage using Stereo PIV. So before moving ahead, let's take a look on the contents which we are going to discuss in coming minutes. First, we will begin with the introduction of gas turbine. Then we will discuss requirement of blade cooling. Then we will discuss the serpentine passages used in the current paper. Then we will discuss SPIV, which is stereo particle image velocimetry. Then literature review, followed by experimental condition used in the current paper. Then we will discuss some results, and the last we will discuss future scope. Gas turbines are used to generate power, for which gas turbine blades are exposed to high temperature combustion gases, as you can see in the left of the figure. Therefore, these blades has exposed to high thermal and mechanical stresses. To increase the power output of the gas turbine, the turbine inlet temperature needs to be increased. So currently around 1400 to 1600 degrees centigrade inlet temperature is used, which is very high from the material limit, which is around 1040 degrees centigrade. So it is clear that these blades needs to be cooled, and the study shows that if we cool the blades only by 30 degrees centigrade, the life of the blade will increase to twice. As you can see from these two figures, first figures in the left of the slide is the gas turbine blades assembly, and in the second figure, after the failure, you can see if only one blade will fail, so we have to change the whole rim and the whole assembly. So it is quite essential to cool these blades. To cool the turbine blade, the blade has been provided by some serpentine passage. The air bleed from the compressor passes through the serpentine passages and cool the blade. There are lots of techniques to cool the blade, from which some conventional techniques are rib turbulated cooling, impingement cooling, pin-fin cooling, and film cooling. You can see in the figure that in the leading edge of the blade, film cooling are there, and in the middle chord of the blade, the internal convective cooling are there, which is provided by ribs turbulated cooling generally, and in the trailing edge, the pin-fin cooling is there. In the present study, the flow investigation of the serpentine passage has been done using stereo PIV. As we all know, PIV is particle image velocimetry, in which the flow field has been illuminated by laser light and captured by a single camera, and this seeding particle has been tracked and the global velocity field can be measured. In the stereo PIV, this work has been done by using of two cameras instead of one camera. These two cameras gives a third component of velocity also, which is in the z direction or in the third direction. The only difference between PIV and stereo PIV is the cameras are two and they are aligned with an angle to the light sheet. The skim flux condition should be satisfied as the lens plane and the object plane and the image plane for each camera has to intersect in a common line. As we know that the internal cooling channels are generally serpentine, and in the serpentine passage the fluid generally experiences a U-turn. Because of the U-turn, the aerothermal characteristic of the fluid changes. So if the design of the U-turn is not up to the mark, so it can lead to a cooling problem. Therefore, the efficiency of the serpentine passage depends on the proper design of U-turn. So for the effective design of the U-turn, the heat transfer as well as the flow behavior needs to be known. In the present study, the flow characteristic of a sharp U-bend inside a two-pass rectangular duct has been inspected or investigated. This investigated has been done in 3 planes and at a Reynolds number of 6200, which is based on the hydraulic diameter of the rectangular duct. Lots of studies has been done numerically and experimentally to study the behavior of air during passing through U-bend. These are the experimental conditions. We have taken a rectangular duct having aspect ratio of 3.26, which resembles the gas turbine blade mid-chord region, and three planes are taken for investigation. The SPIV parameters are region of interest, we have taken 170 into 30 mm square. Image size 1932 into 341 pixels. Calibration factor 88 micrometer per pixel. Frame rate 15 Hz. Number of sample 1000 and pulse separation is 80 microsecond. This is the model diagram of stereo PIV and U-turn used in the present study. As you can see in the right of the figure, that this is the U-turn and these are the three planes which we have taken for study. These planes are categorized by plane 1, 2 and 3 and divided by two location 1 and location 2. As you can see, there is two cameras are there and these cameras captures the region of interest which is changing as the plane changes. The laser in the left side of the figure, you can see this is a laser head and the laser has been illuminating the required region of interest and which is captured by the two cameras. This is the actual photograph of U-turn with stereo PIV. As you can see that this is the two cameras which sees the region in the U-turn. This is the U-turn and here three planes are there, plane 1, plane 2 and plane 3. After performing the experiments, we have processed the images and we found the results. First, we will discuss the mean velocity time average streamlines. As you can see in the left, there is a U by WR at plane 1, plane 2 and plane 3. Then it is V by WR and then it is W by WR. U is the velocity at X direction, V is the mean velocity in Y direction and W is the mean velocity in Z direction, where WR is the centerline velocity. We have normalized all the mean velocity with the centerline velocity. So first we will discuss this result which is U by WR. U by WR basically increases up to X by DH1 and then suddenly decreases to a minimum value. From X by DH1 3, mean velocity remains constant to a minimum value. This is a turning region. This sudden decrement in X direction velocity is due to the sudden expansion and bending of the flow. This abrupt change in U by WR is also caused by obstruction caused by the internal corner of U-turn. At the beginning of the second pass of the duct, the velocity again starts increasing and reaches to a maximum value up to end of the second pass. U by WR at vertical plane 2 and 3 shows approximately the same result. It increases up to X by DH4 and we can say that the effect of sudden expansion in the bending flow diminishes in these planes. By analyzing V by WR, we can see that this flow has been guided by upward direction and topmost direction by the wall of the duct. By analyzing W by WR, we can say that one shows the higher value which is equal to the centerline velocity and -1 shows the same higher value goes in the secondary direction. So the time average streamline at plane 1 shows an entirely different flow structure than the plane 2 and plane 3. It can be concluded that in plane 2 and 3 not so much changes are there, but in plane 1 there is a significant changes in the flow characteristic. So this flow characteristic has been analyzed critically. As you can see in the figure, there are lots of nodes and bifurcation line is there. So as we analyze it, so we can say that as the flow enters the U-turn at X by DH1, 4 positive nodes created at different points 1, 2 and 3 and 4. At the entrance of the second pass, which is this, the duct where the flow again take a sharp turn at X by DH3, the streamline splits into two opposite directions. So a bow-like bifurcation line is created. This bifurcation line is due to the negative pressure gradient caused due to the outer wall of the second pass of the duct. Fluctuation statistics are also present here to have an insight of the moment transfer and mixing. The results are shown in terms of URMS, VRMS and WRMS normalized by WR. Fluctuation velocities in X and Y direction are superior towards the exit of the U-turn than that of the entry of the U-turn. The higher value of URMS and VRMS is due to the higher velocity gradient, which results in higher turbulence production at the exit of the U-turn. WRMS is higher at the entry side of the U-turn. This means a higher velocity gradient in this direction. This high velocity gradient is due to the continuous retardation of flow in the jet direction by the end wall of the duct. However, this trend of high velocity gradient at the entry of U-turn in the jet direction is reducing as plane move near to the end wall. So the conclusion is that when the flow enters U-turn, an abrupt change in flow pattern is seen at plane 1, but there is no significant change has been seen in plane 2 and plane 3. The velocity suddenly reduces to almost zero and a number of positive nodes formation take place for plane 1. At x by ds3, where the flow takes the second turn to enter into the second pass of the duct, a bow-like bifurcation line creates. This critical flow structure and abrupt change in velocities is disappeared at vertical plane 2 and 3. This shows that effect of sudden expansion and bending is diminished at this plane. Fluctuation velocities shows higher velocity gradient towards the exit of the U-turn, which means higher turbulence production at the exit of the U-turn. This leads to a high heat transfer at the exit, which is also noted by other researchers. Finally, it can be seen that proper flow investigation of the U-turn is necessary for design of the serpentine passage with minimum pressure loss and high heat transfer. So the future scope is more flow parameters can be studied as vortices, normal stasis, turbulent kinetic energy budget terms, and SPIV measurement of U-turn in horizontal plane can be investigated. Thank you. These are the reference and questions.
Thank you for your presentation. Now I would like to open the floor for questions. Okay. Anybody got any questions? Yeah, we have a raised hand. So, Vivek, you want to ask something?
Yes, sir.
Yeah, please go ahead.
Sir, in your presentation, you mentioned that number of samples is.
Yes. Number of.
Are they sufficient to get a converged solution?
Yeah, the previous studies which has been done by our seniors in our lab and in the other researchers are shown that 500 images are more than enough, so that the error percentage was less than 5%. So due to this, we have taken 500 samples.
Okay, I have another question. What kind of seed particles have you used for your experiment?
We have taken the olive oil and we have taken olive oil particles, which is the droplet of, the olive oil particle has been atomized by a compressor, Luskin nozzle compressor.
Okay, because if you use olive oil, they will create some viscous effect over the surface. Will they affect the solution?
Actually, the velocity and the dimensions of the U-turn is so large that these particles is not being, the movement of these particles not affect so much in terms of viscous force, as you asked.
Okay, thank you.
Thank you.
Is there any more questions? If there is no question, just I would like to ask Vaibhav one question.
Yes, sir. Sure.
In stereo PIV, actually one of the important aspects that we need to consider are the PIV uncertainties. So did you make any calculation on the uncertainties for PIV experiments?
So yes, we have calculated, but it's not been presented in the paper.
Oh, okay. Yes. Okay. And your sampling rate was during PIV?
Sampling rate, pulse separation rate you are asking, or number of samples?
Number of samples.
So number of sample, basically we have taken 1000 by 500 image pair.
Okay. Okay. So that's all. Thank you for your presentation.
Thank you,
Now,
sir.
now we would like to move to our next presentation. Our next presenter will be Lavala Srinivasa Rao. He will be presenting his work on experimental aerodynamics. So his paper name is Experimental Investigation on Shock Cell Characteristics of Sonic or Supersonic Jets. I would request organizers to play his presentation video.
Respected sirs and ma'ams, good morning, one and all. Title of the paper is Experimental Investigation on Shock Shell Characteristics of Sonic and Supersonic Jet. Myself, Lavala Srinivasa Rao, and I am currently doing PhD in Department of Space Engineering Rocketry at BIT Misra. My professors are Dr. Sudeep Das and Dr. Partha Mandal. This is outline of the presentation, which consists of basic introduction, objective, experimental setup and methods, results and discussion, and I have drawn some conclusions here. Application of jet goes to nozzle exit of rockets, missiles, aircrafts and space shuttles, etc. When these jets are exposed to different ambient conditions, they react in a different ways and subsequently added to the acoustics. Usually, the application indicated in the previous slide as a hot category of jets. However, we neglect the entropy related part of the overall contribution. We could try the characteristic with cold flow jets as well. Jet flows are defined as flow where the fluid without any restriction enter into atmospheric conditions. The various operating conditions of the jet could influence the jet structure. Classification of jet and its structures based on Mach number could be divided into three types: subsonic, sonic and supersonic. In the present study, sonic and supersonic jets were considered. The figure shown in this slide is a typical supersonic jet flow structure indicating the various features of the jet. Subsonic jet contain potential core, mixing zone, transition zone and then fully developed region. Acoustic power mostly comes from the mixing zone, which depend on the potential core length. Unlike subsonic case, supersonic jets have vulnerability in a large alternations in the potential core length with change in operating conditions. The sonic and supersonic jet structures largely depend on the jet pressure ratios. Pressure ratio defined as the jet exit pressure to the ambient pressure. In the current setup is obtained from different nozzle pressure ratio. If the pressure ratio less than 1, it is called over-expanded cases. If it is equal to 1, it is called correctly expanded case, and if the pressure ratio greater than 1, it is called under-expanded jet. The difference between all the cases have either expansion or oblique and weak normal shock at the jet exit. The shock turbulence, interactions and feedback mechanism are the prime reason of acoustic generated for such cases. The different structure of shock waves and its fluctuations changes in pressure, density and velocity fluctuations and could lead to additional acoustic noise. Hence, characterizing isolated jet with basic features like shear layer, barrel shock, triple point, Mach disk, reflector shock, slip line, shear diameter and shock shell length are important to investigate. Objective of the current work is to capture the variation of flow feature and characterization of the shock shell feature for different operating conditions. The experiments were conducted in Aerodynamic Laboratory, BIT Misra. The settling chamber of facility has a diameter of 10 inch and length of 40 inch. The settling chamber is allowed to get filled with compressed dry air at the range of 90 to 100 psi through a controlled pressure regulating valve and a desired nozzle pressure ratio. Constant monitoring of total pressure from pressure transducer and feedback control DAC assisted in maintaining in a desired nozzle pressure ratio through a runs as indicated in the graph shown here. All the runs were controlled using a feedback mechanism to maintain a runtime of roughly 50 seconds. Standard Schlieren and shadow graph method was adopted where the density gradient in the flow were captured for the jet flows. The test details for the present work is listed in the table. For Schonick nozzle, the range of NPR was between 3 to 5. According, the pressure ratio were varied between 1.58 to 2.64. The supersonic nozzle 1.5 and 2.0 were tested in the range of 3 to 5 and corresponding ranges pressure ratios were 0.38 to 1.36. In the present investigation, operated nozzle pressure ratio with design Mach number 1, 1.5 and 2 and achieved exit pressure ratio 0.38 to 2.7 were tested and reported here. These are Schlieren flow images of axisymmetric jets having Mach number 1, 1.5 and 2. Here Mach 1 has slightly and highly under expansion process depicted here. The Mach disk size and location, barrel shock and shape rapidly varying triple points are observed in these pictures. Mach 1.5 has over expansion and slightly under expansion cases. All basic features and process are captured which includes the jet flow development. And the third one, which is Mach number 2, has over expansion case which also has all basic captured features clearly observed in this picture. The shock shell length is defined distance from the jet exit to the interaction point of the shear layer and reflected shock. Here, first and second shock length normalized with jet exit diameter measured for all cases are present in this figure. The trend of increase in the length with increase in the exit pressure ratio could be very well be observed from the figure. The trend of second shell distance rise for lower pressure ratios are quite evident and it always remains approximately twice the first shock shell distance. The rate of increase in a length are observed for high Mach numbers compared to low Mach numbers. Mach disk location is defined as the distance between jet exit and the Mach disk which forms at the interaction of barrel shock, reflector shock and slip plane formation, which is also the triple point of the jet. Here, Mach disk location normalized with jet exit diameter measured for all Mach number cases with similar NPRs are shown in a figure. Mach disk location is observed to be closer to the jet exit for higher Mach numbers, lower pressure ratios compared to the lower Mach numbers. Higher pressure ratios for similar NPR conditions. Mach disk cone angle is defined as the angle between horizontal jet axis to the line connecting center of a jet exit and the triple point. The measured values from the Schlieren are plotted with changing pressure ratios and Mach number in this figure. The diameter of the axis-symmetric Mach disk normalized with the jet exit diameter is also plotted in this same figure. The diameter and angle decreases monotonically for Mach 2.0 due to over expansion process, but Mach 1 and 1.5 the trend has been changed with increasing pressure ratio due to under expansion process. Pitot pressures were measured using a house-built pitot tube which was installed in a linear traverse unit covering the axial streamwise distance of 20 times of jet exit diameter. The effect of Mach number with constant NPR 5 shown in a figure which indicates the difference in pattern of compression and expansion and changes the location of feature along the center line and steep pressure decay was also observed for the higher Mach number. A trend of future with increasing Mach number can be observed in this figure. Similarly, effect of NPR, typical Mach number 2 and over expansion process is captured in this figure. The rise and drop indicates shock cell behavior which alter to the change in a nozzle pressure ratio. Mach 2 indicates over expansion region which is having margin difference of NPR 4 and NPR 5. NPR 3 indicates a clear difference in the pressure decay region having change in a locational mixing pattern. The figure shows the effect of NPR for Mach number 1 and the under expansion process. The rise and drop indicates the shock cell behavior which alter to the change in nozzle pressure ratio. Mach 1 which is under expansion region, there is a huge difference observed NPR 3 and NPR 5. An increase in the NPR 5 shows a drop in a total pressure undulations. This could be critical and important characteristics difference between under-expanded and over-expanded processes. The pitot pressures were also measured in the transverse direction to get the radial information of the jets by traversing the pitot tube unit in the cross direction at specific 8 number of planes. Figure shows the variation of pitot tube total pressure in the transverse direction at Mach 1 by running pitot tube transverse direction of the flow at several axial locations. The distribution immediately to the nozzle of the exit fairly flat but gradually decreases the region further downstream at x by d 10, where the flat section is shown have almost vanished and value at the center decreases in the region more downstream because of expansion fan and highly under-expanded case. In figure shows Mach 1.5, the x by d8, the flat section appeared and the section of center value also section appeared in downstream because of expansion fan and slightly under-expanded case. This figure shows transverse direction of a pitot tube distribution. Initially it's disturbed, then flat section appeared till x by d6, then after x by d10 and 12 totally disappeared because of weaker expansion fan and over-expanded jet. Based on present investigation, we have drawn conclusions here. Flow field were studied and captured by using different experimental techniques. Shock cell features were measured by using qualitative measurements. Shock cell and Mach disk features depend on the exit pressure ratio, Mach number and nozzle pressure ratio. All the observed influence has been captured with limited range of operating conditions. These observed variation could lead to further better understanding of acoustic of such free-jets. Thank you to all for patience to listening my presentation.
Thank you for your nice presentation. Now I would like to take some questions.
Yes, sir.
Is there any question from the audiences? Please, you can ask. Okay, so it seems we don't have any question. So we move to our next presentation on flow stability over blunt-headed cylinder at an angle of incidence through dynamic mode decomposition by Ashish Pawar. I request organizer to please.
My presentation is flow stability over blunt-headed cylinder at an angle of incidence through dynamic mode decomposition.
Yes, please play the video. Yeah.
Blood bodies have tremendous engineering importance as they are used in various technological applications such as in chimneys, solar heating systems, buildings, dry cooling towers, electronic cooling, probes and sensors, etc. Blood body induced flow, unsteadiness and mixing can enhance heat and mass transfer. After comprehensive literature survey on blood bodies, it has been found that there are very few experimental studies on blood bodies in low Reynolds number region. Blood bodies like blunt-headed cylinder needs extensive study. Areas like steady to unsteady flow transition, 3D transition of flow over blood bodies, flow stability analysis need more attention. Instabilities developed in flow due to increase in Reynolds number or change in configuration of body may grow over a period of time and can affect both fluid and thermal characteristics. With DMD as a tool, stability analysis for forced convective flow past a blunt-headed cylinder at incidence has been carried out. Simulations are performed for air at Reynolds number 100 and angle of incidence in the range 0 to 80 degrees. It is assumed that flow is unsteady, incompressible, two-dimensional and laminar. Also, fluid properties like density and viscosity are constant. Computational domain has been shown in figure. Reynolds number is defined on the basis of projected width of the cylinder, that is capital D, which is related to the cylinder diameter D from the expression as shown in the figure. Dimensionless equation for continuity and momentum are shown in this expression, whereas dimensionless variable for velocity, xy coordinates and time and pressure are shown in these expressions. Upper and lower walls have free slip condition, whereas surface of blunt-headed cylinder is under no slip condition. Domain length is such that far-field boundary effects are eliminated and stability of simulation is ensured. The outflow boundary condition is applied at the outlet. Before using dynamic mode decomposition, one must know what it is and what advantages it provides in blunt-headed cylinder analysis. Dynamic mode decomposition is a method to decompose time-resolved data into modes with each mode having characteristic frequency and growth or decay rate. It is equation-free, data-driven method. With DMD as a tool, one can find out and visualize different modes in the flow, which is not possible in traditional methods like Fourier transform. For different angles of blunt-headed cylinder configuration, DMD compares energies of dominant modes in the flow. One can say instability is grown up, damped, or flow is in dynamically steady state by looking at the respector. Any dynamic system like Navier-Stokes equation can be represented as this expression. Measurements of system such as velocity, vorticity in terms of coordinates can be represented as this expression. DMD approximate best possible linear dynamical system as dx by dt is equal to ax, whose solution can be given by this expression, where phi k and omega k are the eigenvectors and eigenvalues of the matrix A, and the coefficient bk are the coordinates of the x0 in eigenvector basis. Measurement matrices from x1 to xm are put into the matrices x and x dash having delta t time lag between each entry of the matrices. Now we need matrix A which assigns x to future state x dash. We have multiplied both sides by x plus, that is pseudo inverse, which is least square regression algorithm to obtain A. We put this value of A back into this expression and obtain value of x. In present blunt-headed cylinder analysis, DMD is performed over instantaneous vorticity build data spanning at least 6 periods of oscillations. Sampling time and snapshot numbers are selected as 0.1 second and 100 respectively on the basis of sampling time and snapshot number independent study. Qualitative nature of first mode is consistent with time average plot of vorticity, whereas evaluation of vortex state has been shown by mode 2. L2 norm gives measure for comparison of energies of different modes. Each mode is denoted by a vertical bar corresponding to its frequency and amplitude. At the origin, the eigenvalue characterizing the mean flow shows the highest frequency amplitude among all nodes. Except mode 1, other modes have complex conjugate eigenvalues. For angle of incidence 40 degrees, there is highest amplitude for mean flow frequency in all angles that have studied here. In order to analyze damped or undamped oscillations of instabilities in the flow, read spectra of real versus imaginary eigenvalues have been studied. Reed's values, which lie on the circle with unit radius, gives the zero growth rate modes. However, the Reed's values lying inside and outside the unit circle represent the damped and undamped modes respectively. It can be seen that for alpha is equal to 40 degree and 80 degrees, nearly all Reed's value lie on a unit radius circle, which represent dynamically steady state of the flow. For other angles, some eigenvalues lie inside the circle, implying dying out of fluctuations. DMD spectrum is the plot between real and imaginary logarithmic eigenvalues. It can be observed that spectrum is symmetric about neta I equal to 0. It can be seen that the cluster of eigenvalues approximately gives an inverted parabolic arc, which represent stable eigenvalues. Some pairs of modes are lying in the positive quadrant of the DMD spectrum. These modes denote very high frequency structures and are in a very low energy state. Hence, these modes are insignificant in the view of flow instability. To summarize the present analysis, following points can be noted. First mode of the angle of incidence 40 degree shows the highest energy among the modes for angles considered here. From Reed spectra, it can be seen that most of the eigenmodes for angles considered in the present study lie on the circle showing the dynamically steady state condition of flow. Dominant mode reveals flow physics such as vortex state. There are no unstable eigenvalues in the DMT spectrum as the temporal evolution of flow in the vortex shaded cycle is in an equilibrium state. Thank you.
Welcome you all. Myself Vivek Kumar from Madras Institute of Technology.
Thank you for your presentation. Now I'd like to take some questions from the audiences. Any questions? If there is no questions, just I want to ask one question regarding your simulation or coding problem. So, did you conducted any validation study with any other study? Hello? Hello? Yeah. So, my question is, during your modeling, did you conduct any validation case? Hello, Ashish Pawar? Hello? I think we lost his connections or there is some audio issues. So without further delay, we will move to our next presentation by Vivek Kumar on experimental investigation on co-flowing chevron and truncated chevron nodules. So I'd request the organizers to play the video.
Welcome you all. Myself Vivek Kumar from Madras Institute of Technology. Our research work entitled as experimental investigation on co-flowing chevron and truncated chevron nozzle. Let's see a brief introduction about it. Jet mixing plays an inevitable role to design efficient combustors in both gas turbine engines as well as rocket combustors. Nowadays, most of the commercial jet engines uses chevron nozzles. The main reason behind this is the chevron nozzles suppresses the noise level at a considerable amount by enhancing the jet mixing across the downstream. The present study tries to identify the difference between chevron and truncated chevron nozzle in jet mixing process. To fabricate the truncated chevron nozzle, we made a truncation at a 2 mm distance from the nozzle exit plane. The present experiments were performed at various Mach number levels. Their Mach numbers varied from 0.4 to 1.0 in steps of 0.2. Let's see a brief introduction about our experimental setup. Our experimental setup consists of various components such as high pressure tank and compressors, settling chamber, pitot tube, and a traverse mechanism. Finally, a data acquisition system to measure the pressure signals. The reciprocating compressors used to charge the high pressure tank. Once it's fully charged, we used a high opening valve to generate a required amount of pressure at the nozzle exit. The pitot pressure was measured at the nozzle exit plane across the downstream as well as lateral direction to plot radial as well as axial Mach number decay profile. If you see at the right side of our slide, we can see the fabricated model as well as the CAD model of our chevron as well as the truncated chevron nozzles. Here we presented few results from our experimental data. If you see at the top left corner at Mach 0.4, both chevron and truncated chevron nozzles potential core length are almost same. The potential core length is nothing but the distance at which the a nozzle exit Mach number is preserved. If you look at the top right figure, at exit Mach number 1, the chevron nozzle have a major reduction compared to the truncated chevron nozzles in the potential core length. For various nozzle exit Mach number, we plotted our results in the bottom left figure. Here we can see the linear variation of potential core length for both chevron as well as truncated chevron, but there is a interesting results here. The variation is very steep for chevron nozzles compared to truncated chevron nozzles. Similarly, we plotted our results for in lateral direction also. Here also we observed significant variation between the chevron as well as the truncated chevron nozzles. In lateral direction also, the chevron nozzles reduces the potential core length higher than the truncated chevron nozzles. From that, we conclude in such a way that increasing the jet Mach number increases the mixing in both nozzles, but influence is more in chevron nozzles than the truncated chevron nozzles. It is evident that chevron nozzle generates stronger downstream eddies than the truncated case. So the apex of the chevron are the primary source for the strong downstream vortices. Flattening of chevron apex in a small amount leads to a significant effect in jet mixing process. Thank you. Thank you.
Thank you for the presentation. So now I'd like to invite some questions from the audiences. Any questions? Okay, we don't have any questions. Vivek Kumar, I would like to add a question that how many conditions actually you tested for both the nozzles?
So there are 4 Mach numbers from 0.4 to 1.0.
Any particular? Yeah, please go ahead.
It's a totally 8 tests, sir, actually. I mean, 8 conditions, actually.
Any particular reason for being in the Mach number around 1 only, not going very high?
Yes, sir. Actually, we can go for under-expanded case also, but it's very difficult to maintain such a pressure in our laboratory. So that's why we restricted ourselves up to 1.0. We can go beyond that. It will be under-expanded case.
Okay.
So we fabricated our material using nylon rod. So it sometimes it may get ruptured if you go for higher pressures.
Okay. Any more questions from the audiences? Okay, if we don't have any question, thank you, Vivek Kumar, for your presentation. Now we would move to our move to our next presentation by Ravindra A. Shishat. Ravindra will be presenting his presentation on computational investigations of aerodynamic properties for flow past NACA 0012 3D wing in ground proximity. I would request organizers to play the video.
Hello everyone, myself Ravindra Shirsat, a PhD scholar from the Department of Applied Mechanics, IIT Madras. I'm working with Dr. Rinku Mukherjee. Today I'll be presenting a part of my work, that is computational investigations of aerodynamic properties for flow past NACA 0012 3D wing in a ground proximity. The outline of my presentation is I'll briefly introduce the problem, followed by the methodology that I have used. Then I'll explain the domain and boundary conditions that we have used for the present work. With the choice of turbulence model, we have tested different turbulence models and remaining studies done by using the best model that is suitable for the present work. Then I'll introduce the results and discussion where we'll see the pressure and velocity contours for two different angles, that is at 0 degrees and 21 degrees angle of attack. Though we have done it for all the range of angle of attack, but briefly I'll explain the two extreme cases when the wing is in ground effect and out of ground effect. When the wing stalls, the flow separation can be clearly seen through the streamline patterns that I'll be showing. Then we'll see the CL alpha and CD alpha graphs, and finally I'll conclude with the important observations. The effect of ground proximity on the aerodynamic performance of an airfoil or wing is studied for quite a long time. The main reason for which people study this effect is the wing in ground effect increases the lift, reduces the drag, thereby improving the overall aerodynamic efficiency of the wing. However, a detailed systematic study is required in order to know how exactly the wing plan form, aspect ratio, angle of attack, sweep angle, etc., as well as the unsteady movements of the wing such as pitching, plunging and flapping will affect this phenomenon. We have used a simple rectangular wing with aspect ratio of 6.4 in the ground proximity, simulated by solving the 3D Reynolds average Navier-Stokes equations as shown here. The closure is achieved by using SST K omega turbulence model after testing the different models such as Spallard-Almaraz, K omega, SST and K epsilon models. We have used the commercial CFD package ANSYS Fluent. The version is 18.1. For all the cases that we have studied, we have changed the angle of attack from 0 degrees to 21 degrees in steps of 3, that is 0, 3, 6, 9 and so on, to cover both the pre-stall as well as post-stall flow regimes. The ground clearance, that is h by c, is varied from 0.2 to 1 in steps of 0.2. That is, first we kept the wing at 0.2, then 0.4, 0.6, 0.8 and so on. This is the domain that I have used, a rectangular domain. Inlet we have given the velocity corresponding to the Reynolds number of 0.1 million. The wing is kept at the origin. Domain extends 6 times the chord ahead of the wing and 12 times the chord behind the wing. Vertical dimension of the domain is 6 times the chord, and along the span we have taken double the wing half wingspan. The main important thing for using the SST K omega model is the y plus should not exceed 1, that is unity. So first we have plotted the contours for y plus over the wing as well as over the ground. Here the ground is given moving wall with the same velocity as that of the inlet velocity. And we see that throughout the ground as well as on the wing, y plus is not exceeding 1. That is the basic requirement for the SST K omega model. The choice of turbulence model is critical in these studies. Therefore, we have tested the given wing for given conditions using the Spallard-Almaraz model, K epsilon model, K omega SST and the experiments. And we found out that in this conditions for the given mesh and domain, K omega SST best predicts and matches with the experimental results. And therefore we decided to go ahead with the K omega SST model for our remaining analysis. Now we'll see the pressure contours for 0 degrees angle of attack in the two cases when the wing is out of ground effect and when the wing is in a closest position to the ground, that is h by c is equal to 0.2. All the contours I have plotted for the plane which is at the root of the wing. As can be seen from the first figure, when the wing is at 0 degrees angle of attack and out of ground effect, it is well known fact that since it's a symmetrical wing and at a 0 degrees angle of attack, the pressure distribution on the upper and lower surface of the wing will be exactly symmetrical, thereby not producing any lift, as can be clearly seen here. But when the same wing is moved close to the ground, that is 20% of the chord from the ground, we can see that though the wing is still at 0 degrees angle of attack and the pressure distribution on the upper and lower surface of the wing is now not identical. The symmetry is disturbed. And the main reason for this is already as suggested by found out by many other literatures also, the convergent and divergent passage that is created underneath the wing. As can be seen here, because of the convergent divergent passage created between the wing and the ground, that is also called as Venturi effect, the velocity in this place is higher and therefore the pressure in this lower surface of the wing is less as compared to the pressure on the upper surface. Thereby, in this case, though the wing is symmetric, kept at 0 degrees angle of attack, but still it produces a small negative lift. This can be more from the velocity contours. When the wing is out of ground, similar to the pressure distribution, the velocity distribution is also symmetric on the top and bottom surface of the wing. Whereas when this wing is moved close to the ground, now we can see the velocity underneath the wing is slightly higher than the velocity on the upper surface of the wing. And that is the main reason this wing is experiencing a negative lift. Now we'll see the pressure contours and velocity contours for the next angle of attack, that is 21 degrees. When the wing is out of ground, we can see a large negative pressure region is created on the upper surface of the wing, whereas pressure on the lower surface of the wing is still high. Similar thing is observed when the wing is close to the ground, but this effect is not as much as observed in the earlier case. The velocity contours also we can see when the wing is out of ground, a large separation region is created on the upper surface of the wing. In both the cases, out of ground as well as in the ground effect also. Now to see the effect of flow separation, where exactly the flow is separating, we have plotted the streamlines for the same plane, that is at the root of the wing, for different angles of attack, that is 6, 9, 12, 15 and 18 degrees. As can be seen, for an angle of attack of 6 degrees, the flow is almost seen attached on both upper as well as lower surfaces of the wing. Further increase in angle of attack to 9 degrees, a small separation region is observed on the upper surface near the trailing edge of the wing. But when the angle is further increased, at an angle of attack of 12 degrees, we can see a relatively larger separation region on the upper surface of the wing. This is what is called as flow separation, and we call it as in aerodynamic terms, we call it as the wing stall. With further increase in angle of attack of 15 degrees, the size of the separation region further increases, and at an angle of 18 degrees, the entire upper surface can be seen as a separated zone, and a flow reversal is observed on the entire upper surface of the wing. Our intention was to see how much lift increment we are getting because of the ground effect. Therefore, in the CL alpha graph for different ground clearances, we see that when the wing is in the closest position to the ground, that is at h by c equal to 0.2, When the angle of attack is 0 degrees, the lift coefficient produced is around minus 0.15. As already discussed, this is because of the Venturi effect created between the wing and the ground. With the increase in angle of attack, the lift coefficient increases, and at an angle of attack of 3 degrees, we can see this lift coefficient crosses this lift curve crosses the other lift curves, indicating that beyond 3 degrees, the lift produced by this wing in the closest proximity of the ground is much higher than the lift produced when the wing is out of ground. Similar observations can be done for the other cases also, that is when h by c is equal to 0.4 or 0.6 or 0.8. We see beyond 3 degrees, for all the ground clearances, the lift produced by the wing is higher than when the wing is out of ground. This is what we call as the increment in the lift because of the ground proximity. Though the stalling angle for almost all the cases remains same at around 9 to 10 degrees. Now, the next thing to observe was to the drag coefficient. Therefore, we plotted CD versus alpha curve for all these different ground clearances of 0.2, 0.4, 0.6, 0.8 and 1. The important thing we observed here is the wing experiences lowest drag when it is out of ground effect. Whereas when the wing is in the proximity of the ground, the drag experienced is slightly higher than that it would have experienced out of the ground effect. This is mainly because of the increment in the lift and increment in the lift dependent drag that is experienced the wing. So finally, I will conclude that we studied a effect of ground proximity on the aerodynamic performance of a rectangular wing at a Reynolds number of 0.1 million and the aspect ratio of wing is 6.4. We tried different turbulence models and concluded that for the present study, the K omega SST model gives the best performance. Considerable increment in the lift is observed with decreasing the ground clearance. However, this effect is favorable only for the medium ranges of the angles of attack, as we observed, that is around 3 degrees. Also, considerable reduction in the maximum lift coefficient is observed, while the stalling angle less or more remains. These are the references that I have used. Thank you.
Thank you, presenter, for your presentation. Now I'd like to invite some questions from the audiences. Yes, Vivek Kumar, you may ask your question.
Sir, actually, I have one suggestion. Actually,
yeah, please.
Instead of plotting a separate CL and CD curve, if we plot CL by CD versus alpha, we may get some very interesting results, I think. So we can find which one is the most efficient configuration. I think.
We have done it, but not included in this presentation.
Okay, thank you. Okay, then which one give more efficient? Which one is the most efficient configuration?
Closest to the ground, that is according to our observations, what we saw here, that 0.2C is the best.
At which angle of attack? I mean,
the angle of attack comes in between 3 to 9 degrees, somewhere around 6-7 degrees. That is the range of the angle of attack where you see the best performance in the presence of the ground.
Okay, thank you.
Any more questions? Just I would like to add a question. Did you consider the negative angle of attack also?
No, sir. For this case, we are not considered because the airfoil that we are using is 0012, and the lowest ground clearance we considered is 20%. If we make a negative, it may hit the ground. We can try a small negative angle, but as of now, we are not considered it.
Okay.
But we'll try, sir.
Yeah, definitely you can because
yes.
Sometimes these wings may need to, if you talk about the aerodynamics, may need to land or whatever may be your application, may need to use a negative angle of attack.
Okay, sir.
So in those cases, and then there is another important observation. If you look after the stall,
Yes, sir.
For ground clearance, I think 0.8.
Yes.
If you look into this, this lift coefficient behave very changed as compared to the other. No, when you are increasing the ground clearances slow by slow, then 0.2 was the top lift coefficient, and then
Yes, sir.
it is 0.8 ground
Okay.
clearance, which is giving you the second most lift coefficient, I think. And
Okay,
after that
we'll,
again 0.6, 0.4, like that. So
okay, we
maybe
will check it.
yeah, after stall behavior is different. Maybe some physics is there.
Yes.
You can analyze that one.
Okay, sir. Thank you, sir.
Thank you. Any other question from audiences? So if there are no more questions, thank you all the presenters for your nice presentations. We have seen both the experimental aerodynamics as well as computational aerodynamics through different applications. And I hope we have taken also some feedback from the audiences, which will be more fruitful in our future research. With that note, I conclude this session on aerodynamics, and I pass the floor to the organizers again.
Thank you, Professor Sukanta Roy. We will take a break for 10-12 minutes and we will join at 4:15 once again. Thank you, Professor. And thank you, everyone.
আরে জাস্ট ইয়ে চালানো দরকার নেই, টাইম নেই তো পিএসআইটা একবার চালিয়ে দাও, আমাদের মানে ইয়ের ভিডিওটা চালানো দরকার নেই। পিএসআইটা একবার চালিয়ে দাও।
Yeah, good afternoon. मैं गाड़ी Okay, I think everybody join.
Hello, this is Harshad Gaikwad. Good evening, everyone. This is organizer from FMFP conference team. Professor Datta.
Yeah. Good afternoon to all.
Good afternoon, sir. Good afternoon, sir. This is Harshad Gaikwad from IIT Guwahati. So, this is session 3C, Hall 3, and the topic of this session is measurement technique in FM and FSI. So, I now today's session chair is Professor Sushanta Datta from IIT Roorkee. So, I hand over the charges to Professor Datta.
Okay, thank you. Good afternoon to all. So let's start the session. So first paper by Ms. Mitanjali. Her topic is development of PIV system with angular scanning based dual color illumination. See there, Mitanjali. Yeah. Okay. Okay, you can play now. That.
Yes, sir. Just.
Okay.
Hello everyone, my name is Mitanjali and I am from IIT Kanpur. I will discuss my work on PIV system with angular scanning based dual color illumination. So starting with the introduction of conventional PIV, which is an experimental technique to get the velocity information over the whole domain. So this is the schematic for the system where the flow is seeded with tracer particles and a small region is illuminated by a 2D laser sheet. At the same time, flow is recorded by a CCD camera on two different frames at two different time instants. The recorded information is the displacement of the particles between two illuminations, which can be extracted by cross-correlating these two recorded images and using the information of the time delay between illumination, the velocity data over the region can be estimated. So this is the conventional planar PIV. In the scanning based PIV system, the pulsed lasers are replaced with the continuous beam laser and the illumination of the test section can be achieved via scanning of the beams. Two types of scanning is possible, angular scan and the linear scan. Motivation to work in the scanning based PIV system is the high cost and bulky setup for the conventional system, due to which it has limitations in the field deployment such as underwater measurement, and also it is not suitable for large scale field applications. Moreover, it has non-uniform intensity field because the beam is converted into a stretched 2D sheet. So, while considering all the shortcomings in the conventional PIV, here the objective is to develop a cost-effective dual-color scanning-based PIV system. The major components are two different color continuous wave lasers, rotating plane mirror, and a color CCD camera to capture the flow information during illumination. A synchronizer is required to synchronize the time of scan, the rotation of mirror, and the incidence of the beams while recording the information. So the major key processes are the illumination, flow recording, and the image analysis. In the illumination, the beams are directed on a rotating plane mirror which sweeps the beams over the test section and creates a pseudo light sheet. This pseudo light sheet illuminates the section in a progressive manner. The flow is recorded by synchronizing the exposure time with the scanning time of the beam, and a single image is captured which consists of both illuminations. So the captured image is then analyzed by statistical technique, and the displacement of the particles between illuminations can be evaluated. In the illumination, the plane mirror plays an important role and follows the law of reflection, that is angle of incidence will equal to the angle of reflection. And using this characteristic, we can see that as the mirror rotates, the reflected ray also gets rotated accordingly. So using this information, we end up with a very important relation which shows that the angular velocity for the reflected beam will be twice the angular velocity for the plane mirror. In the flow recording, a single color image is captured which consists of both the illuminations and can be separated into different frames based on the single color particles. These color images then converted into grayscale images so that the cross correlation can be used to extract the information of the displacement from these two images. So here comes the difference. The time interval between two illuminations is always constant for the conventional PIV, while for the scanning case, it varies over the test section, and the variation depends on the relative difference of the scanning velocity of the beams and the velocity of the particles. So, while knowing the information of the displacement and the distribution of the time delay over the test section, can get the velocity vector field. And to get this information, we have considered one particle within an interrogation window. These images shows the angular position of the beam. This is the at the start of scanning, while these shows the beams when the same particle is illuminated by red and green beams. The respective displacement of the particles while illumination are shown here. Is the initial position of the particle, while R and G are the same particles when illuminated by red and green. These are the final expressions which can be used to get the velocity information as well as the time delay over the test section. We can clearly see that the delta T is not constant and it varies spatially over the region of interest. To evaluate the system, we have tested it on two different flows. One is uniform and the second is the non-uniform. In the uniform case, parallel flow with three different values of acceleration is considered. Three different values of accelerations are considered to see the effect of extent of unsteadiness within the flow. Similarly, for the non-uniform case, rigid body vortex flow is considered with three different values of angular acceleration. Some basic parameters which are common to both cases are given here. So, as it is a theoretical analysis and a virtual image is formed. A virtual image is formed which consists of approximately 5,000 particles, and the size of the particles is approximately 2 pixels. Particles are considered to be randomly distributed, and image is formed using all the selected parameters given in the previous slides. Similarly, the formed image is then separated into different frames based on the color and converted to grayscale images, so that the cross correlation can be applied, and the displacement information from these images can be extracted. For the uniform parallel flow, initial velocity is kept as 1.0 second, and here the results are here. The contour shows the delta t distribution, and a clear pattern is shown, which is due to the combination of angular scanning and the difference of the velocities of the scanning beam and the particles. Observing the vector fields, we can see for the steady case and the low accelerating case, the velocity information is almost similar, while for the high accelerating case, we can observe that the vectors in the lower region are smaller than the vectors in the upper region. It is due to the progressive illumination. The progressive illumination will can be explained in the next slide. Uh, Here we can see the black particle shows the initial position of the particles, while red and green are the same particles when illuminated by red and green beams. So we can see that the particles in the lower region are illuminated just as the scanning starts, while particles in the upper region are illuminated after a time delay that the beam takes to reach this location. In this meantime, the particles shift from their position, and if the flow is unsteady, velocity also gets changed. So here's an example. The For the parallel flow with 40 meter per second square as the acceleration, the initial velocity is 1.06 meter per second, but the maximum measured velocity is 1.3 meter per second and is majorly in the upper region. It is the effect of progressive illumination. So the results from the scanning PIV are compared to the conventional PIV, which are also calculated using the theoretical analysis. We can see that for the steady and low accelerating case, the error is almost similar to the conventional PIV and in the acceptable range, while for the high accelerating case, it takes a spike and reach to 18% and mostly restricted in the upper region. This is again due to the progressive illumination and can be reduced by increasing the scanning rate for the beam. For the rigid body vortex case, initial angular velocity is 13.2 radian per and the results are shown here. These are the delta t contours, and a different pattern can be observed here, which is again the combination of the angular scanning and the difference of the particle velocity and the scanning velocity. Vector fields can be observed, and we can see in the right region the value is higher for the delta t. It is because the particles are moving away from the scanning beams. Again, the velocity fields are almost similar for the steady and the low accelerating case, while for the high accelerating case, vectors in the lower region are smaller than the vectors in the upper region. It is due to the progressive illumination. One more thing to observe here is the range of variation in the delta t. It is 7.5% for the steady case, while for low accelerating case it is 9.3%, and for the high accelerating case it is 14.2%. So the results are again compared with the conventional PIV, and we found that for the steady and low accelerating case, the results are very well comparable with the conventional PIV, while for the high accelerating case, error goes to very high, 40%, and it is due to the progressive elimination and can be reduced by increasing the scanning rate for the beam. Here is the summary for the system. A mathematical model is presented for the scanning illumination based PIV system. Delta T found to be varies over the region of interest, and the variation is more significant for the complex flow field. Results are very well comparable with the conventional PIV for low accelerating case, while for the high accelerating case, error increases in the direction of scanning, and which is due to the progressive illumination. The system will be more effective by making the rate of scanning equivalent to the characteristic rate of change of the velocity for the flow. Thank you.
Okay, so 1 2 questions can be from the audience. Any question? Please raise your hand. Then Anybody want to ask any question to Mitanjali? Okay, then I have one question to Mitanjali. Are you hearing?
Yes, sir. Yes, sir.
Yeah. So see, this is a scanning type of thing. So for unsteady flow field, how will measure the velocity field if the flow is unsteady?
Sir, we have tested the cases for unsteady. So there is some limit.
Mirror is rotating particular frequency or giving the rotation to the mirror, no?
Yes, sir.
So you are basically continuously scanning. So the flow field is changing continuously, suppose, isn't it?
Yeah.
Unsteady
Yes.
flow field. So how it will be capturing that field?
Sir, for the unsteady cases, there is only one requirement of a high scanning rate. If we can maintain the high scanning rate according to the flow field, then it will be easily captured.
Okay. But okay, so then suppose I don't know the first-hand information about the flow field. Okay,
Yes,
we don't have unsteady information. What is the unsteadiness in the flow? So how will capture that? Because we don't have information about this, no, beforehand.
Yes, sir. Yes, sir. So we have tested the cases and we found that obviously that it depends on the prior information, but if we don't have the prior information, then we can run I think more tests so that we can have some prior information, and accordingly we will shift towards that.
Is there anything in the can be done in the programming part to take care of the errors? This type of error, whatever. Is there any scope for modifying that? Because this is, I think, that is the main part for this scanning thing. That programming, that how to basically take care of the errors in the.
Yes, sir. One more thing, sir, we can do the CFD simulation for that flow if we don't know the information, and we can get some initial or prior information. According to that, we can arrange. And all the things in this model have done by the coding only, so we can set accordingly.
Okay. Is there any role of the wavelength? Because the two light you are using, one is your red, another I think green, isn't it? So the wavelength, is there any function of that? No.
No,
wavelength
sir.
Because two wavelengths will be different, no?
Yes, sir. Yes, sir. There are two different wavelengths are used for the lasers, but their effects is not considered.
Okay. Okay. Good work. Thank you.
Oh, thank you so much, sir. Thanks, everyone.
Okay. So next paper is by Tanmay Bose. He will presenting the paper Detection of Bubble Embedded in Water Using Double Frequency Method. Tanmay Bose is there? Okay. So, okay. So we can now play the video. Make it full screen. Audio is not coming.
Literature review, methodology, and Dr. Biplav Kumar Devnath in NIT Meghalaya, and presenter is Dr. Tanmay Bose. So these are the contents of the presentation.
Who is there?
So,
just wait. This is I think.
First is introduction.
Hello, sir.
Make it full screen.
Hello,
it's not full screen till.
Yes, sir. I have made it full screen, but the presentation video is in the same format. So,
okay. So
I'm showing the.
On it.
Yes, sir. Yes, sir.
Okay. So it is because it is coming very small in my screen.
Sir, sorry for that, but we have received the same video as an input.
Okay. Okay. Then continue. Fine.
Thank you, sir.
And literature review, methodology.
Okay. Sir.
Tanmay is there. Okay, fine. No issue. Continue.
Business definition, results and discussion, conclusion, then references. So first is the introduction. So the bubble is a glass globule of one substance to other, usually gas or liquid, and the bubbles are visible because its refractive index of air is less compared to the refractive index of the water. And the detection of bubble plays a major role in many industries, that is nuclear power plant, where the bubble formation is not at all important, or it's not uh, desired. Okay, so we have to eliminate the bubbles in there, and also in the measurement of ocean acoustics, where the bubble usually make a seething effect. Okay, and you cannot get the data properly. The working of the sonar, it's been hampered. So for this thing, we have to make a good detection technology for the bubble, and for these two domains. So the bubble dynamics was it's very old. So bubble dynamics is usually explained by this Rayleigh-Placid equation, usual equation. Everyone knows this one. So where rho is the density of the this liquid. Okay, A is the radius of the this gas bubble. Okay, A double dash is the change in rate of change of the radius. Okay, correspondingly other terms are also defined in this way. Here PA is the basically the pressure within that gas bubble, which is the air pressure, and outside pressure we mention it as a P0, and A0 is the first bubble diameter, and then whatever is the change, we can mention that by AT, A as a function of T. So this is that equation, and one modification of that equation is known as the Rayleigh prosperity equation, so which is defined like that. And the third one is very important equation for the perspective of our work, that is the mineral resonance formula. So it's given like this way, that F naught is equal to 1 by 2 pi A root under of this one, where A is the radius of the gas bubble, and pi is the gas constant, rho is the density, and P here is the air pressure within the bubble. So now we'll come to our work. In our work, we have will use the dual frequency method. So in this thing, what we're doing, that two frequencies are used. One is the chart frequency. So chart frequency range is usually selected so that the bubble resonances, what we are getting from the mineral resonance frequency formula, that resonance of bubble will be excited. Okay, and the second one, which is basically your probing frequency. Okay, so in that thing, what we are doing, that a fixed frequency transducer we are using, so in here to detect that particular bubble in that particular area. Okay, and excitation is done by using this one. So it's shown in the thing that this is the pump frequency and this is the probing frequency. Okay, so this figure has been shown, and here you can see that the compressed air can come from here. So this figure has been taken from Newhouse and Shankar, Journal of Acoustical Society of America, 1982. And in the right hand side, you can see that various bubble pulsating modes are there. The first one is the monopole source. Second one is the dipole source. Like that, the other sources are mentioned in here. Okay, so this is the thing, that all these modes play a big role. So what we'll do, that mainly the monopole source plays a big role, because in here the displacement or the vibration part will be much more. So detection will be easy for the monopole source. Okay, and is the fundamental source. And the mineral resonance frequency formula is particularly gives the resonance frequency for the monopole mode only. So this mode will mainly concentrate and will mainly try to detect the bubble based on this mode. So we have different researchers who have previously earlier worked on this field. Okay, so we can see that the research has been started way long in 1959. Okay, by this works, and then previously the works was mainly experimental. Okay, and after that, currently the numerical trend has been coming due to we have different simulation softwares, and we have different simulating tools are there. So recently these three papers also worked in the similar domain in which we have worked. Okay, we have done whole simulations. Okay, so these are the things. Now, in this methodology, we'll explain that how the things we have developed in Abacus. So in Abacus, what we have done that we have taken the pipe, okay, some small cross section of the pipe so that we can numerically model it very easily and computationally easier. And we have taken the water part, okay, like this way. The cross sectional is shown in here, and also we have modeled the bubble also. So this bubble has been embedded within that water so that we can see that thing. If you take the cross section of this one, then we can see that part. So right hand side you can see one single bubble at the middle, and in the other figure we can see that there is 5 bubbles are there which are embedded within the water. So then what we have done that in the pipe, 2 parts are there where we are giving the excitation. So we have given one sharp excitation, which is basically your pumping frequency. So sharp across some frequency so that the resonance frequency of the bubble will be excited, and one probing frequency has been used, which is we known as single period frequency or SPF. So this has been done. Now, for the simulation purpose, we have used here the CFL laws, well-known CFL laws in here, and we have calculated in here based on the speed, wave speed, and what is the highest frequency we have used. We have calculated the wavelength element and SU3D4, which water and bubble both are modeled by using this thing. So this and the fixed time implementation we have got it from the CFL. So this has been taken, and one edges we have actually fixed in here so that it should not some rigid portion has been given. Okay, and like this way. So we have done 3 steps analysis. So first is the frequency analysis, then steady state analysis, then dynamic explicit and implicit analysis. So here what we have done in the frequencies analysis step, we have calculated simple modal analysis to calculate the frequency of the bubble. Okay, first frequency, fundamental frequency of the bubble, and second one, steady state analysis, we have got the amplitude also, okay, at that particular frequency. So the frequency has been verified in here, and then the wave propagation analysis has been carried out in dynamic explicit or implicit analysis in that thing. So here both the cases, in all these 3 cases, same models has been used, so convergence can be satisfied for both the cases. So here I'll come to the results and discussion part. So first we have done the frequency analysis in here. So 28 to 35 kilohertz we have used. So highest volume pulsation has been found, this one. So this is the frequency which we can see from this figure. And then we have done the dynamic explicit analysis also, following to the steady state analysis. So here also we have found near about same one, 32.6. So this is for single frequency case, and also we can see that near to the probing frequency or the SPF, okay, we have found that there is some sideband we can see, combination resonances. This term is called combination resonances, F2 plus F1, F2 minus F1, okay, or F2 plus minus n into F1, where n is the number of harmonics. After that, for similarly, we have done for the 5 bubbles case. So here the excitation range is from 10 to 50 kilohertz. And in that case also we have done the frequency analysis, and we have seen the mode shapes. Okay, you can see that single bubbles are vibrating in one cases, and that has been listed up in here. And then we have done the steady state and dynamic explicit analysis also. So here also we can get the following pattern like this way. Okay, and all the frequencies has been evaluated. So here, if we just compare that for single frequency, the mean rate formula and the what we have numerically obtained from dynamic explicit, we find that it's matching. But in case of 5 bubbles case, we can find that the difference is quite more when the radius of the bubble is much less. Okay, here you can find that the difference is more. Okay, but slowly if you go to higher radii, then you can find that it's quite matching. So this actually happened due to that in case of minaret resonance frequency formula, we have to imagine that it's a infinite, the bubbles are within a infinite liquid media, okay, which is not possible in here. Due to the surrounding cases, the natural frequency changes. So due to that thing, we are not getting the same thing. So these are the conclusions that we have got for a single frequency, single bubble and 5 bubble. We have got the frequency analysis, steady state analysis, dynamic explicit analysis, and we have also compared with the minaret resonance frequency formula. And we have found that once the bubble has higher radii, so in that case, the deviation from minaret resonance frequency formula is more, or it's more or less equal for big bubbles. So that will, this numerical estimation will be helpful in future for the bubble detection in water. So these are the references. Thank you.
Okay, thank you. So any question from the audience? Anybody has any question? Okay, then Tanmay, I have one basic thing. Is it a theoretical work?
Yes, it's a numerical work, what I have done.
What software you have used?
Sir, Abacus.
Abacus. Okay. Now, have you compared your result with any experimental result or theoretical, any published result? Any experimental result is available there?
No, sir. It's not going to be validated with experimental result due to this COVID situation. The student cannot come in here and do that experiment.
I am saying that if any theoretical experimental data is there available in the literature, did you compare?
Yes, experimental data is available, but for different cases, whatever we have studied for that thing, the experimental data is not available.
No, you could have done with the experimental data what is available to match your results so that you can publish the thing in a good journal, because this is good work. So just you have to validate something with some literature. Okay, then it will be a good work.
Yes, sir.
Okay, so you try to validate your result with some experimental data which is available in the literature. Okay, so that you can publish it in a good journal. Okay.
Okay, sir. Thank you.
Okay. Okay, thank you. So next is paper by TK Sahu. So his paper is comparative evaluation of typical submersible pumps. TK Sahu is there now?
Hello.
Okay. Okay, you can play that. Yeah.
Can you hear me right?
Yeah, yeah, it is right.
Yeah, I'm there. I'm there.
Good morning to all. I'm Tomesh Kumar Sahu. I'm Assistant Research Officer from Central Water.
You can mute your mic.
Yeah, I will mute you.
Okay.
I'm going to present my paper that is on comparative evaluation of typical submersible pumps. Before going to detail in my paper, let me introduce or let me give a brief information regarding my institute. CWPRS is a premier research and development organization in the field of hydraulics and allied research. It was established in 1916 to cater the problems related to hydraulics and to give proper and sustainable technological solutions concerned to that. As CWPR is having an expertise in various hydro sectors, and pumping or pump studies related to water supply and irrigation schemes is one of them, along with the performance testing of submersible pumps. Now, when or before I talk to the my paper, one thing I want to say or one thing I want to ask is that why it is required. So as of today, also if you saw, most of the agriculture activities in our country is basically dependent upon either rainwater, also the lift irrigation schemes. It is implemented in some states, not in all, or either with the help of submersible pump sets. So when we talk about these submersible pump sets, they are used in large numbers and they are used in remote locations. Therefore, it's very important to know about their hydraulic performance in depth so that it will be helpful to the farming community. Now, for moving forward to this topic, as a general user, when we go to the or go for the purchase of pump, we normally think about two things, that is flow, and second thing is the head. But beyond these things, we have to look for the minor characteristics that are going to affect the performance of pumps. And the same thing I'm showing in my slide. When you saw the operating characteristics at constant speed deviates a little when the operating voltage fluctuates about say 5 to 10% of the designed one or the rated one. The same pumps are also tested for the head variation of minus 25% and the 10%. If I say about head variation, that means I can vary the head by means of the throttle valve. Okay. So when I vary the head, the discharge will automatically head. So it should be in comparison with the ideal operation characteristics of the pump. And it is very important to design the pump or to the performance of pump in the actual field. So to do all these things, first thing that we need is the infrastructure to test the pump, and CWPR is having a well defined and installed infrastructure in their labs, which are having a sum of capacity about 200 meter cube and 4 meter depth. That is very much sufficient to provide a actual submerged condition of the submersible pumps. The outlet of the submersible pump is connected to the manifold, which in turn later connect these pipelines to the volumetric tank. The line size of the circuit will depend upon the outlet of the pump. Thereafter, later on you will see on my slide the circuit diagram of our volumetric lamp. The volumetric tank is having a pepper pot and all the provisions to control the turbulence and create tranquil conditions in the flow system so as to avoid any problem for the measurement of flow and head that can affect the performance of the pump. Now, as you saw in this slide, a pump test circuit and instrumentation, it will have a proper electrical supply system. Thereafter, a pump installation system in which submersible pump and motor is installed or submerged into the sump, and the outlet of that pump will supply the water to the volumetric tank, which in turn connected with the control valve, Borden pressure gauge, baffle plates, digital timer. One thing that is not displayed in this system is a instrument, or I'd say energy meter, which display all the instantaneous output from the pumps. So we can record all this simultaneously when the pump is in operation. Now, after having set up requirements, things next will be the procedure, that how we're going to start the testing of pump. So before starting of the pump testing, a span of time will be given to the pump manufacturer to check the or to go for the preliminary checks of the pump testing. So as to get ensured that to set the pump parameters with the defined settings. Thereafter we go for testing of pump. So while testing of pump, we set a defined head at a preset value and measure the discharge given by the pump with the help of volumetric flow measurement technique, which is basically a technique in which our volumetric tank is filled with water between the two electrodes that is having a fixed volume, and that's what I'm saying. It's a volumetric measurement technique. So, and the net amount of time taken by pump to fill that fixed volume is recorded in the digital timer, and with the help of that we can evaluate the flow given by the pump at that defined set head. At each test point, various parameters are recorded. Okay, I mean to say is that for one head we record various parameters, for another head we record various parameters. When we recorded this one, when we saw our volumetric tank is near about to fill in 50%, and that parameters record from the energy meter installed in the circuit. Yeah. The procedure was repeated for various delivery head from minimum to maximum to cover the entire operating head range from -25% to 10% of the test. This was continued till the maximum limit of operating range is reached. The power loss in the cable motor terminal is also computed to calculate the overall efficiency. To ensure the motor is not overheated during the range of operation, the winding current for each pump is also recorded and compared with the specified values given by the manufacturer of the pump. Now, pump test result need to be conducted at available frequency. Yeah, but as per the procedure given in the IS 9137, it should be 50 Hertz. But frequency is not actually every time 50 Hertz. It is variable, 49.8, 49.7, 49.6, sometime like that. So we have to scale up, or we have to modify that values to that 50 Hertz frequency as per the procedure or mentioned in the IS 9137. Now, as I say, the pump testing will carried out for different heads. Now, similarly, for conducting overload test, the value of initial motor winding resistance has been noted out, and that is known as the cold resistance of each of the three faces of the connecting cable. Now, by throttling the wall of the delivery pipeline of the pump, the value of input power to the motor is adjusted to the duty point declared by the pump manufacturer. The value of power factor and current drawn by the motor at this set value is recorded and noted down for measurement. Now the pump was then subjected to overload power, that is 1.2 times of the grid power, as indicated by the end user or the supplier in the tender specifications. Now, After operation of 1 hour in this overload, the motor was stopped and immediately the values of the winding resistance has been noted down, and that is what we call hot resistance of the each of the 3 phases with the help of micro distal milliohm meter. The temperature rise of the windings is also determined with the help of relationships given by the IS 9137. Now, after doing all this, when we tabulate all these parameters, then we have the result that I shown in the form of table in the slide number 11. So as you know, the pump manufacturer claimed the efficiency and discharge at actual duty point is 60% and 102 meter cube per hour. But after testing of the pump in our labs, we came to know that pump A is delivering the efficiency of 61.25% and pump B is delivering the efficiency of 60.21%. And the discharge will be 104 meter cube per hour against 102 meter cube per hour, and for pump B it is 109 meter cube per hour against the 102 meter cube per hour. Now, as I told you that we test the pumps on different heads, so you can see the results here at the point number 5th, point number 6, and point number 7, which determine at plus 3 meter of head, if we put up or if we load on the pump, then the discharge value is given by is 84 and 98. And what is the head at actual duty point against the 18 meter is the 18.3 and 19.5. Similarly, I told you the current of the motor or the current drawn by the motor is measured for the overload test. They are also mentioned out there, how much they will taken or how much they will be observed. By noting down these values or having an or putting up these values in the formula, we can able to fetch out the efficiency of the pump at the duty point, that is at the design point. And that will provide us a definite idea to choose the pump, that which one will we have to go for that. It will ultimately depend upon the end user to choose the pump. Now it's time to conclude my presentation. Thank you very much.
Any question to the audience from the audience? Okay. If anybody, no question. Then I have one doubt. Means I just want to know, Mr. Sahu. So just this, you have measured the resistance, all these things. It's a submersible pump, is not it?
Yes, sir. It's a vertical turbine submersible pump.
Okay. So your motor is outside the water or is inside the water?
No, sir. It is fully inside the water, and that too, it is well submerged in the water.
Okay. Now, how you measure this resistance, all this within this inside this water? That's why I just wondering.
Yeah. So actually, well, the pump is or the motor is inside the water, but the cable came out to that motor is connected to the energy meter. Okay. So they will give that directly reading of what is the input of motor in terms of voltage, amps, the power factor. These are given by energy hour meter.
Okay. Okay. So now you have checked with the new pump or the old pump also?
No, no, sir. Actually, as per that, I am saying that it is for the irrigation department, Uttar Pradesh. So they have the condition that they will purchase some about 400 pumps, 500 pumps from us, from manufacturers. But they put up one condition that you make 25% of the production, and then out of that 25% of production, we choose one or two in a random way, and they send these pumps to CWPRS for testing, and that these new pumps we can test out here in the lab.
Okay, so that offset means off design condition is a different loading condition. You checked with the pumping, the power head, all these things. Is it?
Yes, sir. Because actually the thing is that we have the pump should have to run in a proper efficiency range with the different parameters. Sometimes with a different load or with a different head and various flow rates, and sometimes it's like that. So these things we have to test for the under various conditions how well it is performing. Because in the areas where it is implemented in the future after testing and after setup after clearing of the all the procedure, they have to perform in different conditions where the voltage, current, and requirement of the various field problems are there. So as per that, we can try to go for that.
Could you check the temperature rising of the motor, all these things in this condition?
Yes, sure. Because it is the most important one, and the last because at the last moment after the complete that head variation and the discharge variation is over, we test the motor for a continuous operation of 2 hours with the overload condition. So ultimately, what happens? The current drawn by motor will increase, and that will increase the temperature of winding. So how much it will increase? It should be limited by the irrigation department people that it should not exceed certain limit. So if it is exceed certain limit, then the pump will go for fail.
Okay, that we measure with thermocouple or something else?
No, sir. It is by digital resistance ohm meter.
Digital?
Resistance ohm meter.
Okay, ohm meter. Okay.
For 3-phase separate.
Okay. Thank you. Very good work. Okay.
Thank you.
Next.
Sir,
okay. So next paper by Miss Jyoti Gupta. Her topic article is jet shear flow. Jet shear layer study of round elevated jet in cross flow at low velocity ratio. Okay.
Good morning to all of you. I'm Jyoti Gupta. I'm giving presentation on jet shear layer study of round elevated jet in cross flow at low velocity ratio. The presentation outline. What is jet in cross flow? The jet exhausting into the cross flow comes under the category of jet in cross flow. Based on the source of emission, the jet can be broadly classified into two categories. First is wall mounted jet, where the jet is issuing from an orifice made on the wall. This is the wall where the orifice is made. So from here jet is exhausting. And second is the elevated jet. The jet is exhausting from the elevated source, that is from the stack. So this is the jet coming from the stack. So it is called elevated jet in cross flow, and this region is called jet wake. It is forming behind the jet, and this is called the stack wake. It is forming behind the stack. These are the application. First is the industrial application, which includes chimney flow, gas flares in oil refineries, wastewater disposal into deep oceans, and the natural occurrence includes plume of volcano, smokes from fire, and bivalve clam jet flow that is generally visible in oceans. And third is the aeronautical and mechanical application that includes vertical short takeoff lift aircrafts, cooling of turbine blades, turbojet thrust bearing. These are the non-dimensional numbers which are used in this study. First is the density ratio. It is the ratio of density of jet fluid to the cross-flowing fluid, and it is 1 because the fluid used for both the flow is same. So this makes the jet to be non-buoyant. And second is the momentum flux ratio. It is defined as the ratio of jet momentum flux to the cross momentum of the cross flowing fluid integrated over the same area. So this expression can be simplified as the ratio of jet velocity to cross flowing fluid velocity, because we have density ratio 1. So the next is the jet Reynolds number, which is defined based on the jet velocity and stack external diameter, and the Reynolds number based on free stream velocity is defined as like this, and the aspect ratio is the ratio of the stack height to the diameter. In present study, the aspect ratio is taken as 9, the shape of the stack is circular, and the Reynolds number is maintained at 2000. The jet Reynolds number is varying from 163 to 1493, and the velocity ratio is between 0.16 to 1.5. So these are the literature survey done by these authors on the jet shear layer, where the J. Andropoulos has examined the jet shear layer and found that the jet shear layer vortices forming at the upstream and the downstream is just got deaccelerated and deaccelerated in the comparison with respect to inner side of the vortices, that result in stretching, and in far downstream opposite phenomena is observed which result in compression. And further, Kelso observed the source of vorticity for the jet shear layer, and what Lim have observed, they have just modeled the continuous jet as a series of vortex rings that are just distorted by tilting, stretching, and interlocking arrangements. And further, Lim has gave the concept of vortex loop of the shear layer. So these vortex loops are just formed via the deformation of cylindrical jet that is coming out from the stack, and thus it gives rise to the formation of two rows of vortex loop at the windward side and at the lee side, and these two vortices are separated by counter rotating vortex pair. So when the jet velocity is maintained at 0, the same model is representing the flow field of finite cylinder. So the flow field of finite cylinder is subjected to two different boundary conditions, that is end condition and two end condition, that is free end and the wall body junction. So due to this, the resulting flow field is resulting flow field is complex and three-dimensional. So to capture the time-dependent flow structure with accuracy is the prime motto of this present study, and the objective is qualitative characterization of shear layer structure of an elevated jet issued in the cross flow by dye visualization technique. So this is the experimental setup. The experiment has been done in the low speed recirculating water tunnel, and here this is the test section where the model is kept. The same model is shown in this figure also, where the circular stack is kept on the false floor, and from below the false floor the dye is injected for tracing the jet shear layer, and the laser Doppler technique has been used to measure the mean velocity. So at varying velocity ratio, we are getting different flow structures. At r equals to 0.3, we are getting clockwise downwash vortices. That is, at this velocity ratio, the jet is not having enough momentum against the cross flow. Therefore, it is deflected at a large angle and bent towards the wake of the stack. And these the vortices which is visible at the upstream side are the clockwise vortices, that is also visible in this figure, and this is the rotation is just observed from the sequence of the images in video frame. So these are the clockwise vortices which is observed at the upstream side, and many authors have referred it as a Kelvin-Helmholtz instability. And in the lee side, the vortices quickly disappear, and while the upwind vortices persist for a long time. At r equal to 0.5, actually this velocity ratio is maintained at 0.5, just holding the jet just holding the cross flow at constant, increasing the jet velocity. This jet ratio is maintained at 0.5, and at this velocity ratio, anti-clockwise upwash vortices are observed, that is visible here, that is anti-clockwise vortices, and the phenomena of formation of this vortex can be seen here. At time t equal to 0, it is visible that the vortices formed is a clockwise vortices, which on further evolution form into two vortices, that is, one is clockwise, which is the continuation of the initial clockwise vortices, but this anti-clockwise vortex is formed. Why? Because because as the jet is exiting from the stack, is just dragged by the cross flow. So as the jet is getting enough momentum, it try to penetrate into the cross flow. That's why this anti-clock vortices starts to form, and these two are the further evolution of these vortices in downstream direction. So at r equal to 1, we observe the swing induced mushroom vortices, and this swing induced mushroom vortices is just formed due to the formation of due to the swinging in back and forth direction of the jet. And this phenomena is just close up of this phenomena is made in this figure. Initially at time t equal to 0 and time t equal to 0.49, the jet oscillate towards left in this direction and simultaneously bend with the cross flow. It is just bending with the cross flow. So at time t equal to 0.99, the clockwise vortices is formed at the lee side of the shear layer, and anti-clockwise is just begin to form at the upstream. And at t equal to 1.48, jet swing towards the right hand side, and in this way the mushroom vortices are formed, and this terminology is used by the Said et al in their paper also. At r equal to 1.49, we are getting the jet-like vortices. At this velocity ratio, due to enough strong impingement, the jet is just starts to penetrate into the cross flow, and very near to the jet exit, the behavior of free jet vortices are observed. And also series of counter rotating vortices are appearing intermittently at the upstream side of the shear layer, and also it is observed that as the velocity ratio is increasing, jet bend over region is also increasing. And these are the conclusion we have observed that 4 categories of shear layer we are getting based on the range of velocity ratio. From 0.16 to 0.4, we are getting clockwise downwash vortices, and between 0.4 to 0.67 we are getting anti-clockwise upwash vortices, and between 0.67 to 1.03 we are getting oscillation induced mushroom vortices, and between 1.03 to 1.5 we are getting jet-like vortices. At a low velocity ratio, that is less than 0.4, the jet bends in a very short interval of time and at short downstream distance, which is responsible for the downwash. And also the clockwise downwash vortices are typically the Kelvin-Helmholtz instability occur at the interface of the jet and cross flow. And till now in this presentation I have shown all the qualitative results. For quantitative analysis, it is planned in future where the statistical measure will be considered to analyze the elevated jet and cross flow. These are the references used in this study, and thank you.
Okay, thank you, Ms. Jyoti.
Thank you, sir.
So, open to audience for question. Any question? Audience, question? Okay, Jyoti, then I have a couple of questions. One is, how you continue to measure the Reynolds number as R is equal to 2000? How you maintain the velocity Reynolds number 2000?
Actually, sir, the cross flow is just in our water tunnel. It is calibrated with the help of VFD, that is VFD drive. So at different frequency, we have just already measured the cross flow velocity with the help of LDV, and that's why we have just calculated, and based on the external diameter of the stack and the cross flow velocity, we have calculated the Reynolds number.
Okay. Second question is, how you did the visualization? So what are the camera frame speed, all these things?
The camera frame speed, frame period and FPS is actually 600 FPS, and we have used 150 watt light, and also we have used a LED panel as a background for the stack, so that we have bright illumination.
Okay, but the images you have shown, the visualization images, dye images, and the schematic you have drawn, there is a little mismatch. Means all the results are not exactly matching with the whatever your schematic you have shown, and the visualization images coming from the dye is not exactly matching. You could have given more better picture of the dye
Yeah, we
visualization
have
so that you
also
can
done
match.
LIF. Yeah, yes, sir, yes, sir. We have also done LIF for after that. So that schematic is generally is actually perfectly matched with the. Actually, this is the bulk flow visualization, which is giving the image on a projected plane. And now after that, we have done imaging in a one plane using LIF.
Okay, that you are matching with the thing. That is matching, is it?
Yeah, yes, sir. Perfectly, every circulation is visible there.
Okay. Okay, good work. Thank you. So, okay. So next, this is the last paper of this session by Atendra Kumar. Atendra Kumar is there?
Yes, sir.
Okay. So the paper is study of unsteady flow separation for shear flow past an array of two square cylinders. IIT Mandi.
Hello everyone. Myself Atendra Kumar. Currently I am working as a postdoc fellow at IISc Bangalore in computational data science department. So my research interest in the area of computational fluid dynamics. Today I am going to present my work titled Study of Unsteady Flow Separation for Shear Flow past an array of two square cylinders. So what is shear flow past block bodies? So these types of basically flow phenomena have various important applications in computational fluid dynamics, like flow around two suspension bridges and this around tall buildings, ocean structures, etc. So basically, these shear flow problems occur in high viscous fluids. Like one is uniform flow, one is non-uniform flow. Shear flow basically is a kind of non-uniform flow. So in that, basically, in non-uniform case of flow, the fluid layers have different velocities. In uniform flow, all the layers of the fluid are of same velocity. So these types of flow occurs in oils, petrol, toothpaste, etc. Whatever. Boundary layer flow is also a type of shear flow. So mathematically, the flow is governed by the Navier-Stokes equation. So in this work, basically, our main target is to study the flow separation from the surface. So in case of flow past block bodies, flow separation occurs when the boundary layer travels far enough against an adverse pressure gradient. So then the fluid basically detaches from the surface of the object in mostly boundary conditions. So now, so basically, in this case, we have used this finite difference method to solve these governing equations. These methods used quite frequently in computational fluid dynamics. The development of these methods basically based on this Taylor series expansion. So now standard finite difference approximations, which are central difference, forward, backward distance, are not that much accurate for to give numerical solutions of these highly nonlinear governing equations. So there is a need for development of higher order accurate numerical methods, finite difference methods to solve such type of problem. So this higher order compact scheme basically which we use here in our case, which is developed by Kalita. The idea is to use the original PD to replace the derivative terms to make it higher order accurate. This scheme basically second order accurate in time and fourth order accurate in space. Compact means basically the distance stencil computation of the of a variable at particular point comprised only directly adjacent points in the neighborhood. So we use this structural bifurcation analysis to analyze the mechanism of distribution separation. This term was first introduced by Henry Parker in 1885. So this means basically changes in the topological structure of the phenomena when a parameter varies. So in our case, basically in case of fluid flow, this flow past solid object also go through the process of bifurcating topological structure as time as a parameter. So basically the for this one parameter value divergence free vector fields, which is our case basically, bifurcation occurs when there is a degenerate single point occurs for a variable at point at some time. So that time basically is called the bifurcation parameter and the point at bifurcation point. So this is basically this concept developed by Gill et al. Next, basically in this case, in the case of flow past solid object, this bifurcation occurs for extreme function verticity formation of Taylor equations if these four conditions are satisfied simultaneously at a point at time, at some time, at the verticity side the extreme. You know, somebody defined as one. So after decision of these equations 3 and 4 by using Harvard complex scheme, we got the system of algebraic equations we solve using hybrid biconjugate gradient solvers, like solvers. Okay. So now the physical definition of the problem. The problem is shear flow past two square cylinders in tandem. Tandem is series. So basically these two square cylinders placed in an infinite physical domain. Now the computations are possible only in finite computational domain. So we bound this infinite physical domain to finite computational domain by using suitable boundary conditions. We use this linear shear velocity profile at inlet to model this shear flow phenomena, and the slip boundary condition on the upper and lower boundary of the computational domain, as well as this convective boundary condition is used at the outlet, which is more suitable for such types of fluid flow than other boundary conditions. It also provided smooth discharge of what is generating from the generating behind the cylinders, the boundary. As well, on the other hand, the cylinder surface are considered as the no slip. Here, cylinder 1 we call later upstream cylinder and cylinder 2 as downstream cylinder. So before doing the vast computation for different parameter values, we validate our results with the existing results in the literature. So we can see, so from here we can see that our results are very close with the existing results. So in this slide, we show the verticity contours and corresponding stick-line patterns for R equals to 200 and S equals to 2.5. Then S is the basically gap between the two cylinders. And in all the cases, we fix basically, we take the Reynolds number as 200. So in that case, we have seen that there is no for this small gap between the cylinders. Verticity generates only behind the downstream cylinder. There is no vertex generated in the two cylinders. So this basically phenomena is similar to the phenomena of flow past single square cylinder. So for k equals 0.0, we have seen that phenomena almost symmetric, but with increasing the shear rate k 0.1, 0.2, we have seen that the phenomena becomes non-uniform, and this vertex generates of different strength and size behind the downstream cylinder. Further increasing k to 0.2, we have seen that the verticity almost tends to separate from the lower side of the cylinder. They are not present in the downstream for a long time. A stick line basically defines like if you have a hollow cylinder, you have a die particles in that die inside that cylinder. You put a hole on the surface of the cylinder, so basically, and eject some particles from that hole. Basically, these particles are follow the same path as the verticity contours, so which is clearly seen from the stick line patterns. at the path of this vorticity can move. Next, the central and velocity fluctuation u versus x and v versus x clearly shows the basically this property of the shear flow. In the phase diagram in this for this parameter value clearly shows the periodicity of the flow phenomena, which is also seen from the vorticity contours. Phenomena is completely periodic with different periodic values for different shear parameters. When we increase Assam in the gap between the cylinders to 3, we have seen that the vorticity generated from the upstream cylinder heads to the downstream cylinder and alters the flow phenomena behind the downstream cylinder. Although there is no vortex setting between the two cylinders because there is because of non-sufficient gap between the two cylinders. Next, the circular velocity fluctuation, so the shear flow phenomena, shear flow properties of the phenomena. And the phase diagram clearly shows the periodicity of the flow phenomena with different strength of the vortices. So next we study this bifurcation analysis of the flow phenomena. So from here we have seen that the 4 conditions which are satisfied at P1 star and P2 star. So for different, I mean downward flow and upward flow. So in this case, the 2 bifurcation points occurs on the upper and lower sides of the cylinder opposite to each other because of the symmetric nature of the flow at the same time at 0.3093. Both the bifurcation occur at the same time. So this is the topological justification of this bifurcation. We have seen that before bifurcation at t equals to 0.25, there is no vorticity generated from the upper and lower sides of the steam cylinder. Although after the bifurcation, there is 2 vortices generated from the developed from on the upper and lower sides of the steam cylinder. So which is clearly shows that these 2 spaces are not topologically equivalent, which is also clearly seen from the surface vorticity plot. So next we study find this bifurcation points for r equals to 200 and k equals to 0.1, which is clear. You've seen that 2 bifurcations occur from at different times and also not opposite to each other. So this is clearly so that so the non-uniform nature of the flow. Next we show the location and timing of the. So basically this bifurcation points occur for all parameters are same process applied. So for other parameters we have shown in the table form. So here we have seen that there is no specific pattern following in the time or point due to the complex nature of the non-linear nature of the flow phenomena. There is no pattern follow for this bifurcation points. This is the bifurcation points on the second cylinder. So for this small gap 0.5, there is no bifurcation occurs on the second cylinder. Okay, which is clearly seen. These are the references that we used. Thank you for your attention and very please.
Okay, thank you, Mr. Atendra, Dr. Atendra. So
yes, sir,
now open to the audience for question. Okay, if no question, then Dr. Atendra, I have just a few questions regarding your study. This higher order HOC method is how computational efficient this method compared to finite volume, all these things.
Oh, okay. So actually, sir, this method is basically 4th order accurate in space and 2nd order accurate in time. And this method is also, I mean, unconditionally stable. Okay, because we are using this Crank-Nicholson type discretization.
Okay.
So that is the main, I mean, important fact of this. I do not aware this finite volume and finite element method that much actually.
Okay, so that means you are saying accuracy wise, you that's why you used for this method due to accuracy.
Yeah, accuracy and compactness of the
this computational time also quite high for this method. Because
computation time,
higher order accuracy, the computational will be how much time you took for this simulation for say one set of results?
Yeah, simulation actually up to time t equals to 500, it takes around 4 days to complete it.
Mm-hmm. Okay, have you measured, have you compared your result with some experimental data?
Yeah, yes,
Because
sir.
there are lots of experimental data on this array of cylinders.
Oh, actually, I don't find this experimental data for this 2-cylinder case. I mean, for shear flow case, but for uniform case,
shear flow you may not get, but without shear flow, just uniform flow, you will be getting. You have the data you can see in the literature.
Okay. I have mostly data for this single cylinder case. For
array of cylinder also data is there. You can check in the net. Okay, I think. Okay. Because one of my student has published one paper on this array of cylinder. You can check paper. Okay. In experimental results are there. Although Reynolds number is little high, but you can do some simulation at higher Reynolds number, suppose 300. You can check with your result because it's a good information for the shear flow, because shear flow information is very less in the literature. Okay. So
sir, actually for R equals to 300, the flow becomes, turbulence, like 3D effect.
Yeah.
So I did only this 2D computation till now.
No, I think 200
3D,
also is there. 200 also array of cylinder data is there. So there is a review article, I think by I don't remember his name. I think Simon or somebody else. So they have done array of cylinder. Okay. We can check their result. They have a literature, that is a review article. So there you can get some data for 2-cylinder. Okay, it's fine.
Hello, sir.
Thank you, sir.
Yeah.
Hello, sir. This is Harshad. So I would like to thank all participants for contributing their work with us and to this conference. And I also would like to thank Professor Datta for joining this session and chairing this session. So with conclusion of this session and also day 1, I would like to invite you for tomorrow's keynote lectures by Professor S. Balchandar from University of Florida in Hall 1, and Professor Partho P. Mukherjee from Purdue University in Hall 2. The keynote lectures will be started at 9 o'clock in the morning. So if you are with your permission, sir, I would like to conclude this session. So
thank you for this all the participants for their presentation.
Thank you, sir.
Good work. Okay. Thank you all.
Good evening, sir. Have a nice day, sir.
Okay. Thank you.
Leave कर गया? Yes.